Yeah, here is what we have for you today. So we will have 7 great keynotes, each of them half an hour long. And our speakers will talk about a wide range of topics, from perception to behavior planning to planning. Yeah, just like the recent conferences, foundation models, large language model, vision language models get more and more popular. And if you're a skeptic or not, today you will definitely hear some takes from our speakers on those, and maybe convince you that they are the next big thing, or make your or make you see what your ideas are. Yeah, the other thing is, this year actually our workshop is in the 7th year of iteration. This is even without counting some of the predecessor workshops we emerged out of. And I think it's really nice that as a workshop in such a fast changing topic, we kind of kept on going with the flow and have, like always, the newest and greatest talks and challenges here. And yeah, maybe as a small administrative update, all the talks except of Kashyap's will be here live by speakers we have in the room, with Kashyap not being able to join, and he will give his talk via Zoom. As I already mentioned, we have our challenges, as it's kind of customary in the workshop. This year, we will have 8 very interesting challenges from our partners, from the Waymo Open Dataset Challenge, and then from the Argoverse Challenge. And as usual, it's always great to have them here and see what kind of the community can make if you give them nice data on challenges. Again, as usual, we also have our paper track. This year, we actually received 37 submissions, and we collected over 100. We collected reviews from over 100 reviewers, and each paper got at least 3 reviews in. At the end, we selected 14 submissions, so we had an acceptance rate of 38 papers. And you can find all the papers in the proceedings or on our homepage. And this is also a bit of a shout out. Please, if you go for lunch, have a look at the posters. They will be in the ARC building. And the posters should be the poster walls 334 to 344. And this will be hosted during our lunch break from 12 to 1:30. Yeah, again here, really big thank you to all the reviewers and authors. Without them, this would definitely not be possible. Here is also a list of all the papers. I think there are quite some nice buzzwords in here, but as said, if you are interested, have a look at our homepage. And you can easily find them. Now, as I already mentioned, we are in the 7th year, and keeping a workshop alive for this long wouldn't be possible without great organizers. And kind of it's a real huge thank you. I think for a lot of them, it's now like a lot of years that we do it together. And I think keeping kind of a nice core of experienced organizer, but also fresh ones coming, really makes this workshop keep alive and push through it. So huge thank you for all of the organizers, and you will see us here in front if there is any questions you have. Okay, maybe also a short note for the talks and questions. So if you are attending remotely and you have questions about one of the talks or questions during the challenge, just drop us the questions in the Zoom call. As the organizers, we will keep track of them and then ask them during the Q&A. And if you're in person, at the end of the talk, just raise your hand. You can come to the microphone and ask the questions. So, and with this, we can actually go a bit to our program. So we have like 4 main blocks of talks. So we will start at 9 with Bolé, have a coffee break, and we will then have actually 2 coffee breaks and a lunch break. So the coffee breaks will be half an hour. They will be at 10 and 3:30, aligned with the coffee breaks from CVPR, as well as the lunch break again will be aligned with the lunch break from CVPR. So don't worry, you get your food and coffee. Lunch break, as mentioned, there will also be the poster session. Now, if you want to have kind of a, if you at some point wondering where can I find the schedule, don't worry, everything is very prominent on our homepage. So just go to WAD.vision or CVPR24WAD.vision, and you will find all the information with all the talks and orders and even titles. So yeah, with this, actually, my opening remarks are done. And the boring part of the day is over. And we can actually get started with the interesting part and get the speakers and challenges going. Okay, Bolé. Yeah, true. Yes, just did you share the screen or the? Yeah, it's on. Yeah, there. I think it will not be on the screen. Okay. It doesn't see nothing on the screen. Great. Okay. So it's my great pleasure to introduce our first speaker, Oli Zhao, who is an assistant professor at UCLA, working at the intersection of computer vision and machine autonomy. His work focuses on an embedded AI system, where he kind of tries to focus on interpretability, generalizability, but also safe methods that align with humans. Before starting his position at UCLA, he obtained his PhD from MIT and was an assistant professor at the Chinese University of Hong Kong. So it's a great pleasure to have Bolé here on stage.
Yeah. Yeah, so thank you for the kind introduction. Thank you for joining me today. So before I get into the talk, I would like to do a quick survey. So how many of you from industry? So please raise your hand. Okay, we have a lot of industry people. So how many of you from academia, like a student, universities? Okay, like 1/3, right? So as you can see, so this autonomous driving research, right? So it's really a community of both industry, academia, right? So, but over the years, so we see a clear gap between academia and research. So today I would like to share with you some of our efforts to bridge the gap between academia and industry for autonomous driving research, right? So as I said before, over the years, so the gap between autonomous driving industry and academia become larger and larger, right? So autonomous driving companies have data collection vehicles, running around 24/7, right, collecting a lot of data. They also have a lot of GPU servers to train their models. On the other hand, for the university labs, we only have this kind of a small-sized toy carts running on this toy track. Then also have a limited number of GPU, like 4090s, to train the models. Right. So the issue is how can we bridge the gap between academia and the industry? So I believe the two key elements to bridge the gap is the access to the real-world data as well as access to the simulators. Right. So those are very important for our university research because eventually, autonomous driving company will also hire talent from universities. So we need to better train and mentor our graduate students. Luckily, over the years, autonomous driving companies already realize this is a very important issue. So they start releasing a lot of open source data sets, right, such as Waymo open data sets have been used, and a lot of challenges and a lot of progress there. Many other companies also release data such as new plan, new scenes, also the Argoverse 1 and the Argoverse 2. Right. So with so many data sets, still some issues, right? So because those data sets are released by different companies, they are in different formats. So it would be great to have a common format and the infrastructure allow users to easily adapt and use those data for their research. And on the other hand, we also have a lot of progress for the driving simulations, right? So NVIDIA have this drive sync, can synthesize a realistic visual appearance and physics. Also, WAD have this Unisync that follow a data-driven simulation, can render realistic scenes. Also, Wavy have this GIA called word model that can generate a realistic visual appearance. But there is a major issue out there. They are closed sourced, right? Those work are more like showing muscles, but not accessible to the communities. What we really need is this open source driving simulators. But take a look at the current open source simulators, such as car racing and smarts. They are pretty simplified, right? They have simplified assets and also simplified scenarios. I would say Kala is a good example. So it has been developed many years, have been used in research community very widely. But the issue with Kala is that they use the Unreal Engine. They also have this fixed asset maps. So it's really hard to load real world data in the simulation and run those generalizability experiments. So then in order to tackle this issue, I would like to tell you our stories, our efforts on bringing this real-world data into simulation, right? Because we already have so many real-world data out there, then it would be great if we can load this real-world data into the simulation, then have this common data and simulation infrastructure to run all this data. And also, we want this infrastructure fully open sourced. So our efforts start like 3 years ago by building this driving simulator called the MetaDrive. So we have this MetaDrive name before Facebook renamed them as a Meta. So for this MetaDrive design, we follow a data-driven simulation. So we allow user to generate a new environment, also loads real-world data. Also, this simulator is pretty lightweight. So on a standard PC, it can run more than 500 FPS. We also open source this simulator fully to the public. So far, it has been downloaded more than 40,000 times with hundreds of GitHub stars. So we started this project like in 2020. But the papers with this simulator have been rejected 3 times from various conferences, right? So it's a very frustrating experience. So we almost gave up this project, right? So it's hard to publish these things. But eventually we submit to DeepArmy and to the CVPR community and get accepted to a journal paper. So this demo video showing you this some traffic blocks we defined, and also we have a procedure generation algorithm that can sample from the traffic blocks and generate new environments. More recently, we try to improve the data module of this simulator by introducing this scenario net. Right, so the scenario net is a data module on top of a MetaDrive simulator that allow us to load the scenario traffic data from different data sets. So this demo video showing you this loaded traffic scenes from the new scenes data. So because we have annotation and HD map from the data set originally proposed for some data collection or proposed for object detection tasks. So we can load the annotation and then recreate those simulated scenes in the environment. So we also can provide this top-down view and all those ground truths. We can load many different traffic scenarios from different data sets. So this demo video is showing you these traffic scenarios loaded from Waymo and the new plan. So far, totally, we have 500,000 traffic scenarios. So we standardize the format, then we can easily replay those scenarios. We also can make this scenario reactive. So if the ego vehicle interact with the traffic vehicles, there will be some rule-based policy take over control of the traffic vehicles. So here is a quick overview on the system design of ScenarioNet. So we first have this data layers allow us to build this API tailored for different data sets, right? So if you have your own data set, you also can write some API interface. Then you can load this traffic scenario into the simulator. Then we have the system layer that can allow us to process those data into like training and testing, and also do a lot of backtracking for the data we have. Then we have the application layers that user can easily develop their own applications, like users data for single agent imitation learning, reinforcement learning, or study some multi-agent learning problems. Also, you can use a scenario for some scenario generation, and also for autonomous driving stack testing. So it's a very flexible frameworks that allow users to develop their own modules for their research and development. So when we have this data loaded in the same infrastructure, then we can do some data comparison. The first thing we do is build some feature embeddings for those loaded scenarios and do some t-SNE visualization. So this image is showing you the t-SNE visualization of the traffic scenarios loaded from different data sets. So we first have the traffic scenarios generated from the procedure generation, like a rule-based algorithm on the left in orange color. And then we also have the Waymo scenario as well as new plan scenario. So the first observation we have is that we can clearly see the gap between the synthetic scenario and the real world scenario, right? So quite a distance from each other. Also more interesting, like for this real world scenario, we also have the difference like between the Waymo and the new plan data set. The reason is that for new plan data, so half of the data collected in like Singapore, right? So which is more like city countries. So they have more narrow streets versus Waymo data mainly collected in like United States. So they have a more larger intersection with the like 10 number of lanes, right? So from this data visualization, you can see if you train your models on certain data set, it also will have hard time to generalize to new environments. So I guess that's also why this autonomous driving company will collect new data in some new cities, because they have a different map structure and the traffic flows. So I'm from LA, so I think Waymo recently running a lot of the data collections at the LA, try to overfit the cities so they can do better autonomous driving at LA versus the model trained on San Francisco. So after we have this infrastructure, so it can support many new research opportunities, such as here single agent and multi-agent learning. And also we built a bridge to the Sumo simulator, which is a widely used simulator in transportation research. So we can use this autonomous driving to study the simulator to study some transportation research problems. Also, we evaluate, we can mount our simulator with some AD stack. So here, this demo video is showing you the evaluation of this Open Pilot, which is autonomous driving stack, like on your dashboard cameras. So you can download, it's open source software. You can download, mount on your dashboard cameras and wire into your car. So you can access basic autonomous driving functions. Also, we have this bridge to a raw system, allow user to use a simulator for this their own autonomous driving stack research and development. So after we loaded this real world data, so one thing we noticed is that those data are pretty noisy and fragmented, because those are the scenario data collected in real world. So a lot of occlusions. So one way to improve that is we can train some generative models, right? Use a Gen AI for traffic scenario generation. Like after we train this generative model on this noisy real-world data, then we can sample from the generative model and generate a more complete and long-term scenario data. So here is an attempt we have done last year. So we developed some model called Traffic Gen that can learn to generate diverse traffic scenarios on the data set. So follow this two-stage generation process. Like first learn to place the vehicle inside, then generate this long-term trajectories by sampling, keep sampling from this motion prediction modules. So this traffic scenario generation is become quite a popular topic, right? So recently there are more like diffusion based measure to generate those scenarios. So here I show you some of the generated scenarios on different HT map. Right? Then you can see the pretty realistic traffic flow. Even for the same map, we resample the models so it can generate very diverse traffic flows. So you can also use a generative model as a prior to augment the existing scenario or extend this missing trajectories. After we generate the scenario, then we can further load this scenario into our simulation, right? This our MetaDrive simulator can further provide the 3D visual rendering versus the generated scenarios. So you can use this for further development. So for the scenario generation, so one thing we noticed is that if you just train some machine learning model, like a statistical models, right? So then this model just fits on the data, then you sample from the machine learning model, most likely you will get some average data, right? So as many of you know, like the average scenario data don't have much training values. What we really need are the safety critical scenarios. But in practice, it's really hard to collect the safety critical scenarios in the real world. Then if you sample from the model, then you cannot get the safety critical scenario. So to improve that, we have another work that try to develop some safety critical scenario generation pipeline called closed loop adversarial training for safe driving. So what we are doing here is we can first load some real world scenario from the data set, right? So those scenarios are pretty standard scenarios, so nothing interesting happening there. Then we develop some algorithm that can help us do this safety critical resampling. Basically, is a motion prediction model modules. Then we will select the future trajectories that can lead to the high collision probabilities. Then we can generate these adversarial scenarios. Then we further use this generated adversarial scenarios for this policy optimization. Another very interesting design is that we want to close the loop. So after we feed this scenario back into the training, so we have an improved driving policy, then we go back to the beginning and regenerate those safety critical scenario. So it's a work sort of like a curricular learning, right? So after we have an agent keep improving, then we will generate a scenario that can match the capability of this current agent. So keep improving this agent. So after this kind of iterative trainings, then we can have a safe end-to-end driving policy that have more than 30% improvement in the safety scores on those holdouts test set. So we also released our codes through this link, so you can check it out. So here are some of the safety critical scenario we generated by our algorithm. So for this real world scenario, we load insights, then we can generate this accident, and then we can use this data as a training to improve the safety of the agent. So for those results, they are pretty good. The behavior are pretty realistic, but we still have the issues with visual appearance, right? So here are RGB frame from MetaDrive. It's still pretty like a simulated scenes. So we want to improve the visual appearance. So we have some recent work called the SenGen. So try to leverage some pre-trained models, like text-to-image model, to improve the visual appearance of the simulators. Basically, we take this hybrid approach because our simulator already can provide a lot of this spatial condition, right, in the RGB, in the depths, and this semantic mask, and also top-down view ground truth mask. Then we've tried to leverage the text-to-image model to generate re-render the scenes with different text prompts. So on the right, I showing you this under different prompts. If we can incorporate the text-to-image, then we can generate a lot of a diverse image. So one innovation for this SenGen is that we try to mix the data from both the simulators and the real-world YouTube videos. On one side, we have the simulator that can provide all those ground truths and realistic behavior data from the scenario we loaded in our simulators. On the other hand, on the YouTube website, we have a lot of videos uploaded by the users that can capture a lot of different visual appearance. But the issue is for this YouTube video, we don't have the ground truth, right? So the challenge is how can we mix those data from those two sources? So then we can further use the VOM to help us do this quality check and the auto labeling for our for this YouTube videos. Now we designed this SenGen. It's we call it the simulator condition driving scene generation. So compared to some prior work that fully use a data-driven approach to generate the videos, we follow this kind of modular design, like use the conditions provided by the simulators. Like we can encode the text and encode the condition from the simulator, then build some conditional generation that can turn those condition into real-world conditions. Then we further fine-tuning some pre-trained text-to-image modules. Then that can allow us to do this controllable image generation. Because these are image generation modules directly linked to our simulator condition, then we can have a full control on the generation process. So here I show you some of the results, like giving this rendered scenes from the simulator. Then we can use this model to re-render this image into different visual appearance based on this text prompt, like a desert, Barcelona, Miami, and here another scenes that generate a different visual appearance for the same traffic settings. Right. So another one on the different condition keywords and can generate a different visual appearance. We also do some evaluation, like compare with some prior method for this controllable driving scene generation. So compare with, by the way, the BVGen is also work, earlier work from our group. So that paper also get rejected multiple times, but it become one of the earliest work doing this BV to image straight generation work. And after that, there's some other work like BV control, like Magic Drive, driving diffusions. So then in image qualities, we can have a better performance. We further use the generated data for some data augmentation for this classification task, like map segmentation, object detection. So we show the synthetic data can help us improve the classifiers. So here I show you that we are building this open source infrastructure, right? So 3 years ago, we have the simulator. So we almost killed this project. We rejected so many times, but we have this resilience to adversity. Then now we have the meta drivers. with rich data and diverse visual appearance. Also, I got my first NSF grant last year to support this lab work to build this open source infrastructure. Then you may wonder what's next, right? What's after this meta drivers? I would say we want to move towards this future of mobility anywhere. You know, nowadays we have a lot of companies work on this mobility on the roads, like Zoox, Neuro, Waymo, building this vehicles on the roads. But the future will be like mobility anywhere. So here I show you a demo video. So this is actually real robots, mobile robots running on the sidewalk in West LA. So it's a vehicle, small size vehicle from Coco Robotics. It's a startup running this food delivery service. So this is small cars running on sidewalk. Then you can see the sidewalk environment is actually much more challenging, right? So there's a scooter parked there and also pedestrians, right? I also have this potted plants and this trees, right? So it's really hard to do this task. So right now they use this human teleoperation. So it's 100% fully teleoperation, which means there are some remote workers control this delivery bots. Then you can imagine if you can add some autonomy, some AI algorithm, like have shared controls, then we can address this, better address this food delivery things. So not only we will have this delivery bots on the sidewalk, we also have many other mobile machines, such as this electric wheelchairs for this disabled and older people, right? Use joystick to control these wheelchairs on the sidewalk. Also, in the future, we will have a lot of this lagged robots, right? This Boston Dynamics robot dog, and also we have a lot of crazy humanoid robots will emerge on the sidewalk. Right. So then how can we ensure and study the safety and the generalizability of these mobile machines is an unsolved issue. So in order to also provide simulated environments, along with my student and postdoc, so we are developing urban simulation environments called meta-urban that we try to simulate diverse urban environments for this embodied AI research. So this demo video showing you some of the synthetic environment generated by our inside the environment. So we have a lot of objects and also not on environment and also mobile robots. Because the sidewalk have a lot of the different function designs, so we follow some this urban planning design have different function regions. Then we also design some generation algorithm that can sample from the predefined configures and generate those different sidewalk structures. Then we can further put this 3D asset inside and also animate the mobile agent. Right. So here are the generated environment. Because after we have this layout, then we can replace those different 3D assets. Then we can have a different simulated urban environment. Not only we have the urban environment, we also want to populate this simulated environment with a lot of dynamic agents, right? So not only we have a lot of pedestrians, we also try to include this mobile agents such as the food delivery bots and the power wheelchairs, and we also have a team of people walking there. So this demo video showing you the parade of the mobile agent inside our environment. Right, so you can see by including those different mobile agents, so we can greatly enrich the diversity of the environment, and also it facilitates many interesting research problems, like how can we train those embodied agents to interact with human beings, right? So how can we do this social navigations? So this demo video showing you this, then we can further doing this reinforcement learning or some imitation learning to train this Coco robot like running on sidewalk to do this social navigation. So I'm very excited about this future direction, right? So mobility anywhere that can enrich this research on mobility in more different problems. This kind of sidewalk navigation also related to many other topics such as urban planning, right? How can we better optimize our sidewalk environment? Okay, so I would like to stop here. So we release all the data and the infrastructure through this MetaDrivers link. So I would like to thank my founding agency, NSF, also wonderful team members. Yeah, thank you. Yeah, any questions?
Yeah, maybe you can go to the microphone. Then also the Zoom speakers can hear you.
Yeah, hi, Professor Joe. Thank you for your very impressive presentation. I have a specific interest. Is it working? No. All right, thank you. So I have a specific interest in the traffic jam and the collision, the CAT work. I was wondering about the other scenarios generation. Do you use the real world, real world corner cases, or you just like resample until we find some interesting corner cases? I'm specifically interested in this part.
Yeah, so that's a very important question. So the scenario we based on will be from the real world. So it's more like after we load the Waymo scenarios, then we will randomly select some real world scenario. Then we will have some like motion prediction prior that allow us to generate multiple future trajectory for this traffic vehicles. Then we will select trajectory proposal with the highest like a collision probabilities. So in a case, we will have the real world data help us improve the realism of scenario. We also have the prior that can help us generate realistic trajectories.
I see. Yeah, I have a quick follow-up question about the pedestrians part. I was wondering, currently the pedestrian is like I will assume controlled by like some rule-based algorithms. Do you have a plan for data-driven method to just use neural networks to control the pedestrians and all the other like vulnerable users in your simulator?
Yeah, so right now it's a rule-based planning algorithm. So we also have some ongoing work that try to learn the human movement, pedestrian behavior from the YouTube videos. So we can use some 4D motion estimator to have a better estimation and generate and sample from that, generate more realistic behaviors.
Yeah, thank you.
Okay, quick question about the generation of the safety critical samples. You showed some picture where like there's a car accident and then the car kind of like flow away. Is the physics controllable in that case? Like, can you have control over like if a larger mass car hit another, then it will be displaced more, for example? Is that something doable in your like generation?
Yeah, I think because this is a generated scenario further imported in our simulators. In our simulator, you can have full access to any location and pose and the velocity of the vehicle. So you can do any post-processing you like.
Okay, and that's also detectable, like when an accident happened,
yes,
right?
Yes.
Okay, thank you very much.
Okay, thank you for all the question. And with this, let's give another round of applause for Leif.
Yeah, sure.
Kashyap, can you share your screen?
Sure. Do you see my screen now?
Yes. Still loading. Yeah, it's good. We can see everything and we can hear you here. Perfect. Okay. The microphone is on. Good. Yeah, so it's a great pleasure to introduce our next speaker, Kashyap Chitta, who joins us over Zoom today. Kashyap completed his PhD at the Autonomous Vision Group at the University of Tübingen in Germany, supervised by Professor Andreas Giger. Geiger. Kashyap was selected for the doctoral consortium at ICCV and as a 2023 RSS pioneer. And he also produced winning submissions to the 2022 Carla Challenge map track and the 2023 and Challenge. And yeah, it's a great pleasure to have you here or remotely. Yeah, you can go ahead with your talk.
Great. Yeah. Thanks for the kind introduction. And I'm going to be talking about some of our work on simulation, which is very much in line with what we just had from the first talk. So I had the great fortune of working with an amazing team on this project. It's a very large team. So this is everyone involved. And the problem that we tackled is just that benchmarking autonomous vehicles is really hard. There's been a lot of skepticism, at least like from people I've talked to, regarding whether we have actually made real progress in the last year or so, because there has been a lot of hype and interest in end-to-end autonomous driving systems. There have been a lot of new research papers in this area, but it's really hard to compare these different papers and see if the performance is actually improved. So I want to illustrate this with a very simple example, which is based on like how benchmarking is done currently in a majority of the recent literature. So in this situation, you're like slowing down, approaching a red light, and I've projected 3 different possible future trajectories in 3 colors onto the image. And I think that most people would agree that the green trajectory here looks the most sensible, but it turns out that if you measure average displacement errors, which are the primary component of most evaluations these days on end-to-end self-driving methods, the red trajectory, which is veering off and crashing into this van, gets a better score than the green trajectory. It has a lower displacement error. And this is because the human driver who recorded this scenario in the dataset actually slows down at a different frame compared to this model output, which is the green line. So if you take a different but correct approach to tackle a particular scenario, you can end up with a higher displacement error, even though this is like perfectly acceptable driving behavior. And this is not the only problem. There's like a great paper, which I believe is at CVPR, so definitely check it out in the paper sessions later, where this team discovered that the data set, which is most predominantly used in research on end-to-end driving, called WaveScenes, has a lot of data which can simply be summarized as driving straight at nearly a constant velocity. So there's this heat map, which shows the distribution of trajectories given the ego vehicle placed at the top here. And 75% of the data kind of just goes straight. This leads to weird things in the results people have observed on this benchmark, such as I've plotted here a subset of papers that have been released on end-to-end driving between the end of 2022 and right now, so like in the last 2 years. And you have this set of different colors and different shapes in this plot. And it's so confusing because here all the shapes refer to different evaluation methodologies. Different papers kind of change the way the ground truth is calculated, change the way averaging is done, change which frames are sampled in the evaluation, leading to like a lot of inconsistent protocols. And there's also just a lot of different methods that came out. And surprisingly, like based on this displacement error metric, where lower is better, a very naive type of model, which is called like a blind agent, which does no perception. So it just takes in the historical states and driver intention into a tiny MLP, can actually perform very competitively to most principled end-to-end driving methods that came out later on this particular benchmark. So it's not clear like how much progress was made with all of these newer methods, if they are like relying heavily on just this past trajectory input, or if they're actually doing something meaningful. So with all of this in mind, I want to quickly touch upon like simulation. So we had this like great talk just now about how you can benchmark in simulation. And it is true that simulation is more principled, but simulation does have its own issues as well. There are limited open source options, like Carla was mentioned as like the most popular and standardized one in the literature. But the problems that you get when working on Carla are that there's going to be a lot of domain gaps. The data is still not extremely realistic. The evaluation or running these simulations is actually very compute hungry, because you need to render sensor data, which typically needs a lot of GPUs, and you need to benchmark these driving agents by doing a lot of driving, so several hundreds or thousands of kilometers, which eats up a lot of compute. And another subtle problem is that you have really huge variance in results reported on simulation-based benchmarks. So in Carla, which our group works on a lot, on a scale of 1 to 100, where the metrics lie, if you simply retrain your model, sometimes your score changes by 20 or 30 points. And not all papers train 3 or 5 seeds of each model they have in their paper, because this just further balloons up the amount of compute you need to do to actually make meaningful research in the simulators. So we have the situation where there's no ideal path for quickly and correctly benchmarking end-to-end driving algorithms, but there's still a huge community that's very interested in it. And this is sort of the hole we wanted to fill with this project. So the key idea of this particular method, which I'm going to talk about today, is something we call non-reactive simulation. And to simplify this, this is essentially bypassing all the challenges of simulation and making a very minimalistic simulator that can lie as a sort of middle ground between the very unprincipled displacement error based evaluation that we have out there, which is convenient, but kind of gives no signal as to whether your models are actually improving, and the more principled but very compute hungry simulator-based evaluation on Carla or such. So this is going to be a middle ground of sorts between these two things. So what do I mean when I say we bypass the challenges of simulation? So if you think about it, there are two main challenges in simulation. The first one is that you need to simulate sensor data, because most of your driving algorithms need sensor data as their inputs. What we do here is actually a trick which is related to how the ego vehicle processes its input data and produces its output. So typically in a simulation, the ego vehicle is reactive and it gets a new state at every time step of the simulation. So I'm going to illustrate this here with this little graphic where in red we have the ego vehicle. The green line is the output of the ego vehicle. And as the simulation starts, you'll notice that the green line is always centered at the ego vehicle and changes every frame. So let's have a quick look. So you can see that the vehicle, let's say, is getting new inputs and producing new outputs at each frame. And this particular type of simulation, you require a new sensor input for your model at every frame if you want to use a sensor-based policy and evaluate it. But what we do, which is non-reactive ego simulation, is actually fairly simple. We restrict the input of the ego vehicle to the very first frame and hold its plan consistent for the entire output horizon. So what you'll see here is that the green trajectory, which is output by the model, it's actually the same at this very first frame as if you had a reactive simulation. But what we're going to do instead is simply hold this green trajectory constant without changing it at every frame, which means the model actually gets no new inputs. The model is just making a single prediction for a horizon of, let's say, 4 or certain number of seconds. And it will commit and run through this entire horizon without having the ability to replan. So this is how that looks. So you can see the green line doesn't always start at the center of the ego vehicle anymore, but it also doesn't shift around each frame. It's basically the same plan over the entire simulation horizon. And with this particular approach, you don't need to simulate new sensor data, because as long as you have the first sensor frame at the beginning of the sequence which you're simulating, you can run this entire simulation in a bird's eye view, just like we have visualized here, without actually inputting new sensor information into the policy. And this is a very strong assumption because it makes it so that your policy never observes states that are not in the training data or like in the original recorded data when it's being tested. So you'll always only see states that are, let's say, like in the center of the lane where a human driver would be. But in exchange for this, the policy has a more challenging task that it needs to anticipate things over a very long time horizon. It doesn't have the ability to replan if the expectation over like what is going to happen in 3 or 4 seconds of the policy is wrong. It's going to be penalized with an error for making a plan that was incorrect in the long term. So this is what we do to circumvent sensor simulation. And the second challenge of simulation is actually how to simulate the background traffic. So in a typical simulation, the background traffic, which are the blue cars in this particular graphic, need to react to what the ego vehicle does. So here we show a scene where in the original recording, the car didn't come to a stop on the highway like this. So the blue cars would have kept moving straight. But if the new policy now decides to suddenly stop, you would expect the background traffic to correspondingly stop behind you. But what a non-reactive simulation would look like is basically the background ignores the ego vehicle completely, and it's going to just drive as it did in the original driving recording you have in your data set. So you can see this weird behavior of the blue vehicle driving straight through the red vehicle. And again, this is another very strong assumption, which is more or less incorrect in most situations where your policy behaves differently from a human driver. But as we'll see, this basically bypasses one of the most challenging tasks within simulation, which is how the background traffic will move, and lets you have like a very lightweight behavior model of the other cars, which is just loading from their recording. So we've bypassed both sensor and traffic simulation, which are like the most challenging components of running a simulation. And once you do that, you can actually use simulation-based metrics, which are, unlike displacement errors, like principled in that they actually measure things that you care about when you're evaluating a driving model. So we use this like bird's eye view world to calculate different simulation-based metrics, which can be related to collisions, staying on the drivable area, maintaining a safe distance from other vehicles, having enough progress, and being comfortable. I'll go into a little bit of details on each one. So you want to measure collisions by bounding box intersections in this bird's eye view space. But if you recall that we have this non-reactive simulation there are going to be some collisions which are caused due to the background traffic not reacting to the ego vehicle. And unfortunately, since we bypassed having a proper behavior model, we need the metric to now not penalize such collisions. So we have a no collision metric, which only penalizes collisions where the ego vehicle is at fault, which is determined by the relative orientation and speeds of the two vehicles that are in the collision. So you wouldn't get a penalty if something drives into you from behind and drives through you. You have a drivable area compliance metric, which is more straightforward. If you have a HD map in your dataset, you can run your simulation and see whether you drive off-road. We penalize near collisions by having a penalty for being within 1 second of a collision given the current velocity. We encourage the model to make a decent amount of progress and not be overly conservative by using a privileged planner on the exact same scenario and measuring the progress relative to what you can achieve with a simple privileged planner. And we can inspect the acceleration and jerk and make sure that the driving behavior isn't too uncomfortable. So if we go back to the scenario I showed right at the beginning, this is what you get now. With these metrics, you can clearly distinguish like these multiple facets of driving, and you observe that this particular trajectory in red is going to collide and not maintain a safe distance. This trajectory in orange is not comfortable and going into this bike lane, so not complying with the driving area. Whereas the one in green, even though it has a higher displacement error, is actually safe as per all of these different subscores that we have. And we kind of combine these into a single metric with a notion of having some penalties and a weighted average. So you have these metrics that all of the metrics lie between 0 and 1, and these penalties basically are for behavior that's not permitted, such as collision, and the trade-offs are more for behavior that is favorable but could potentially be violated in case of a complex situation. Now, this particular metric and formulation is designed to be very extensible and adaptable. So we start off with these 5 metrics, but you can incorporate more. And putting this all together, we have this final metric, which we call the PDM score. We do like a small 4-second simulation, and it correctly attributes the green trajectory in this particular scene to be the best one of the 3. So just I want to mention that based on our assumptions, like one key problem with the PDM score is that it can't be used for arbitrarily long simulations beyond a certain number of seconds. Like the task, first of all, becomes too challenging for a planner to output trajectories for like, let's say, a minute. And it also becomes like infeasible for the background traffic and ego traffic for this assumption to hold at that point. So does it work? We did a bunch of tests on privileged planners. So planners that actually take bird's eye view HD maps and bounding boxes as inputs, and used a proper closed loop simulation. So we used something called the closed loop score, which was the primary metric of a driving challenge called the New Plan Challenge from last year. In this particular score, you simulate the planner's output with the proper reactive style simulation at 10 Hertz for 15 seconds. So it doesn't use any of these assumptions that we have of non-reactiveness of the ego vehicle. And what we plot here is a scatter plot of the closed loop score, which is our sort of target metric, the gold standard for a correct evaluation, and our PDM score metric, which is plotted in red points, versus something called the open loop score, which was also a metric used in the same challenge and is primarily based on displacement errors. So this is one of the more principled open loop metrics out there. so far in the literature. And we have like different shapes here for learned planners and rule-based planners. So we collected 150 different planners for this like little experiment. And what we see clearly is that the PDM score, which is the red points, kind of increases with the closed loop score. It does overestimate the closed loop score a bit, so it's not a perfect diagonal correlation, but it's much better correlated than the open loop score. And this kind of shows that despite these simplifying assumptions, we are going somewhere with this non-reactive simulation. So besides the metrics, I still think there are quite some entry bottlenecks to doing end-to-end driving research. And this is something we also tried to handle in this project. One is that the storage requirements of doing benchmarking at a sufficient scale is often like out of reach of smaller labs. So NuPlan, for example, downloading the sensor data is 20 terabytes of storage. And we released this subset of NuPlan, which is just subsampled. It's called OpenScene, where we essentially subsampled to 2 Hertz, which is the typical frequency used by today's state-of-the-art methods as inputs. And we also generated some standardized train and test splits, which I talk about in a second. We made a private fixed evaluation server, so different papers can't come up with their own metrics and their own definitions of the ground truth, and this gets standardized. And basically, like, we improved the distribution of the test set a lot to deal with the problem of straight driving. So here I show the performance as per 3 of our new metrics: no collisions, drivable area compliance, and the PDM score, which is our aggregated metric I showed with the combined set of 5, where if you go to our OpenScene dataset and look at the performance of a simple straight driving with constant velocity and heading, it actually gets a quite respectable 80 PDM score already, which means that unfiltered recordings are mostly static or straight driving scenes. You also see in this plot, like, this is on the log scale, the lateral endpoint of how much you turn, and it's nearly like 80% or more that is just going straight. So we use some simple heuristics to filter out some of this data based on this constant velocity and heading baseline, and significantly improve the distribution to generate more diverse and challenging scenes. So putting this all together, we provided this interface with like a standard sensor suite. It uses this OpenScene dataset, but it can be expanded to support more datasets with camera, LiDAR, and state inputs. It looks something like what we see on the right for a 1.5 second history. And we kind of re-implemented the state of the art, the best methods taken from the literature up until today on like end-to-end driving. So in the interest of time, I will not go into extremely deep details about these methods, but there are state-of-the-art approaches for new scenes, such as UniAD. This was the best paper at last year's CVPR, and ParaDrive. When evaluated on new scenes, these methods don't significantly outperform the Ego MLP, so it was not really clear whether they are making a significant improvement, given that they are very compute hungry. They use high resolution multi-view video inputs, and the training budget is extremely huge. It takes like 80 GPUs for multiple days, 5,000 GPU hours to train these models. So we re-implemented these on NavSim, and we are having these as our first baselines. We also took some baselines from Carla, and just as a representative, one of these methods is transfuser. These are much simpler in comparison with more lightweight 24 hours on 1 GPU style training with less output auxiliary tasks and less input resolution and sensor counts. So what does the new benchmark show us? So the first sort of good thing to know is that the UniAD and paradrive methods, which are the current state of the art on new scenes, are clearly better than a blind ego MLP as per now the more principal metrics we have. So that's good. There's like quite a significant gap, and it's around almost all of the metrics, like keeping safety distances, drivable area compliance, making progress. Comfort is the one metric where all the methods kind of cap out because it's like very easy from imitation learning to learn to not have huge acceleration and jerk. Surprisingly, the transfuser method, which was more or less developed completely in Carla and simulation and has a much smaller training budget, actually gets a performance on par with these more complex UniAD and paradrive methods on this benchmark. So that's something interesting to explore as to whether like we can have much more efficient models and get good scores. And human trajectories. So if you evaluate the ground truth in the data set, this is 11% better than all sensor agents. So there's still quite some headroom to make progress in this benchmark. And the benchmark can always be made harder by extending the output horizon from 4 to 8 seconds or improving the metric definitions or adding more submetrics. So we also held a little challenge. I'm not going to go into depth on this, but we had a lot of participation, some interesting entries, and we had a lot of diverse entries. A lot of teams used foundation models, which was hinted at the introduction to this workshop. Seems that they are a thing. And we saw like a lot of variety, which was like quite exciting for us. So people didn't simply use the existing methods from new scenes in Carla. There was a lot of diversity in the solutions to this leaderboard, and many of them perform quite competitively. I want to sort of come close to the end by giving this caveat that we do have this new benchmark and it is solving a lot of issues with previous benchmarking out there, but we still recommend complementing an evaluation on NavSim with a proper closed loop simulator like Kagla or MetaDrive, which was just mentioned in the previous talk. This is because like the NavSim approach cannot do long evaluations, which are actually we have found important in our research in Kagla. So we can just do like 4 or 8 second simulations, whereas these simulators can do several minutes. And we currently can't consider some infractions, like because of our definition of this non-reactive simulation, we can't penalize rear end collisions, for example. We also don't have a metric for running red lights yet. And while these things could be improved, it is going to be complementary to have evaluations on a simulator along with this benchmark in your papers or while developing your models. It is good that our particular simulation approach is much, much less compute intensive than using a simulator though. So maybe a good first step before going towards a simulator is trying out our benchmark. So yeah, that's my last slide now. The dev kit is available. You can scan this QR code or go to the link to get access to everything. Basically, we have like baselines, all the simulation implemented. It's super fast and efficient. All the data set and downloads for our like standardized splits have been simplified and made as convenient as possible to get started. And we are actively developing this framework to make it more useful in the coming months and years. So there's going to be better metrics. There's going to be more metrics. We will hopefully add support for more data sets and have more challenges in the future where we may eventually be able to resolve a lot of the issues with the non-reactive aspect of the simulation and make like faster progress by leveraging sort of the whole community. So yeah, with that, I'd like to end my talk and I'm happy to take questions. Thanks.
Yeah, otherwise, yeah, otherwise, kind of since we are already kind of a bit behind schedule, and the coffee break starts basically now, and I think everyone needs their coffee to wake up, especially the people with jet lag. I think yeah, thanks a lot, Kasia, for your talk. It was very interesting and definitely learned some stuff on how to test our models more efficiently. Yeah, thanks a lot, and maybe another round of applause for our speaker.
Okay, thank you.
For the program, we have a break for half an hour. And next will be Sanja Fiedler from NVIDIA, so definitely come back. It will be interesting.
I can only test these. Yeah. Again.
Yes, 1, 2, 3.
Yeah.
Okay.
That's right.
Can we?
I'll check my audio devices. But yeah, okay. Maybe, yeah, now it works. Okay, good.
Gosh, what if he doesn't show up? Do you mind sharing your slides? I guess it's a PowerPoint.
Here, yeah.
window. Yeah.
You said the audio correctly.
Yeah, I believe so.
And there's sound and
Exactly. So we can test this right now. So we can do now is
double check the last slides. Okay, sounds good.
can you speak into the microphone for a second and let's see it's
Hello, hello.
yeah, you're on.
It's all good.
Okay.
Should I do a full screen now or?
Full screen together, yeah.
And they're seeing just this, right?
No, actually, so no, we are screen mirroring, so they see exactly what you see.
Okay, so what do I do?
Do you need the
Slideshow?
speaker view?
No, I don't need it.
You don't need. Okay, in that
No,
case,
but at the moment, they see the correct thing.
wait,
They
no, I
won't.
see maybe this is lagging right now. No, but yeah, they see the speaker view, so that's so in that case, you just go full screen without a speaker view.
Like you need to.
Oh.
Yeah. Ah, wait. How can we?
PowerPoint, this doesn't work. You need to. I mean,
What happens when?
Okay.
yeah. Now the people in the room see this
Ah.
slide. I think what you would need to do is the easiest thing is to just change the settings that you don't mirror. You just mirror the screens.
Wait, let's try
Never
again.
mirroring, it's just the fact that we
No,
don't want the presenter view.
No, but the easiest
What
is
if
if you
we do
just
this?
do mirroring,
Yeah.
then
Oh,
you don't
shit.
have the issue.
Yeah, you're right. You're right. Okay,
I
so
think-
in that case, we're gonna.
Yeah, by far the easiest thing is we go for
Okay. Oh yeah. Place settings. So it's different.
no, but it looks so correct. It says mirror.
You don't want mirror.
We want mirror. She doesn't want presenter views.
Okay. So if we go full screen now.
Share. We can stop share. Then we can share, and we can do. Where is the switch thing? Because now,
Oh, because the PowerPoint does that.
yeah,
I think you can do slideshow and then. Oh, let's see. Damn it. Do this. Oh no, she got it anyway.
now, what do you see on the Zoom?
What's going on here?
Okay. By,
Are we good
by
now?
magic, we now see it correctly.
And she's not on mute and audio.
So I see it like this.
Right. Test.
All right.
And audio is also gonna stream.
Yeah, that's where we just tested it. You can hear it on the Zoom. Give a quick introduction. Can make it very quick or
Yeah.
quick or
You know what Jeff always tells me?
what.
This is Jeff, who needs no introductions. So.
But then I also heard that you should never say the person needs no introduction.
No, don't do that. I still need a bit of introduction, but don't make it like 5 minutes.
No, I even when we prepared, we did. When we prepared, it was also like I want short introduction because it's also annoying to talk like for 5 minutes.
Yeah, then you cut out. So I think I'm gonna be maybe like 30 minutes and then just switch to next thing and people can ask me questions.
Okay, yeah. Okay. Welcome everyone. Welcome back from the coffee break. I hope you're now all a bit more awake. And with this, it's actually a great pleasure to introduce our next speaker, Sanja Fiedler. She's an associate professor at the University of Toronto and a vice president of AI at NVIDIA. She's also the co-founder of the Vector Institute and the Canada Seafair AI Chair. Sania's work is in the area of computer vision, machine learning, specifically the intersection of computer vision, graphics, 3D vision, 3D reconstruction, and synthesis. Please join me for Sania's talk. It's a pleasure to have you here.
Yeah. Thank you for inviting me. Can you all hear me? Yes, even in the back? All right, sounds great. Oops. Guys, we're too smart. All right, so today I'm here to represent NVIDIA, to tell you a little bit about the AV program at NVIDIA, and specifically what we're thinking around next gen, so what's coming next. So AV at NVIDIA is really full stack, right? So we produce hardware, meaning in-car chips that are accelerating the software. Infrastructure, right? With AV, you know, we need massive data, massive training, simulation runs, right, to test the software. So you need the appropriate infrastructure amount of GPUs that scales. Simulation. We don't depend on any external software. It's all in-house, meaning that, you know, it's all repeatable, state-of-the-art graphics, fully controllable by us. Drive, so NVIDIA Drive is a product. It's going to launch, I think, next year with L2++, meaning it's going to run autonomy, city, and highway, but human in the loop still, so L2++. And then, of course, there's also research. So research is an important part of NVIDIA, many different topics from generative AI, robotics, graphics, and also AV. And for our next gen, actually, we're all kind of combining forces, which is quite exciting. So hopefully I'll tell you a little bit about that. So if we look at the AV stack evolution through the years or even decades, right? It started with rule-based, more algorithm-focused. Then AI was basically inserted in all the modules, right? From perception to planning. And this is actually what is mostly deployed these days in OEMs in the cars, right? And the future needs to go beyond this, right? It needs to extend the generalization capabilities, meaning foundation models and stacks with as little human engineering as possible. Right, so the AI-enhanced stack is basically what NVIDIA currently has is standing up in product. Issues, of course, right? So you have heavy dependency on label data that doesn't really scale. You have limited understanding of complex scenes. Everything, you know, rare cases you almost never collect, right? So it's hard to deal with them. Very short-term system memory, right? Typically have like a window of maybe 1-2 seconds. Meaning, you know, like worst case, if I change lane 5 seconds ago, I don't have a memory of that anymore, which is not great, obviously. And there's a lengthy development because there's human engineering heuristics between every pair of modules, meaning that you have this very slow iteration cycle. So we want to kind of in the next gen, which is mainly what I'm going to talk about today, kind of fix all of this stuff, going towards more scalable and generalizable system. So one thing is just more end-to-end training stacks. I think the community is building or gearing towards that. And foundation models that basically train general knowledge and then fine-tune in domain, basically everywhere in the AV, right? From the stack to simulation, data, maybe even some part of metrics, and of course, any kind of in-cabin assistance. NVIDIA has strong foothold in generative AI. I think just last week we launched the LLM, maybe the biggest, 340 billion with a permissive license, beats a lot of the LLMs out there. Picasso, text-to-image, text-to-3D, and more. It's basically diffusion-based architecture for generating images or 3D. You can go to Getty and Shutterstock. It's already in action. So those features are supported by this architecture. DLSS 3, who plays games, RTX on, right? 7 out of 8 pixels are invented by AI. Villa is a captioning, or let's call it a visual language understanding model, released maybe 2 weeks ago. Got 1 million downloads in basically a week or two. Best open source model for visual language understanding. So in recognition of that, of course, NVIDIA also building a next-gen hardware on top of the Blackwell GPUs with particular performance improvements for transformers and generative AI, right? So you got like 10x or almost 10x speed up for something like Llama 7B, and even CPU is much faster. So it's really gearing towards you guys deploying foundation models in the car, okay? So today's talk, we're gonna talk about 3 different areas, how we're kind of thinking about the role of foundation models in data tooling, really speeding up, how we interact with data, how we're introducing foundation models in the AV stack, and then simulation. That's dear to my heart. So we're gonna talk about how AI is kind of transforming simulation and making it more scalable. All right, so foundation models and data tools, right? So you're collecting a ton of data, like massive data, especially once the product is deployed on consumer cars, right? And there's already standard tools that process that data, but now we can go to really the next level, right? We can introduce VLMs, so you can have auto labeling, but open vocabulary, captioning, descriptions of what's going on. We can use that for scenario search, video search. And semantic clustering, you're going to see some cool examples of that as well. Then, of course, we need to build data tools and incorporate technology, so you can do really powerful image retrieval, video retrieval, more semantic scenario retrieval, and even like 3D open vocabulary labeling. And of course, there's a loop, right? So all these tools are being used by developers to do model training, creating evaluation data sets, as well as for simulation, like replay, or even what we're going to talk about today, going from data to simulation. So we have a pretty powerful visual retrieval, both image and video model deployed. It's currently indexing around almost 40 million video clips, and is basically indexing all ingested data or most of the ingested data per day. Text search, you can also do image video search, and it kind of learns from on-the-fly human feedback as well. So we're estimating that with these kind of features, the developers can just go open vocabulary, a dog walk in the street or something like that, can give you around 30 to 60 speed increase in data sourcing, right? Which was previously mostly, I wouldn't say manual, but definitely very slow. Captioning. We've noticed we're training these big video models as well, maybe not exactly for AV yet. Longer captions are super good for training these performance models. And for AV, this is particularly important. You really want to describe everything that's going on that's relevant to driving. So we're working on video captioning methods. And then using those descriptions to do semantic scenario clustering and retrieval. So here is one example. This is a little bit different than video retrieval. Video would be, a dog is walking the street. Here, you really want to have a scenario, a cut-in. For example, agents from adjacent lanes entering ego lane. So let's look at a couple of examples. You can see the agents actually going into the lane. Another one, this is a slowdown because the vehicle in front has a braking light on. Super useful for testing, right? Because you really want to check that you're handling this kind of hard scenarios. And some kind of earlier research work that allows you to just do, a description of an item you want and then label everything in 3D or find relevant queries. All right, so that was about data. Let's talk a little bit about the stack. I would say that we are still early on, but I'm going to tell you a little bit about what we're thinking and where we are. So we're going with the tokens and transformers architecture. So all the sensors, plus maybe optional context such as text or even ego action are tokenized. And then we build basically a large transformer models that encodes that. And this transformer is trained to predict with the generative objectives, so predict the next frames. And we're pre-training on generic images, whatever you can get your hands on, images, videos, and text in terms of modalities, and then fine-tuning on AV data, which means that now you have multi-camera rigs, maybe even other sensors. So there needs to be some adaptation for in-domain processing. Of course, you need to put a driving stack on top, right? So we're decoding parallel heads. So there is no connections between heads, at least that's the current thinking of basically standard models. They're just not interconnected. And one thing that actually I'm going to show a little bit later, what we're doing for trajectory prediction, we're going to do human driving, right? Which a lot of other people are also working on. Because you got like really nice human-like driving, but we're also trying to supervise from simulation. So you want to have rollouts, and you want to kind of teach the model to not break rules and to be safe and comfortable. And of course, there needs to be safety monitors and guardrails that make sure that we are actually deploying a safe system. All right, so we're kind of drawing the inspiration for this stack from various research results that are going to be presented here at CVPR. We had access to them many months before. So ParaDrive by Marco Pavone's team is essentially doing a search over all possible connections between these modules. And they found that if you just do parallel decoding, you're getting like a much lower collision rate. So you get a safer system as well as much faster system. Super awesome work. Jose, where are you, Jose? Invented this Hydra MDP that basically says that if we use this rollouts in simulation as a teacher for these other losses, safety-informed losses, well, you can win a benchmark on it, apart from other innovations in the architecture. So there's this end-to-end challenge leaderboard, and Hydra MDP by Jose and team actually won by 5%, which is significantly. So we're celebrating that today. We also had this work that was focused on behavior modeling, but we're going to go with this kind of approach. It basically represents output trajectories as discrete tokens, and then again, transformer is autoregressively decoding them. And this has been shown, at least for the behavior modeling, to surpass state of the art, at least at the time when we released it. And we checked a couple of days ago, and not all top performers actually follow this paradigm. Super powerful architecture. The really key is going to be how to make this real time to run in the car. And we have quite some good results on that already. The backbone is currently where we're putting the most attention, right? I talked about video generation as a pre-training task, so you can actually consume all this massive data, both on the internet and internal data. And we built quite a muscle on this already, right? So we had one of the first world models that was in 2020. And then 2023, which is basically a year ago, was the first latent diffusion model. We introduced Sora, and stable video model is basically based on top of this kind of architecture, obviously more advanced with transformers instead of UNet. At the time, so this was already a year ago, we were kind of looking at this model, and then we found some really nice emergent properties. One is compositionality, right? Because we're kind of interested in AV. So we were testing just by training on internet, how much compositionality can we get actually relevant for driving? Can we put an elephant or a dog with like VR goggles on the street? And the answer is actually yes. There's quite a bit of camera and motion control you get like as an emergent properties of this model, but just a little bit of fine tuning. So you can see that little frog is being rotated if we just keep the right prompt and controlled by just motion and no camera. So all this kind of gave us the belief that there's so much knowledge, there's compositional knowledge, and there's 3D understanding in these models that we should be able to exploit. So we've been kind of working on that for as a backbone now for AV. So one of the first things was just maybe improving the architecture and then fine-tuning the pre-trained, like world pre-trained model on internal data. And the results were quite surprising because first of all, it's very stable temporally. It can handle some really nice effects such as rain, snow. None of this was actually part of the data that we fine-tuned the model on. We fine-tuned it on about 2,000 hours of data. We didn't have those examples. And it even creates an accident on top right. We had no single example of an accident in our training data, meaning that the model is really kind of learning the sensors, the intrinsics of the internal sensors, but bringing all that knowledge from the internet here. And this is exactly what we want. I don't necessarily care about pretty pixels. We care about understanding the capabilities of these models, okay? Pretty pixel is an afterthought, maybe for simulation. The next was extending it, right? The rig actually has more cameras. So now we can do 3 cameras. That's the next attempt. Just kind of look at the consistency between the camera. That's what you should be noticing. There's a snowman in the query, both in front and the top right camera. It looks consistent. This car, as it drove here, it kind of casts a shadow into this camera. It looks pretty nice and consistent. Here's one more example. Even the sun is kind of consistent across the different cameras. And just now, I would say this is earlier results, 6 cameras, which is the rig we're going to be going with. This started to present more challenges because now you can't really fit this anymore into a GPU. So there's some compromises we're making here. So maybe the quality is not quite yet there. But definitely we're seeing a lot of consistency across the 6 camera generation. And of course, for deploying this in the car, you need that. Some funny challenges here that we still need to, basically means more scaling. Right now, we really haven't scaled this model yet. We're still in development. Just kind of look at this green box over here. There's going to be some inconsistency, some cyclist or motorcycle appearing and then disappearing. He just hasn't seen enough, motorcycles, doesn't really understand yet how they behave. So some physics is still not there. But we think this can be solved by scaling or at least addressed. One thing for those that you're developing these models, video tokenization, how you actually tokenize the frames or the video of the video clips, is pretty much the most important thing when you're developing these models. Right, because the transformer is basically sitting on top of these tokens. If the pillar is not good, then nothing on the top can compensate for it. So fewer tokens means that you would be faster in the car, right? But at the same time, fewer tokens also means lower reconstruction. So if you look at the left, the text is gone, it's kind of all muffled up, right? If you start introducing discriminative losses in the token reconstructions, not just reconstruction, but discriminative losses, which typically what people do, the pixels start looking better, but the model starts hallucinating, okay, which is actually not what we want for driving. Maybe for generation, that's good, but for driving, we cannot basically, look at this example, right? The input was a green light, and the model turned into a red light. So you really need to be careful how you train these tokenizers. One of the most important things when you're training these models. All right, so now basically, we have a pretty powerful foundation. The backbone, we're still obviously improving it. But we kind of already want to put like a policy head on top, trajectory, and just seeing whether you can drive on it. If not for anything else, just to see as a metric of how good these video models actually already are and where the gaps are, how we need to scale them further. So here on the left is just a short snippet, and the last frame is basically where we're going to be predicting a trajectory, and the video is encoded with basically this video model. This is run true. This is where the car actually drove, and this is what the model is predicting. So it's kind of interesting, for example, here, because we're not conditioning on the goal yet. It's kind of seeing that it could go straight, but also turn right. And here it's predicting correctly there's a turn. And so the color here, the more yellow means higher up, so higher elevation. It's actually predicting that we are moving upwards, which is pretty awesome. All right, so this is open loop, all right? But obviously for testing, even for development, we wanna have a simulation in the loop. We wanna be developing this model in simulation. Especially as we're going more towards end-to-end models, right, where we cannot break it up into components as easily, we really need to think about powerful simulation tools. So at NVIDIA, we have 2 different approaches plus a hybrid. One is, let's call it more traditional graphics based. So full real-time physics, ray tracing and physics simulation. Perfect for hardware in the loop, so integration testing. There's also scalable environments, but still the content is relatively limited, I would say. And then because we want to have this fast iteration cycle, so as soon as you find an issue on the road, ideally you would quickly check whether you have actually corrected it. So we need something that kind of closes the domain gap, right? If you went directly into the graphics engine, you're never quite going to be matching what you recorded. So we're also looking into reconstruction methods, and this is already a simulator in production. And of course, the hybrid model, the hybrid simulators that exploits both traditional graphics and neural graphics. All right, so let me show you a little bit about the simulation capabilities. Specifically, I want to focus here on this hybrid simulator. So the environment is reconstructed, neural techniques, NERF, and all the objects here are going to be inserted full physics, and that's exploiting the Omniverse features. You can see kind of, I don't know whether you see, but the cars are kind of bumping on the road. We reconstruct traffic lights, inserts in synthetic traffic lights, so we have perfect control of the traffic, can test different scenarios. With Omniverse, we inherit great physics. We can put the fire on the truck, you know, collisions, damage, and smoke. Can also deal with dynamic reconstruction, obviously, scenes or scenarios or the real world is dynamic. So this is basically showing that the scene is not playback, is actually reconstructed. Or here is a constructed. In some of the scenarios, you're gonna see a little bit of bumpiness, which is gonna reveal that it's still not as perfect. But this is already in production now. We're running tests against the simulator. And you can use this also to do scenario editing. So just four versions of the same scenarios. It's kind of notice there's kind of variation. We can swap and replace the cars into this different rollouts. All right, so that was kind of the simulation. We talked about the AV stack. Now let's put them together just so that you guys see some, you know, first rollouts of these models in this neural simulator. So in the top, let's look at that first. So is this, you know, generative pre-trained video backbone with a trajectory on top, currently only driving this car. So it kind of correctly slow down and turn right. Here it's gonna handle a pretty complex intersection, which is quite exciting. Here we're doing multiple rollouts. We're just going to be sampling from the model, just seeing how the, you know, what are plausible futures. It's going to be a pedestrian that pops up here. So the car is going to correctly actually change lane. And in different rollouts, it's going to change the different lanes, which is pretty awesome to see. One more example. One decided to park and one decided to drive. Okay, last one. Slowing down. Here, one rollout decided to go straight where the original capture was done. One decided to go right, and then we're kind of running out of the world. So you see like bad reconstruction here. So here is where generative AI perhaps is gonna help in the future. I showed object insertion because really kind of, yes, you reconstruct the world. Yes, you want to have exactly the same scenario, maybe interactive, but you also want to put a whole bunch of distractors and actually check that the car is doing what you want it to do. So object insertion and the quality of that is super important. I already showed that in the beginning, but we're really working towards improving those, you know, the quality. So top was kind of the most basic result, and the bottom is kind of our current result, which is much more realistic. Here is just like one example. You can handle night and different lighting condition. Looks very realistic. All the assets are synthetic here. secondary effects. We can now do ray tracing with these neural representations. Again, super important so that there's as little gap with reality as possible to really test these vehicles. And the other one is just scale, right? So in autonomous driving, especially if you're in a highway, 20 seconds, 30 second scenarios can quickly be kilometers. And if you check any of these neural approaches, they typically kind of like run out of capacity 100 to 100 meters, right? So you need to make sure that you're able to reconstruct much, much larger environments in a consistent manner. Okay, some 3D generation. Like I said before, we kind of run out of the world. So we need to equip ourselves with some generative capabilities. And AV, especially simulation, is about large worlds. Our world is really large, right? So when you're driving, even that, you probably want to see 200 meters ahead. So typically people put a lot of heuristics of where they're going to put their capacity. I'm quite excited. So we're going to release this machine learning framework that handles really large scale spatial intelligence at SIGGRAPH. And it's really leveraging the power of graphics. It's using this data structure called VDB and putting all the machine learning operations on top of that. And we can do quite amazing things with it. So that's going to be all open sourced.
Algorithms like city scale neural radiance fields, and algorithms like mesh reconstruction from a billion LiDAR scans. The main level application of the algorithm is deep learning. You need infrastructure that can handle large spatial scales to capture the size of the world. You need infrastructure that can handle high resolution to simulate the fine details. And we need infrastructure that can be distributed on multiple GPUs to leverage computation at scale. To address these infrastructure needs, we've developed FDE, a deep learning framework for Spark, large-scale, and high-performance system intelligence. FDE enables many useful applications, such as reconstructing a triangle map from a building input point, building and rendering neural radiance fields at the scale of cities, building generative models for large spatial scale data, and enabling high-resolution simulation with systems.
Yeah, so that's hopefully going to enable all of you guys to have much, much more fine-grained and large-scale perception, simulation, whatever you're building. VDB is this data structure that's actually the inventor of VDB has been working on this. That's Ken Musset. He just got an Oscar for that. Pretty cool. All right, so summary, kind of I said NVIDIA's full stack, we're building hardware, we're moving toward generative AI, and it's really research and product working together, super exciting. In this kind of phase development, agenda. Advanced simulation tool, and I didn't talk more about safety today, but there's a lot of effort going into online monitoring, guardrails, and of course large-scale testing. Yeah, and I think I'm very excited about this because it's really multiple research teams stepping together and working with product, and this is really the culture of NVIDIA. We win by being one team. So thank you very much.
Yeah, thanks a lot, Tanya, for this amazing talk. I think in the time, we will skip questions. If you have any, you can
find me later. Sorry,
Yes,
I took more
exactly.
time than.
Able to unmute, test. Okay.
And I'll share. Yeah, looking good there, looking good there.
Test. Do you want to confirm that Zoom is hearing? Okay.
Yeah.
Test 1, 2, 3. Test. Okay.
Okay. So, yeah, as I said, we now have our first challenge competition here. The first one is by Argoverse. They will actually have, they will talk for about 4 different challenges. And yeah, we are really looking forward to what the community was able to do with the Argoverse dataset.
Okay. Hey, everybody. I'm James. I'm a faculty member at Georgia Tech. I was also at Argo AI. Well, anyway, I'll have a word about that in a second. I'm going to be presenting this. I'm just going to give a brief intro before Kyle and then Nihar and then Tarasha present over the next hour or so. And first, let me thank the organizers. This is an awesome workshop. This is our 5th time presenting these competitions at this workshop, and there's been an astounding amount of progress made on these benchmarks, on everybody else's. So thank you, except that you made us speak right after Sonia, and that's rough. Anyway, so I'm just going to talk for a few minutes about an overview of Argoverse and then hand it over to Kyle to talk about that scene flow, and then we'll go through the rest of the competitions. So Argoverse 2 is really 4 different data sets, each with a collection of different scenarios that all have some common traits. For example, they all have HD maps. That means lane level geometry, things like lane markings, crosswalks down to the centimeter level. And they were all gathered by autonomous vehicles that Argo operated in 6 US cities, pretty diverse places with different weather, different architecture, different pedestrian behavior, things like that. The first data set, which was the basis of some of the competition, so Nihar will talk more about this, was the sensor data set. And I think this is what you traditionally think of when you think of an autonomous vehicle data set, and that it's, it's the LiDAR data, the stereo data, the camera data with 3D annotations of where things are in the world. Argoverse 2 is a little different from other really influential data sets like the Waymo data set and WaveScenes in that it tends to have more annotations at range, all the way out to 200 meters, basically the LiDAR range. And it has a more fine-grained taxonomy than those data sets. But otherwise, it's broadly similar to those types of data sets in scale and the types of tasks it supports. And again, every scenario has an HD map underneath it as well. The LiDAR data set is not as widely used, which is why I'm happy to promote it here, is that it's 20 times as many scenarios, and each scenario is twice as long. So it's a tremendous amount of LiDAR data collected in the real world. There's not 3D object annotations. In fact, there's not even imagery in this data set. It's already terabytes with just the LiDAR returns. But if you want to do self-supervised learning with LiDAR, this is a great data set to try it with. It does, again, have HD map annotations with every scenario. Moving on, the motion forecasting data set has been probably our most widely used set of data sets in these challenges and otherwise, and we will, again, present some competitions that use these data sets. These are non-perceptual data sets, so what you're seeing there are tracked objects from the real world. The tracking is imperfect, so the object position and velocity might be imperfect as well. But we track 10 different object classes, and the task is to predict the future, basically, to say, well, this object that we're interested in moved this way over the past 5 seconds. What does it do in the next 6 seconds? And Nihar will go into more details about this. And then another data set, the final data set, which is not widely used, but again, if you want to set state of the art on something, this is probably a good one to try it on, is the map change data set. And I think it's again, fairly unique. So the task here is to be able to say that my AV with HD maps has come upon a real world scenario where the sensors are showing things that don't match with my maps. And this will happen in the real world, right? Robotaxis tend to use HD maps, but the real world changes. And so this data set contains actual scenarios where the Argo fleet encountered this. So what you're seeing on the left there are visualizations of recently repaved roads. The city added a bicycle lane or moved the lanes. And so at some point, the AV has to, for the first time, encounter these and realize that hey, my map is stale, fall back to some limp mode, start real-time mapping or whatever. Or I guess other people would argue, well, you shouldn't be using HD maps at all. I'm not convinced by that yet. But anyway, yeah, these are real scenarios like that. If you do want to get started with Argoverse, we have a user guide to help you. Just Google Argoverse user guide, you can find it. And yeah, the Argoverse team is pretty big now. Again, Argo doesn't exist anymore. It's been shut down for about 2 years. So most people here were affiliated with Argo in some capacity. But now this is the community's data set, you know, it belongs to us. They gave us the keys to the kingdom, which was super nice to us. So there's no more corporate oversight of this data set. It's just us, the people in this room. So if you have something that you want to do with a data set, you're like, oh, I think these data sets are using the wrong metrics, so they're not benchmarking a task that I care about, then come talk to us, because, you know, we can stand it up and you know, maybe that'll be the next challenge for next year, something like that. So I have 4 goals for this set of presentations before I hand it over. 1, you know, we should learn about what's new, the state of the art for all of these competitions that we ran. 2, we should celebrate the teams that made really cool contributions and you know, give them the credit for what they've done. 3, again, I'd like you to be interested in Argoverse and go try it out. And 4, if you do try it out, I'd like you to go further and actually contribute, you know, have your photo up here next year because you are running a challenge that we thought was interesting. Okay, with that, I'm going to hand it over to Kyle, and he's going to talk about the unsupervised scene flow competition.
Thank you. Yeah, so on the list of new challenges, this one's pretty new. We did it for the first time last year, and we changed the metric for this year. So we'll talk about that as we get into it. So first, why do we care about cars but not trees? Cars move, right? When you're driving in the real world, you typically care a lot about the movers because they aren't just static obstacles that you need to avoid. So what is scene flow? It's the task of predicting between 2 point clouds motion vectors on a per point basis. So you can see here a car, right? The original point cloud was the dark green one. The orange one is the T+1 time step. And the red vectors are the flow vectors that you're basically trying to predict on a per point basis between them. So the way we get labels is we have amodal bounding boxes describing the full volume of the points over time. And the motion of these boxes, right? Motion from T to T+1 describes a rigid transform, and we can use that to get per point motion vectors. So, you know, there's an open question, which is how should we go about evaluating these systems, right? I have a scene flow method. I claim it's good. What does good look like, right? Naively, you can say, okay, we'll just say on a per point basis, we'll compute endpoint error between the ground truth flow vector and what your method spat out. The problem is that's going to get dominated by describing the background well, right? 85% of the points are from the background in these real scenes. So last year when we ran this competition, Nate cooked up it's called 3-way EP, and you split the world into 3 distinct sets, right? Background, foreground static, foreground dynamic. And the idea here is that you have these very different sized buckets, but in principle, you now have some measure of, you know, the movers that we care about. The problem that we ended up discovering is that this is still dominated by large objects. So we're talking about cars, trucks, that sort of thing, because there's a lot of cars and a lot of trucks in AV, and also there's many points per object. And so you find that there's more than 10 times fewer points on things like pedestrians, bicyclists, VRU is a vulnerable road user. And these are actually objects that are very important and we care about. And we want to be measuring them appropriately. Now, importantly, this isn't just an academic concern. So I'm the author of the Zero Flow method. I evaluated my thing on 3-way EPE. We got state of the art. The numbers are really low. I'm like, oh, cool. Is scene flow solved? I went to go make teaser figures for the paper. And I was like, is my method broken? Because it just simply did not know what pedestrians were. And I thought, okay, well, maybe the other methods work and mine is just uniquely bad. No, none of them do. So you can see on here, this is a pedestrian. This is an unusual scenario in that they're particularly close to the AV. So you have many, many points. Despite this, none of the state-of-the-art methods at the time were able to pick out any sort of motion. And so both methods needed to get better and our metrics needed to reveal that this was actually a problem. So motivated by this, we came up with a new evaluation protocol called bucket normalized EPE. So broad strokes, you know, you probably recognize the class-based breakdown that you see from like MAP evaluations and that sort of thing. But one of the key things that we do is we also segment speeds in this like 2-dimensional matrix, right? So you can see speed columns here, and you essentially evaluate EPE for each one of these buckets, and we normalize the bucket by the speed, right? So if you have a car moving at 30 meters per second, and you have 0.7 meters per second of EPE, that is a smaller percentage of missed description than a pedestrian walking 0.5 meters per second with 0.5 meters per second of error, i.e. you didn't describe its motion at all. So this normalization is very important to getting good descriptions of motion, right? You want to know what percentage of the motion was described well, and you're willing to be more forgiving as a percentage of total motion on objects that are moving fast. So we're able to put together essentially a dynamic normalized EPE score that's, hopefully 0 to 1. If you have more than 1, your error is like really bad. And then we have static EPE, which is just like, how do you perform in the background? If you average over all of these classes, you're able to get a mean static and a mean dynamic error. And so for the purpose of our challenge, we rank every method by mean dynamic score. And so that's what we're really looking for this challenge is, can you actually move the needle on this number, which in aggregate is some statement about like what percentage of motion do you care about over the classes that we are using to break down the taxonomy. With this new evaluation, we also propose a dead simple baseline track flow. But what we do is we take an off-the-shelf detector, right? The detection people have known for a long time that class imbalances are real and matter, and they do a lot of copy, paste, augmentation, that sort of thing. So we just run a detector on each frame individually, and then we run a Kalman filter. Dead simple, the dumbest thing you can think of to knit these things together. And this, we found, was like a new state-of-the-art baseline, actually both on three-way EPE and on our metric, where it was significantly better. And so that was the baseline that we put up for the challenge, basically as a point of reference, and asked people, all right, what can we do to beat this? So we ran 2 tracks. We ran a supervised and an unsupervised track, right? One of the things that James mentioned is this is a very heavily annotated data set. The public number is somewhere in the order of $750,000 to label the train split on this. It would be nice if we could take this and scale to the LiDAR data set, build priors, and we'll see some methods that do that today that don't require this enormous amount of labeling. So these are roughly the results. Our supervised method track flow was beaten by Flow 4D, which we'll talk about next, and as well as 2 very strong unsupervised methods that are quite good. So one of the big things that you can see is that pedestrian and wheeled VRU are where these methods are shining, right? Cars, you're not really getting much additional performance, but it's really these other vehicle category, it's a bit better. And then wheeled VRU and pedestrians, we go from, less than half of the motion being described properly to almost 80% of pedestrian motion being described well. So this is like a pretty significant improvement over what we had even a year ago. So with that, I want to talk about Flow 4D. This is a very interesting method because when we put out this challenge, what we expected for people to do is build more intricate loss functions, right? One of the things that people do when they want to do class rebalancing in the detection literature is they do all kinds of copy paste augmentation. They do all kinds of, upweighting for the rare classes. That's what we expected. Turns out that there's actually a tremendous amount of juice left to squeeze in the architectures themselves. So the key takeaway, I think, from this architecture is fuse early and fuse temporally the points. And by that, I mean, if you look at prior literature, what they tend to do is they ran a point pillars backbone on each point cloud individually, fused them after this feature preprocessing, and then computed flow. And it turns out if you fuse them much earlier, so rather than computing features independently and then fusing them together, if you compute features very early on and then do these 4D voxel convolutions, you don't need to change the loss at all. You just get significantly more juice, basically for free. So this is a more detailed diagram from the authors. Basically, they encode all of these points with a time as well as position information, and they're sticking them in these voxel features very early on. And then they have this 4D voxel network. One of the contributions they had is that they were able to do this as a 3+1 deconvolution as opposed to a full 4D. 4D is very expensive. And so they're able to get like the same performance with significant computational savings. So this method is yet to be published. They will release more details when they do. One of the things that I thought was very interesting is they provided an ablation. So they have a 2-frame and a 5-frame version of their method. The 2-frame method is, unsurprisingly, a little bit worse, but not much, which tells you that really most of the juice that they're squeezing out here is just better architecture design. So I think that one of the big takeaways from this for the community is this architecture is a step function improvement over prior methods. Like, don't use other architectures, build off of this, and maybe take a lot of the key insights that the authors have found and use that to build the next generation of stuff. So I was really excited to see this because they didn't do any loss function tuning at all. They had a standard loss function and got really good results. With that, that was the supervised winner. I'm now talking about the unsupervised track. So Yang Kong is sitting right there. And he is presenting this paper at CVPR. So please go talk to him afterwards and figure out when his presentation is. And with that, I want to tell you about what it does. So I would say that the key insight here is that you can get a lot of juice just by clustering plus doing ICP intelligently on these clusters. One of the big things is we have amodal bounding box annotations. They are rigid motion. Use that information to your advantage. So step one is do ego compensation. HD maps allow for ground removal. And what you get are these floating clusters of various objects, be it pedestrians on the sidewalk or cars driving down the road. You can do standard clustering to get these clusters. You then match them. And then really the magic sauce of this method is finding good initialization for ICP. So they do all points pairwise matching. They get a histogram. And then they use that as an initialization to figure out what the transform for ICP should be. Once you have this good init, you have, roughly, hopefully convex optimization service, and you're able to then lock in and get really good flow. And they use ICP for refinement. And so this is like a non-trivial improvement over prior methods. So like fast NSF and NSFP, these are like previous state-of-the-art methods. The jump here is on par with the jump from NSFP to fast NSF. So this is like meaningfully moving the needle. And this is an entirely unsupervised method, right? Zero flow labels. So this is an optimization-based approach. I want to talk about the honorable mention, SE flow, which takes a different look at things. So they were, instead of doing, test time optimization, they want to distill into a student network, and then you have a feed-forward network to actually do training and inference with. So the key takeaway from their thing is that, again, there's a foreground, background imbalance. You should actually be able to estimate jointly with your training whether these points are from the foreground or from the background. And this information is useful for class rebalancing purposes. So yeah, like I just said. And importantly, nearest neighbor alone is like kind of a bad prior. So this is taken from the Zero Flow paper. We looked at what is the error between the ground truth and nearest neighbor as a prior look like. This should be a dot. It's not. It's like all over the place, right? Something like neural scene flow prior, which we used as a teacher in Zero Flow to train a student, has a more collapsed error distribution, but it's still pretty significant. So instead of just using raw nearest neighbors, they use nearest neighbors as a noisy estimator to then do nearest neighbors only on motion clusters, and then use that refined two-step process to then train this feed-forward student. And what they found is this is much cheaper than running neural scene flow prior, which is a quite expensive test time optimization method. And it also provides better quality flow. James mentioned the LiDAR data set. This has been, I think, criminally underutilized. But one of the things that they do is, like with Zero Flow, they're actually able to take their method and scale beyond just the point clouds in the sensor data set. So they show not only do you get good results, as you scale up, you're able to go to 200 or more % of your training data set, and your scaling laws just continue. They only trained to 200% because they were compute limited, not because that's where it bent. So this is like a very exciting path forward as well. So, I want to close by saying the AV2 Scene Flow Challenge remains open. We've had a lot of progress over the last year. I think that this metric really makes clear what is it that we actually care about. And we went from methods that qualitatively kind of didn't work. I mean, I was the author of one of them, so I don't feel bad saying that, to honestly, these things work pretty well. There's still a lot of juice left to squeeze, and you should stay tuned because I know for a fact that we can do better. But I'm very excited for where the community is heading. I think we've had a lot of breakthroughs recently, and this is like a very fertile ground for more juice left to squeeze. So with that, I want to hand it over to Nihar for end-to-end forecasting.
All right. Thank you, Kyle. So today I'll be talking about the end-to-end forecasting challenge, and I want to start with an observation about the state of AV perception research. And it seems like there are almost two sub-communities within AV perception. And there are folks that work on detection and tracking, and here we're pretty used to working with noisy sensor inputs and intermediate representations. And then we have folks that work on motion forecasting, and different from detection and tracking, the motion forecasting setup assumes ground truth tracks as input. And in recent years, and in large part due to Uni-AD, which was the CVPR 23 best paper, there is significant renewed interest in end-to-end perception. So this is starting from raw sensor data and predicting all the way to forecasts. And in the spirit, we've been hosting the end-to-end forecasting challenge for the last 2 years to facilitate research on this problem using the AV2 sensor dataset. So this year we had 12 teams that participated with over 250 leaderboard submissions. And in this talk, I'll sort of briefly describe some of the progress we've made on these 3 different sub-challenges. So first I'll start with object detection. So the problem set up here is that methods are required to predict outputs for a 150 meter by 150 meter range over 26 object categories. So notably, this is much larger than comparable data sets. And methods have access to LiDAR and RGB point clouds. So first, before we dive into the methods, let's understand how they're scored. And the primary metric which we score methods on is composite detection score, or CDS. And I'll explain this metric with a small example. So let's go through the example of evaluating car CDS. So here in green, we have ground truth boxes, and in blue, we have predictions. Each prediction has a confidence score. We define predictions that have an overlap with the ground truth using center distance. We call these true positives. We can compute for these true positives average translation scale and orientation error. And predictions that don't overlap with the ground truth are false positives, and ground truth with no matched predictions are false negatives. So now that we've sort of split up the distribution here, now we can go and compute MAP, and we can compute the other submetrics of the CDS score. So CDS, which is largely inspired by NewScenes, is simply a product of MAP and a sum of these normalized true positive scores. Okay, so now that we know how to evaluate these metrics, let's talk about the challenge winner. And this year's challenge winner is a returning competitor from team LE3D E2E. And the key insight from their method is that there's still room to explore new architectures, new and better architectures. And in practice, this team uses focal former 3D, which mines hard instances through a multi-stage heat map encoder. And what this means is, in the first stage, they run their standard object detector to find the easy examples, and then they ignore these easy examples and run their detector again to try and find the remaining hard examples. And this better architecture pays tremendous dividends, as we'll see in the metrics. So their method here is an ensemble of ensembles. So they combine the output of their method from last year, which is the LE3D E2E detector, which we'll talk about next, in conjunction with focal former 3D. And importantly, focal former 3D is a LiDAR-only detector, whereas last year's submission was a multimodal detector. They combine these outputs through late fusion using weighted box fusion. And last year's architecture is a pretty straightforward multimodal fusion approach, where we can represent both RGB and LiDAR data through bird's eye view features, and we can combine these spatially and temporally before detecting things with a deformable deader head. So importantly, this method ensembles 8 different models with respect to different voxel sizes, different resampling strategies. They train some models that are LiDAR only, some models that are multimodal, and they combine all of these post hoc with late fusion or weighted box fusion. So importantly, although, as we'll talk about, this method performs incredibly well, this is far too slow to run on vehicle. But I still think this is interesting for off-board perception purposes. So if we have a large set of unlabeled data, like the Argoverse LiDAR data set, you can run this to generate some sort of pseudo labels, which can be useful for downstream perception. Okay, so comparing to last year's winner, so LE3D E2E won the competition both this year and last year, we can see they improve on CDS and MAP by 4% each, and they sort of beat all the other true positive metrics. And as I mentioned, the performance is largely due to this better architecture. So focal former 3D is really what's allowing this performance improvements. And if we actually break down this performance by range, we'll see that there's a modest improvement in the near field detection of 2%, but we see much more significant improvements from 50 to 100 meters, improving by almost 6%. and then from 100 to 150 meters, improving by almost 7%. So this is incredibly notable because in previous iterations of this competition, we've seen most competitors focus on near-range detection. So it's interesting to see that just by adding this new LiDAR-only detector, we're able to do significantly better at long range. Okay, and finally, this method shows better performance across rare categories as well. So as I mentioned, Argoverse 2 evaluates over 26 categories, many of them underrepresented, like strollers and wheelchairs. And we see that we're able to see considerable performance improvements across many of these rare categories as well. Okay, so that sort of summarizes the state of the detection challenge. Moving on to multi-object tracking. The problem setup is very similar to detection, but now we only look at a 50 by 50 meter grid. We still evaluate on the same 26 object categories, and the inputs are the same. This challenge is evaluated using a higher order tracking accuracy, which decomposes tracking into detection scores, association scores, and localization scores. So this is a very standard metric used in 2D tracking, and we simply repurpose this for 3D. And the challenge winner for this track is also Team LE3D-E2E. And this is really not surprising, considering that they use a training-free tracker, specifically AB3D-MOT. And for those of you familiar with the tracking by detection pipeline, given really strong detections, it's quite straightforward to sort of build a really strong tracker as well. So the top two teams used AB3D-MOT, and this is in stark contrast to last year's method from the same team, which used a learning-based tracker. So importantly, they use Motor, which is sort of an end-to-end learnable framework, which uses object queries from the object detector and sort of learns to associate objects over time. So simple trackers still seem to work incredibly well given strong detectors. And we can see this sort of play out in the metrics as well. So this year's winning team improves HOTA by 8%, AMOTA by 7%, MOTA by more than 10%. So all of this is really just because they spent a lot of time and effort tuning up their detector. So it still seems like, you know, if you have a really strong detector, tracking sort of becomes a much more simpler problem. Okay. We can compare the performance between the first place team, which is LE3D-E2E, and the second place team, Vallejo Forecast. And importantly, both methods here use the same exact tracker. So the performance delta between these two methods is strictly due to differences in detection quality. So I think that's interesting to note here. And that sort of wraps up the tracking side of things. And I think the most interesting part is end-to-end forecasting. So this end-to-end forecasting challenge also looks at a range of 50 by 50 meter grid. And different from most traditional forecasting datasets, we want to evaluate forecasting for 26 object categories. And the inputs remain the same as all the other sub-challenges. Importantly, methods are allowed to look at an unbounded history and are asked to predict the motion of all agents for the next 3 seconds. And we can reuse the sensor dataset, although this dataset wasn't meant for the task of motion forecasting. We can turn the track level annotations into forecasting annotations by sequestering parts of the track. And for this, we propose a new metric called forecasting MAP. And this metric is heavily inspired by MAP. And the only difference here is we tweak the definition of what it means to be a true positive. So in this forecasting MAP metric, we define a true positive to be one where the prediction and ground truth overlap at both the current time step and the final time step. And once we sort of modify the definition of true positive, we can simply compute MAP as normal. And importantly, the sensor data set, as I mentioned, is not really meant for motion forecasting. So what we find is most of the objects in the scene are static. So 71.2% of all actors in the scene are static. And we see about 28% of actors having some sort of dynamic motion. And this has notable impacts on algorithm design. So if we naively evaluated forecasting accuracy on the entire subset, which is dominated by static actors, we'll find that you can do really well by predicting that everything moves with constant velocity or doesn't move at all. So to solve this problem, we can break down evaluation by different motion subcategories, and we define 3. So static subcategory, the static bucket is defined by detections or trajectories where the final position is approximated by no motion. The linear bucket is where the trajectories or the final position is well approximated by constant velocity, and we bucket everything else into nonlinear trajectories. And we can compute a final MAP or forecasting MAP score by simply averaging performance across these 3 buckets. And the winner of this sub-challenge is the team Vallejo forecast. And interestingly, they repurpose leading motion forecasting methods, such as MTR. And it's interesting to note that this method in particular won the Waymo motion forecasting challenge in 2022. So this method jointly predicts global agent intentions and local trajectory refinements. But I think the most important thing about this approach is not their method, it's not their architecture, but rather the way in which they train their method. So first, they pre-train MTR on 1,300 hours of motion forecasting dataset. So using a framework called Unitraj, they combine the WaveScenes dataset, AV2 motion forecasting dataset, and the Waymo motion forecasting dataset. And they use this to pre-train MTR. And they train the model on the roughly 30% of dynamic movers within the AV2 sensor dataset. Next, they fine-tune their model with perception-augmented trajectories. And what this means is that they replace ground truth trajectory history with projected tracks. So this is meant to reduce the distribution gap between your perception outputs and your ground truth trajectory forecasting datasets. And they keep the ground truth forecasting targets. And then lastly, they apply a post-processing step. So as I mentioned, they only train on the dynamic movers. So this biases their method to predict that everything will be moving. But as we saw in the distribution of movers, most things in the dataset are not moving. So they simply replace the lowest confidence prediction within their top case set of predictions with a static forecast. And interestingly, this is very similar to last year's top performer, which uses data augmentation to also reduce distribution shift. But different from this year's method, they jitter trajectories with Gaussian noise, and they drop detections and interpolate trajectory history to increase the size of the data sets. Okay, so we can compare the performance between Vallejo forecast and LE3D E2E, and we see a substantial improvement in performance. So despite Vallejo forecast having lower quality detection and track predictions, they're able to get 13% higher MAPF compared to the second place team. And the performance really translates to nonlinear movers, where they're able to get more than 38% improvement. And this improvement is really due to their data augmentation and fine-tuning of perception outputs and post-processing steps here. So with that, that will conclude the end-to-end forecasting challenge. But we still have another forecasting challenge, which I want to talk about, which is the multi-agent forecasting challenge. And this is sort of the longest running of the Argoverse challenges. And we've run this challenge for 6 years, for the last 6 years, starting all the way back in NeurIPS 2019. And every year, we've sort of spent a lot of time and effort to improve the evaluation setup, introduce new ranking metrics. And year over year, the community has continued to impress us by improving motion forecasting performance across all of our different tasks. So a little bit of history here. The Argoverse 2 motion forecasting dataset was first introduced in 2022 and contains 250 scenarios across 6 different cities. And at the time of publication, this dataset was among the largest and most geographically diverse datasets publicly released to the community. And importantly, the AV2 motion forecasting dataset, unlike the sensor dataset, is highly curated to have challenging motion forecasting scenarios. So this dataset is chock full of AV-relevant interactions with socially complex environments. And we also look at interactions between the ego vehicle and non-vehicle actors. So the first iteration of the AV2 motion forecasting challenge, which we ran in 2022, only focused on the task of single agent forecasting, where we wanted to forecast the motion of a single focal agent. So this is an agent which we deem to be interesting and important within the scene. But importantly, this is sort of a limited subset of what we should really look at if we want to build safe autonomous vehicles. And safe planning, importantly, requires that we forecast the joint probability of all agents in the scene. So this sort of motivated the shift from single agent forecasting to multi-agent forecasting. And we instantiated this multi-agent forecasting through this concept of multiple worlds. So within each of these worlds, we want to predict the joint future states for all actors. So here is an example of world 1, and each world is assigned a different likelihood. Each of these likelihoods is normalized such that we can sum up the probabilities to equal 1. And this problem setup is very similar to motion forecasting challenges in previous years, where we assume 5 seconds of history. We know exactly the inferred actor types, and we have access to a local static map. And methods are required to output normalized probabilities for 6 predicted future worlds. And within each of these future worlds, all scored actors will need to predict a different trajectory. We'll need to predict trajectories for 6 seconds. And importantly, we only evaluate scored actors, which we deem important for planning. So before we can talk about how to evaluate this multi-world, multi-agent forecasting problem, let's quickly refresh ourselves on single agent forecasting metrics. So importantly, there are 3 metrics here. First is min FDE, which measures the distance between the best prediction and the ground truth at the final time step. Next, we have miss rate, which is the proportion of actors with a min FDE greater than 2 meters. And we have a Breyer min FDE, which is simply just min FDE with an added penalty for low confidence predictions. And we can take each of these single agent forecasting metrics and turn them into multi-world forecasting metrics. So min FDE turns into min world FDE, which is simply computing the lowest min FDE out of all predicted worlds. Miss rate turns into actor miss rate, which is the proportion of scored actors with min FDE greater than 2 meters in your best world. And lastly, we have Breyer min FDE, which naturally follows from Breyer FDE. Okay, so we've had a great number of submissions to this challenge this year. So we've had 300 submissions across 16 teams. Many of these teams submitted across leaderboards, including the Argoverse 1 motion forecasting challenge. And we had many entries from top teams of previous Argoverse forecasting competitions. And this year's winner is Light QCNet, lightweight query-centric trajectory prediction. And interestingly, there was a lot of tight competition towards the end. So Light QCNet beat out the second place method, LOF, by just 1%. So there was a lot of healthy competition going on in this challenge. So to briefly talk about Light QCNet, we first need to refresh ourselves with QCNet, which was the winner of last year's challenge. And Light QCNet simply modifies QCNet using patch-based attention modules, which are inspired by Behavior GPT. And if I'm not mistaken, Behavior GPT is one of the top competitors on the Waymo Sim Agents challenge. So by simply swapping out this patch-based attention, this method was able to show improved training speeds and reduced memory consumptions by 45%. And they're able to do all of this without having to sacrifice any accuracy or performance. Now, moving on to the single agent challenge results, we've had 300 submissions across 40 teams in this similarly tight time span. And interestingly, people were able to improve by 11% year over year in min FDE. So the best method here from 2024 is FutureNet LOF, joint trajectory prediction, and lane occupancy field prediction with future context encoding. And again, we had a very tight competition here between the first and second place winners. So I just want to highlight Sept++ was trailing just by 1%. So this was a really tight race towards the end. Okay, So FutureNet LOF incorporates recurrent context from predictions across all actors and predicts lane occupancy fields to jointly reason about goals and behaviors of all actors within a local spatial region. So interestingly, although this is a single agent forecasting method that achieves the top performance on the AV1 and AV2 single agent forecasting leaderboards, it also shows incredibly strong performance on the AV2 multi-world forecasting challenge without ever explicitly being defined or designed for this task. So to conclude, I think there's a significant amount of interest in end-to-end forecasting and these challenges as a whole, but there remain a number of open questions. So first, we have this distinction between end-to-end versus stage-wise methods. So the top performer last year used an end-to-end method, whereas this year we're seeing the top performing teams using stage-wise methods. And although there are benefits to each, I think it still remains to be seen which one wins out on top. We also see that there is a lot of scope for leveraging trajectory level motion forecasting data within the end-to-end forecasting challenge. So the winner of this year's forecasting task, Vallejo Forecast, demonstrated that you can pre-train on 1,300 hours of motion forecasting data. And they're only able to do this because they're a stage-wise approach. Lastly, we see that data augmentation remains an incredibly important component when we try to bridge the end-to-end and standard motion forecasting tasks. So although the winner of the motion forecasting task, Vallejo Forecast, used one of the previous winners of the standard forecasting task, they had to spend considerable effort to bridge the gap and perform some sort of data augmentation to make it easier to work with predicted outputs or predicted perception outputs. And lastly, the key challenge that still remains is improving runtime for on-car deployment. So the winning detection method, which we highlighted, is an ensemble of ensembles with maybe 15 models under the hood. So I think it would never be feasible to try and run this in practice. So I think if we want to try and distill some of the learnings from this challenge into real on-car products, I think there still remains to be a lot of progress that needs to be made in this direction. So with that, I'll hand it off to Tarasha to talk about 4D occupancy forecasting.
Cool, thanks, Nehar. This is the last forecasting challenge for you all, hopefully. So I'm Tarasha, and I'm a PhD student at Carnegie Mellon University. Can you hear me now? Okay. I'm a PhD student at Carnegie Mellon University. I'm Tarasha, and I hosted the 4D occupancy forecasting challenge this year, which I'm presenting today. Let me start by talking about the task of 4D occupancy forecasting and why it holds relevance in the autonomous navigation stack. So recall that for perception and prediction tasks that we talked about till now, lots of costly human annotation is needed in the form of object tracks, labels, and HD maps of cities. But this annotation process is not really scalable. So we want to encourage tasks and methods that do not rely on these annotations and are rather self-supervised, so that they can take advantage of the ginormous amount of data that is being collected by autonomous fleets every day. So one such task in the autonomous driving world is called point cloud forecasting. Given a set of past LiDAR sweeps, it aims at predicting the future LiDAR sweeps. And no annotations are needed for this task because the ground truth is already available in the archival logs. Now, while this seems straightforward, understanding where every point in the point cloud is going to lie in the future is non-trivial. And that is because points depend on the intersection of rays from the LiDAR sensor and the environment. And these rays change with the change in the motion of the autonomous vehicle and the ray sampling pattern of the LiDAR sensor. So then accurately forecasting points requires accurately forecasting extrinsics and the sensor intrinsics and the motion of the environment. So we argue that from an autonomy standpoint, it only makes sense for the autonomous systems to make predictions about the environment that they are in and not the calibrated LiDAR sensor that they are equipped with. And to this end, instead of directly learning to forecast points, we propose that methods instead learn and forecast the underlying occupancy of the world. And once we have this occupancy, we can easily render it into future point clouds. So this brings us to a problem setup where we learn a more useful and generic quantity from exactly the same training data as point cloud forecasting, but without any annotations. And we call this task 4D occupancy forecasting. All right, but then how does one even evaluate occupancy? Because of course, we don't have access to the ground truth occupancy, which would have been the gold standard, but we do have point clouds that can be rendered from this occupancy. So for evaluation, we give methods query rays, along which they have to predict the distance that this ray travels before hitting a surface. And based on this distance, we calculate the L1 error and the absolute relative errors as our primary evaluation metrics. So for the second iteration of this challenge, similar to last year, we allowed methods to look at the past 3 seconds of data and ask them to forecast the next 3 seconds. And we defined a bounded volume called the near field volume within which all the metrics were computed. Traditionally, chamfer distance is also used for evaluating point cloud forecasting. So we compute that inside the near field volume and then also on the unbounded point cloud. And finally, this challenge was relatively popular this year, and we got a total of 42 submissions as compared to last year. And we had started the challenge last year with 2 baselines. The first one was a simple ray tracing baseline, which was based on an aggregation of past point clouds. And then the second baseline was a self-supervised method, which predicts 3D occupancy grid for every future time step. And then self-supervises using the ground truth point clouds after differentiable rendering. So the winner for the challenge last year relatively improved our ranking metric, which is the L1 error, by 8%. And this year, we had methods pushing the state of the art even further, relatively improving the L1 error by 24%. And I'm happy to announce that this year's challenge winner was Team Uno from Wabi and University of Toronto. And so they requested to present their method, and I invite them, specifically the authors Ben and Quinton, to take it away from here.
All right. Hello, everyone. My name is Quinn. This is Ben, and we're going to be presenting our submission to the Argoverse Occupancy Challenge Uno, a 4D occupancy foundation model. So Uno is a foundation model that is designed for the physical world. The way it actually operates is you give it a continuous point in space and future time, and it'll tell you if this point is going to be occupied. We also showed that it can be transferred to a variety of different downstream tasks, such as that of LiDAR forecasting, and also the task of bird's eye view semantic occupancy forecasting. So how do you actually go from unsupervised LiDAR information to occupancy labels? Well, the way you do this is by taking a closer look at the information you get at each individual LiDAR array. So if you trace the position of the LiDAR to every single point in the scene, you get some kind of information about which regions of the scene are unoccupied, since otherwise LiDAR would have stopped earlier. It also tells you that there must be a small region of occupied space behind every single LiDAR array, since this needs to exist to reflect the actual LiDAR itself. Now, this is pretty sparse supervision, but if we rely on the fact that neural networks are generally pretty good at generalizing and filling in the gaps, this actually allows you to get a pretty good supervision for all the occupancy in the scene, especially if you can balance the total number of sampled unoccupied and occupied points that you use during training. So more specifically, this is kind of how our architecture works to do all of this in a continuous manner. You take the past LiDAR sweeps, you put it into a voxelizer with the timing and intensity information, you put it into a LiDAR encoder, which produces you a bird's eye view feature map. And now let's take a single look at a single query point. So what you do is you take the bird's eye view feature map you got from the LiDAR and you interpolate it at the XY location of the query point you're looking at. This can be used to give you an attention offset, essentially telling you where else in the scene to look for other information. And this can be used to, again, interpolate a secondary feature vector. Taking it all together, you can use this information to produce your future occupancy predictions. So this is really nice because one, it can run in real time in a large number of different query points, allowing you to actually, again, render larger scenes. Two, it has a larger receptive field because of the deformable attention. So that allows you to basically track fast-moving vehicles that maybe exist in the scene. And finally, most foreground motion that you care about in self-driving scenes happen in the bird's eye view plane. So this kind of summarizes this and distills the information into the regions in the actual format that you care about.
Yeah, so as Quinn said earlier, to perform LiDAR forecasting, we want to leverage UNO's understanding of the geometry and dynamics that it has in its occupancy. And to do so, we attach a small learned renderer, which transforms UNO's 4D occupancy fields into LiDAR point clouds. The learned renderer takes a query array as input, and in turn queries UNO for occupancy values at regular intervals along that array. These occupancy values, along with their positional encodings, are fed into a small MLP, which predicts the LiDAR point depth and is trained with an L1 loss against the true LiDAR point depth. So we have a qualitative example here, where on the left we have UNO's, let me put this in loop, UNO's point cloud forecast, and then the ground truth future point cloud. And we can see that UNO is pretty good at capturing moving vehicles, which we found that previous methods weren't so good at, such as this turning actor here. And this here is actually a small cyclist. And we get, as discussed earlier, large relative improvement from previous methods across all the metrics. So here we can look at the 4D occupancy forecasts underlying these point cloud predictions of both UNO and the previous year's method 4D Occ. So let me just loop this. So here you can see that 4D Occ struggles to generalize beyond the point cloud input and predicts all actors to be static, whereas UNO has a good understanding of the dynamic actors. And again, you see this turning vehicle here represented well in the occupancy and the cyclist here. Thank you for listening. And if you have any questions, we have a poster session later this week, so come to that.
Cool, thanks guys. Up next. Okay, I want to announce the runner-up of the 4D occupancy forecasting challenge, which was Team NLK from DGIST and Naver Labs. The method that they developed is largely based off of the self-supervised pipeline that we saw before, except that the 4D encoder decoder, or specifically the unit, is slightly different. Specifically, the input LiDAR sweeps are used to construct a single 3D voxel volume, which is then passed through a feature extractor and an encoder, once again to predict a single bird's eye view feature map. And then this feature map is passed through a temporal decoder, which predicts occupancy features for each future time step with information from the previous time step. And then finally, there's an occupancy classification layer, which classifies each voxel of the future occupancy grids into whether the voxel is occupied or not. And this is surprisingly effective in capturing dense information about the occupancy of the world as compared to the last year's baseline, which was 4D Occ, as you can see here. And for both the winning methods, I am showing a high-level overview of their pipelines. And the one thing which is evident is that both methods use an intermediate bird's eye view feature map to bottleneck their pipelines. So even though the input and the output are in 4D, which is in 3D space and time, the right intermediate representation seems to be the bird's eye view feature maps, likely because they can capture any dominant and relevant motion in the scene for driving. Finally, in general, for occupancy forecasting, I think we still need to think about how to forecast multimodal futures while learning the driving dynamics, and then also tying in quantities like scene flow, which can be used to represent physical constraints like conservation laws for occupancy. And with that, we come to the end of this year's Argoverse challenges, and all the challenges are going to remain open even after CVPR, and we'd like to encourage you to submit to them, and we can take any questions you would have now. Hmm.
Yeah.
Cool. Thank you.
Okay. So thanks a lot for the Argoverse team. It's always great to have you here. And as said, there is now the lunch break. Please have a look at our posters. There should be close to the place where you can get your food.
Yeah, okay. Yeah, I'm going. Yeah. It's actually, I think we're good to see you. Good presentation. I'm serious. Really. So,
And then it will start the red phase and the red because you very high. And then you can't restart it actually. So yeah, this is keep it wrong. And I'll be protecting these.
They are for the folder, yeah, already.
Yeah, maybe we can get back from him what's going on. Send you a message. I don't want templates. There's a dumping shop. Yeah, so we can order pickup probably. Be ready. You want to do that?
Yeah. From which website?
I just found this. Like,
I had that yesterday. I don't like it.
On different locations. I'm going for a very small radius because we need to be quick. There's a bump, the bump will have to like a bump. So
I also or I just go.
Sure, Stella, what are you?
Oh, she's and we also get a back.
Get it back.
On
okay, I'm gonna get them because I know
it turns out more data. Anything like
I can get more for other information. I'll have to go there.
I can keep track here.
Okay, I'll bring you. Start this and we'll bring your lunch. Okay. You want to pizza or ahead?
So here's my right. We have the ability to run for
water,
right. Your method. In zero flow, like I could choose to reintroduce the counting points, but for the feed forward network, you could. So what I'm planning on doing is like finishing up some papers just do obviously it's slightly better problem.
Yeah, and I can just like take it.
When you're done, you have a keyboard network. Doesn't just need to know how to park, which you could solve for.
I would love to have
I mean, no, like, the problem.
But I don't know.
Video right you should demonstrate skip though. It's actually
way over, but they.
I mean, if you have a you have
We have the
Yes.
Yeah, right. So if you have a join all their brains.
Yeah, and then I said, yeah, if you can, you just send your Gmail.
So but you're just doing right over the yeah. So I think we should do
everyone has it. Yeah, but everyone has one.
Use that.
I'm thinking some kind of low level. Data sets have
Very big.
Can you say something?
This is muted, right?
No, it needs to. Red is on.
Oh, okay. All right. Is this working? I think it sounds like it is. Yeah, sure. I think we have the audio working. Yeah. Okay.
That's it.
So I'll need to rejoin and
Stop sharing, and then I put. Once you rejoin, the settings for the audio should also be taken over.
Okay.
That should be all no problem.
All right.
If you leave the screen, I just need to make you a co-host again. But I mean, we
make sure it's the right device. So input should be USB. And speaker should be external headphones. Can you hear now? Hello?
You're there.
Good. I think so. Are you amplified? Yeah.
Yeah, looks like.
Okay.
Yeah, I think we're good to go. Yeah, great. Yeah, thank you. What's the effort of converting?
Oh yeah,
Yeah.
just safe.
Yeah, okay. Yeah, there's still one. The sound out, but it's fine.
Oh.
Yeah, it's fine.
Yeah. Is
What's
that a voiceover or?
there's a voiceover. Yeah, it's just showing people how excited they are.
Actually, nice that we had it. Can you not when you click share screen? There's a checkbox in the bottom.
Let's try another
And that-
time.
Yeah, and that should ask you whether you want to share audio. So if you click this, right?
Click this, right? Yeah.
To share audio, share a tab instead. Oh,
It's not
a
browser window. It's not a browser window, so
Okay.
I
So
don't
it
know.
might
be the case that using the web interface, it's not possible to access a different app on the computer.
Oh, only Chrome, yeah, within the
Exactly,
browser.
but only within the browser you can share it.
So if it was Google Slides, in that
But then
case,
this setup wouldn't work anymore. So I think
Yeah.
the way
Okay.
it is right now, I think it's the best.
Okay, I would
talk it over.
I would just delete that one. Let's just make it.
Or you can like do the excitement yourself.
Okay, I'll just
Yeah.
speak a little bit.
Voice. Oh, hey.
Apologies, I can't join for dinner tonight.
Oh, it's fine.
I'm on a
Yeah,
7:30 flight to San Diego.
Oh, wow.
Oh, yeah. So, I'll be back. Is there any-
所以现在做的就是他那个 online mapping 是没有现场的高精地址，可能是就通过周围的证据，然后推到传到网上推到生成。如果 end-to-end driving 确实不用高精地址需要这个。
All right. Yes, that seems to be working. Good.
Okay, so for the Zoom call, I can now go ahead again. It's a great pleasure to introduce Nick Roy, who is a principal engineer at Zoox. His research focuses on decision-making under uncertainty, mobile robot autonomy, and human-robot interaction. Nick is also a professor at MIT, where he leads the robust robotics group. Today, he will share his work at Zoox towards scalable and robust autonomy. Please join me in welcoming Nick.
All right, very good. Thank you. Microphone working okay? Excellent. All right, so it's a pleasure to be here. Morning was full of inspirational talks, and I really want to thank the organizers for including me and Zoox as part of this. And although I am a faculty member at MIT, I'm on leave, and what I'm going to be talking about today is a lot of the exciting work that's going on at Zoox. And I want to emphasize that I am representing, a bunch of people and a lot of different contributions here, some of whom are here because I've ruthlessly stolen slides from their own presentations, but there's many more people supporting this as well. I have the pleasure of helping lead the architecture group at Zoox. Yeah, there we go. And one of the things that I wanted to talk. All right, this works. Very good. One of the things that I want to talk about is Zoox's perspective on how to actually organize a lot of the processes that go into developing and operating an autonomous vehicle. Had I given this talk even 6 or 7 years ago, I think that I could have rendered this, or I know I could have rendered this architecture and said that pretty much every single operational autonomous robot of any kind, whether it is a vehicle on the streets, whether it is a rover exploring the surface of Mars, whether it's a factory robot, more or less is an architecture that looks like this, where we have sensor data that feeds into some kind of estimator that estimates the position, whether it's using GPS or doing entirely onboard exteroceptive sensing. That produces typically some kind of probabilistic estimate that then goes into a planning system. If you're operating in a dynamic environment like a self-driving car does, then you might have a prediction system, and that goes into a controller. And that bottom layer of computation is replicated in almost every system that exists, or certainly every system that existed at the time, and worked extremely well. We have been very good as a community at deploying robots that can move around through the world more or less collision-free for a long time. But that bottom layer is really only good for doing one thing, which is actually moving through what we typically think of as configuration space, moving from point A to point B. So if you actually want to do any kind of complicated mission, such as picking up passengers and dropping them off at a location, whether you're a drone doing deliveries in the environment, you typically have some kind of executive at the top that's sequencing the goals that you have to get to from point to point. And so we typically see 2 layers of computation, maybe 3 sometimes, that operate at different duty cycles. And that's really important when we think about the architecture of our systems. Now, I said if I'd given this talk like 5 or 6 years ago, pretty much every single system that we had operated that way. Things have changed a lot in the last few years. And now we have architectures that look a lot more like this, where we have like a learned controller that in many cases are going directly from the raw sensor input straight to the motors. And it's worth noting that even if you have a learned system that's doing a lot of the actual motion through the system, motion through the world, you typically have to have some kind of symbolic representation of the goals, if nothing else, to tell the humans that are in the loop somewhere. There's always a human in the loop somewhere. What exactly it is that you're trying to do and why, and maybe allowing the human to inject some additional guidance. It's also worth noting that these 2 architectures really represent 2 points on a continuum of possible architectures. On the left, I have the first architecture that I drew. It's often referred to in the literature as a classical architecture. I don't really like that designation. It suggests sort of like that architecture was devised by Gauss and Bayes themselves in a series of letters that were passed between Göttingen and Kent 300 years ago. It's still actually far and away the dominant architecture that's used by operational robots around the world. And then, of course, we have sort of what are typically referred to as end-to-end learned policies at the other end. And it's worth also thinking about what are the relative advantages and disadvantages of these architectures. The structured optimization architecture, the first one I described, is usually interpretable. Usually it's written, that's architected by people, and they put a lot of domain knowledge in there so that we can actually get a sense of agents as agents around our robot and objects as objects, et cetera. It brings with it a lot of the time an increased ability to provide guarantees. That's not to say the guarantees are easy, and sometimes they're not even available. But a lot of the technologies that we have for providing formal guarantees and verifying our systems are more available on the left. Joshua Bengio has been on the record saying publicly he thinks that guarantees of learned policies will only ever be available statistically. On the other hand, Drew Bagnell has taken the position that statistical guarantees are the only thing that matter anyhow, and he himself would never not get on an airplane that had only been formally guaranteed and never been flown. And he's not entirely without reason. It's probably the case that the left architecture is more data efficient. Certainly, VC dimension of a lot of the models on the left are smaller. And so, many verify or getting the data, learning the models of a smaller VC dimension is typically much easier than one big model of a much higher VC complexity. On the other hand, the left thing, structured optimization. Optimization is a very computationally expensive process, and it's usually more expensive on the left. On the other hand, we certainly believe that learned architectures are showing themselves to be more flexible. They're showing them to be more computationally efficient because you get to amortize a lot of the very expensive computation offboard over the lifetime of the vehicle. We typically don't have to write more code to generalize to more instances. On the other hand, I think most of us understand the amount of data required to do learning for any system of reasonable complexity some of the speakers this morning were articulating that that's really only increasingly available. I think Bolay was the one who said it's really only available in industry, and academia doesn't have the ability to scale. I'm not sure that I completely agree with that, but certainly it's the case that the architecture on the right is more data intensive. So the question then is, how do we get the best of both worlds? And many of you may be putting yourselves at different places on the continuum, and almost nobody's really all the way on the left. And there's not that many people who are deploying full end-to-end learned systems on self-driving cars on the right. Some of them may be in this room. I don't want to make judgment calls, but most of us live on the continuum somewhere. And Zoox is no exception. The position that Zoox is taking at the moment is really trying to, and we're not the only ones, and I don't want to pretend we're the only ones, where there's tremendous value in learning a representation of the world and where we are in it, but not actually learning all the way to the end, that actually creating a learned representation that is also interpretable and then is fed to that symbolic state executive at the top is really useful for a lot of the reasons that I said. We get a lot of the benefit out of learning in terms of flexibility and computational efficiency, but we get a lot of the benefit in terms of verification, interpretability that's available. And we're not going to pretend that we don't have a symbolic state executive that allows us to specify goals for picking up, dropping off, fleet management, et cetera. So most of what I'm going to talk today about is some of the challenges that we have faced in developing this particular architecture, and 3 of them are here. And I'm mostly, but not exclusively, going to talk about our learned estimation scheme. I mean, this is, after all, CVPR. And so what are the issues in terms of having a learned estimation that fits in the overall architecture for the system? So the first one that I want to talk about is that we really, if we're going to have a learned system that's outputting a particular representation, we actually have to make design decisions around the representation. One of the advantages of a full end-to-end learning system is that it's going to pick the representation itself. There's an entire conference called ICLR, the Conference for Learned Representations. We're actually going to make design decisions about the representation, recognizing the reality that that representation is going to, we're going to want it to be interpretable, and we're going to want to feed it into a mission planner at the top there. And so we want that representation to be designed for the entire system. So one of the things that's true about the Zoox vehicle is that we have a lot of sensors. We have more than most of our fellow, as Aisha, our CEO, likes to call them, fellow travelers in the journey to full self-driving. And so the question is, how do we actually process that sensor data? And one of the things that we are moving to, and many of you are ahead of us in that regard, but we are doing so at our own pace, is that we are fusing, we are not taking the position that we're going to process each of those sensor streams separately, but we're actually going to process those sensor streams together. So we're actually going to, what is now being increasingly called early fusion, combining our cameras, our LiDARs, and our radars into a single representation of the world. And so we're committing to a unified representation that combines the radars, all the LiDARs and cameras, et cetera. And this brings with it, without a doubt, data challenges and computational challenges, but it gives us the ability to reason about the world in some interesting ways. So one of the ways that it gives is that we don't actually have to commit to a particular representation that's human interpretable out of the sensors immediately. We're going to delay the decision to commit to that particular representation. So we've actually done a complete inference over all of the scene, geometry and velocity, et cetera. So this particular video here is some of our most recent results in building a representation that captures higher order attributes such as velocity before we actually commit to the notion of other agents. And what that means is that we don't actually have to we don't have to perform things like agent detection, car detection, vehicle detection before we can actually do inference over the velocity of components of the scene. We can, for instance, infer the existence of objects who we can't even necessarily recognize as, say the proverbial dumpster rolling down the hill at us, before we detect that something's moving in the environment, we need to do something about it. We still have the ability to extract the notion of agents with a particular velocity, and that's present in the image down on the bottom left. But we're able to extract the velocity, and that's really important for recognizing the world is full of things that we might not necessarily know about ahead of time, and we need to know that they're moving in order to plan robustly around them. And we're not the only entity, organization that has a representation of the world. Lots of other of you in this room may, in fact, we have representations, but we're really committing to this idea of a full representation of the scene that's fusing all of the attributes of the different sensors in one unified representation before we start extracting the semantically relevant bits that are really meant to feed into that higher level symbolic planning system. Another ability that this fusion gives us is the ability, for instance, to complete parts of the scene that may not be directly observable. So something that learning doesn't necessarily do a great job of is reasoning probabilistically a lot of the time. And I'll talk more about that in a minute. But probability and theory in particular gives us the ability to reason about things like observability. So if you are a classical control theorist, the notion of observability is really familiar to you in that it's it's what happens when the observability matrix is no longer full rank. Well, learned systems don't have the notion of observability. They don't have the notion of an observability matrix, in fact. And so the question is, what do you do when you actually can't necessarily observe all attributes seen in any particular sensor stream? I don't have an answer to that necessarily, but one of the things that we can do is we can leverage, learn models and previous data to complete parts of the scene that are not necessarily directly observable to us. And so this is some of the work that Nick Green in particular has done in terms of actually using, past data from different sensors in order to actually learn to complete the depth model for us. And again, we're completing a human interpretable depth model, in this case, the road surface, in order to be able to make planning decisions. The notion of learned depth completion has been around for a really long time. In fact, it was present in the first DARPA Grand Challenge many years ago. But fusing the notion of depth completion across multiple sensors is something that we've only seen certainly in the literature and that we've been able to do in the last few years. But the idea of a system wide representation shows itself, I think, most acutely in the notion of debris. So debris is something that we have, and I suspect many of you have also wrestled with in recent years. The idea that there might be objects in the world that we don't know anything about. And many of them are often hard to see. So the notion of a wooden plank in the road or a flat tarp. And the question is, do you drive over it or not? Do you even recognize it? How do you put it into the world representation? And debris that we experience in the world on the road surface, where we don't necessarily know what it is particularly hard to detect from a single modality alone. Debris from a vision perspective, has a high variability in appearance. There are a lot of the time there are false positives, and then there may be patterns on the road that we don't necessarily know about. And detection is fundamental in camera images is fundamental, at least initially, a 2D process. Contrast that with LiDAR, where the debris is often characterized by having very sparse points. We can't get much in the way of texture. These are two examples that we've encountered where the debris in particular is very, very hard to see in both the LiDAR data and the camera data. And without getting into the details of how we actually detect debris, the point for us is that we really recognize that there's a whole class of objects out there that are, we're all familiar with the long tail, that we're never going to be able to get any particular kind of classification. The idea of actually training a classifier around debris is not a sane concept. But what is a sane concept is, are there properties of the scene that have implications for planning? The real issue for debris is, do you drive over it or not? Is it dangerous or not? What is the level of risk? And so this particular video here shows the results of our debris classifier, where we haven't trained a system to actually recognize debris or not debris. What we have trained is, what is the level of risk for our planner? And we're using a planner that computes expected costs. And so we can actually train a classifier here, or really a regression model, to actually predict discrete levels of cost, and then incorporate that into the planning system. So this, I think, is a really, really good example of why we at Zoox in particular have chosen a particular architecture that outputs interpretable representations that have system-wide implications. Is that debris itself is not really interpretable from a human being, but it is interpretable by a planner in terms of what is the expected cost. And we're familiar as human drivers with the notion of avoiding debris when we can, but also taking some risk and driving over things like a plastic bag, when avoiding it might, especially at high speed, might bring risks of its own. And we can do a more principled trade-off in terms of those kinds of costs. Okay, so one of the principles that we're pursuing in this particular architecture is the idea that we can design representations explicitly that are intended to support human interpretability, and we can design representations that are designed to support the needs of the planner, but at the same time, we can train the learner to meet those particular requirements. But I think a common theme, looking back at a lot of the presentations at this workshop and over, so I think this is the 7th iteration of this particular workshop, a common theme over many years has been, what do we do about learned systems in the real world where we're going to encounter sensor data, we're going to encounter concepts that we haven't seen before. Machine learning has this very brittle assumption that we're familiar with. All our learning algorithms assume that all the data are independent and identically distributed. And that's just not true of embodied intelligence, agents acting in the real world. We're going to encounter scenes, images that are outside the support of our training data. And what do we do about them? And so we also have some things to say about this. OOD detection has been well studied in the literature for many years. These examples here were pulled up by somebody that we had working on this. I wish I could say we actually encountered these in the real world. We haven't encountered anything necessarily as exciting as this, but it's not hard to believe that driving through the streets of San Francisco or Seattle, you might see something like this. So what is known about saying something about how much you can trust your learner when it's presented with an image like this that it hasn't been trained on? Well, a lot of work has been done on this problem. There's a few representative citations on the right here. I know some of the authors in this room are in this room. If you haven't seen the particular survey by Galakowski and about 30 other people, I highly recommend it. It's very, very thorough for actually understanding how to model the uncertainty out of especially deep learned models. But it's not hard to get a learned model to output its own output distribution, which is in essence is a distribution over possible errors. One of the problems with trusting the output of a learned model is that it tends to conflate things like a label uncertainty or loss of observability with uncertainty that might come from the fact this is an unfamiliar training instance. And so, experience indicates, not just from us, but from a lot of the literature, is that simply training a deep network to be uncertain about its own model is not necessarily the best way you can go about doing out-of-distribution detection. Another approach is to actually look at the input density, try and model the density of the training data, and to notice when a particular query is far from the training distribution. And you can build a model of the input density using something that the most common technique in the literature is this idea of a normalizing flow. So one of the problems with deep networks is they're building their own internal representations. They're building their own features. And we train our neural networks to use all of the available computation to express the training data. There's no input feature representation. There's no computational power that's spent on anything other than representing the input data for the purposes of the loss function. And so what that means is that when you have a query that's far from the training data, it's going to be far from the features that you train the neural network. And so you can get a problem of aliasing where your novel query can actually look very, very similar in feature space to your training data. And the neural network has no way of knowing whether or not it's really far. So one of the normalizing flows basically forces a probability distribution to have representational power. I mean, I'm blurring over a whole pile of details, but a normalizing flow basically forces the density estimation to have representational power everywhere. It's going to try and put as little representational power over places that are far from the training data, but it's going to put some. And so this kind of basically hedges against against the aliasing problem. But one of the problems with normalizing flows is that they are very computationally expensive. You're basically forced to have an entire other network for representing the training, the input density separate from the task at hand. And so you're still a little bit vulnerable to aliasing without normalizing flow, and it's computationally heavy. One of the things we've been able to take advantage of is the recent work in foundation models. So the essence of a foundation model, and more accurately, the essence of the pre-training process, is to try and make sure that you have a representation that's going to generalize against all the things that you can think that you might ask your network to encounter. So that's really what pre-training is doing. It's trying to build that representation that sees all the things and knows all the things. And so aliasing is much less of a concern now. And so one of the things we thought was like, well, okay, if aliasing isn't a concern, maybe we don't have to have the full computational power of a normalizing flow network. And we can just build a density estimator over our latent space, our foundation model features, and then use that to predict whether or not the query instance is low probability and do something about that. And so we tried this on a few of your favorite foundation models, and we actually got fairly good performance. So in this case, positive means it's in distribution. So false positive means we got a query from a held out training set that we thought would be out of distribution, that the network thought was in distribution. And you can see we tried a few different foundation models. We got pretty good performance on using Dino v2. So that was very encouraging. Mind you, we actually had a task at hand. So we picked a task that we do on vehicle, which is to actually classify vehicle lights. And the way that we typically use the vehicle light train the vehicle light classifier, is to take a foundation model and then do fine tuning, as we all do on the vehicle light classification task. Alas, the fine tuning basically destroyed all of the representational power that a foundation model had carefully built up. And all of a sudden we got very bad out of distribution detection. And in fact, our held out of distribution set in orange, all of a sudden looked incredibly in distribution on the vehicle light classification test. So that was sad for us. But happily, Till and Daniel had an excellent idea of actually regularizing against the original foundation feature. So do your fine tuning while actually telling your fine tuner to actually try and preserve a lot of that representational power of the foundation model. And huzzah, we all of a sudden got back a lot of our performance. We didn't, you give up, there's no free lunch here. And so we gave up a little bit in terms of out of distribution detection performance, and we gave up a little bit of vehicle light classification performance, but not so much that it was a problematic. And so now our aligned features are aligned with the foundation model, do well at both of these tasks. And just to give you a flavor of some of the kinds of things that we can do with this is that, you could see that the in distribution, things that are far from in distribution, on the top left here, but we're still in distribution, are sort of odd things like, badly saturated vehicle lights or vehicles of the kind we hadn't seen before. But a lot of the things that were out of distribution are the trucks on the bottom left. And so we've got now a process in place for taking advantage of foundation models, and we're trying to now deploy that more widely in the different systems. And the really nice thing about this particular form of input density estimation on the foundation models is that we're using the same features that we were using for the task anyhow. So the computational hit that we're taking, that a lot of systems that do out of distribution detection are taking is de minimis here, very little computational overhead. So that's very nice for us. And so that's another reason why we have this architecture, is that we can do out of distribution detection in advance of making decisions. And so what that means is that we can tell the planner, we're very uncertain about what this particular entity is. And the planner, again, computing expected costs, can plan according to the fact that we don't really know exactly what this thing is that we're looking at. But at the end of the day, how am I doing on time here? Oh, I've got 7 minutes. All right. At the end of the day, we do need to train these models. And so we need some way to actually get the data. And so once again, this particular structure for us is very, very useful because it allows us to avoid having to pay, or let me back up a second. At the end of the day, data is very expensive, and we can go out and get it from the real world, but we can't really get all the data that we need. So we have to do simulation. There were a lot of great talks this morning about different ways to do simulation. But we don't really want to pay a lot of the computational costs that we saw this morning, that like doing end-to-end photorealistic simulation with all the physics and all of the closed loop driving is maybe a cost that we have decided that we don't necessarily want to incur. And so actually being able to simulate the output of the perception system without actually having to run the entire system and be able to simulate the interpretable symbolic representation is really powerful for us, and being able to generate scenarios that allow us to test out, for instance, the planning system. So this is a little bit more about how we replicate the effects of the learned perception system without actually having to run the full learned perception system. So the problem that we really want here is that we have some description of a desired scenario, again, human interpretable, and we want to generate a scenario that we can run in simulation without actually having to do the full photorealistic simulation. We want to test out our closed loop simulation. And we're going to fill this, of course, with yet more AI magic. The thing that we're really going to use here is a diffusion model. And Bolay talked about some work that he and his group have done in diffusion modeling. We're definitely inspired by that, traffic gen for sure, and also scenario gen and others. But the thing for us that we really want is a lot of the existing diffusion work was conditioned on the world representation. And so you could, like, just for those who don't know, diffusion basically generates random noise and then as a learned model, it progressively refines it until you get the concept that you want. And so you can imagine generating like other agents around you somewhat at random, and then using the diffusion process to slowly refine that until you get to a scenario that actually has like agents in sane places in the map and going sane velocities, and then you can run your forward simulation around that. But this is conditioned on the map for sure. But we really wanted some way for the engineers or to either be able to give an example scenario and say, please simulate a bunch of things like this, or even better, be able to type a description of a scene and say, please simulate a bunch of things like this. And so our diffusion model is not just conditioned on the environment and the map that we want to condition on, but we're also able to condition on tokens that the engineers might give. And so here's an example where we condition on, say, two agents at a particular environment. So let's say agent A is us and agent B is, no, I think it's the other way around. Agent A is some other agent and agent B is us. And we can even say the extent to which we want to populate it at random with other agents that we might be interacting with or have to drive around. And we can go use our diffusion model to explicitly condition on that set of tokens. The most revolutionary idea, conditioned diffusion is something that's been around, but we're very pleased that we're able to use this to do our scenario generation. Essentially, our structured representation, our structured architecture gives us a way to simulate these things and then run simulation and validate a lot of the planning system that we're developing. And so we can condition on specific interactions that we might have between agents to test cases. So that's a U-turn. We can do things like parking or get on road, where again, condition on, say, the parking token, we can put a particular agent in a particular location pulling out of a parking spot. We can also control the extent to which there are other agents that are parked in that scenario. And of course, it's a diffusion model, so we can control the extent to which we're fuzzing the scenarios and control the variation of the scenarios that we can produce in this case. And the really, really useful thing is that we can combine both an existing scenario that has existing agents in it. We can condition on that scenario and those agents and the natural language tokens as well. So it gives us a very seamless way to like inject both the results of the perception system for a particular log and the additional variations in the scenario that the engineer might be actually wanting to condition on. And so other folks have done things like adversarial generation of scenarios, looking for ones that are most difficult. This has given us the ability to actually inject domain knowledge and actually generate a wide variety of scenarios specific to the particular scenario that we're conditioning on. So I've talked a lot about these particular issues in the autonomy architecture. I do want to take last couple of minutes here and talk about Learn Planner. Well, I'm actually not going to talk about the Learn Planner. We do have some work on Learn Planning here, but rather than talk about it, I'm going to point you to a workshop tomorrow where Moritz is going to be talking about some work that we're doing in JAX accelerated reinforcement learning. So the idea, of course, is like we want to have use reinforcement learning to learn to drive not only like humans, but in fact better than humans. That is really, really hard to do, to outperform human behavior. I think a lot of the evidence is that human behavior is a really, really good training signal. If you want to go beyond that, then scaling up to the defense of the arts or AlphaStar, that requires an enormous amount of data. And gathering and in particular, you'd actually like the data to match a lot of the experience that you have. And so without getting into the details, and please go and talk to Moritz tomorrow at the workshop about the work that we've done, is actually being able to show that we can scale up by taking advantage of computational and basically good engineering processes, figuring out how to perform parallel execution, being able to take advantage of JAX in order to actually combine the simulator with the RL framework and be able to train policies with very, very large amounts of data, much more than we've been able to do before. The reality, unfortunately, is that the volume of data is still very, very computationally demanding. And the second speaker this morning, whose name I'm blanking on, I think it was Kalyak, really alluded to this, is that, you know, we still have a problem in terms of the amount of data that we need to train these things. So I think there's still more work to be done, but please go and talk to Moritz. So very, very briefly, the last thing I want to talk about is the fact that I haven't really talked at all about this top layer in terms of actually getting these smart cars, these self-driving cars, or any other agent, a robot in a factory, or if you're Adam Bree and you've got like a fleet of drones flying around, how do you actually communicate in a more intelligent manner what it is that you want out of them? One of the things that I like to point out is in this architecture, even this structured optimization architecture, it worked really well because a lot of these components were built out of data. Things like system identification is basically a very early form of machine learning. And I can highlight in green here almost every arrow and say that I knew how to actually train this system with data. But these arrows here, we actually don't really know how to train them in a way that gives us the same kinds of performance that we want. And a lot of time we end up hand engineering this relationship between a higher level executive. Sonia alluded to this morning when she said, you got to make sure your tokens line up with the underlying system. And that's true, but she didn't tell us how. And I think it's still because largely it's an open question, how really get, what is the right optimization strategy for generating a symbolic representation at the top level that gives us good performance throughout the entire system. So with that, I'll stop here, say thank you very much, and happy to take any questions.
Since we are already running a bit late.
Sorry.
No, don't worry. But we will skip the question if it's okay. And I'm sure you can find Nick and ask him in a break or at the other coffee break during the conference. It was a pleasure to have you here.
Thanks, Andrew.
Thanks for the amazing talk. And yeah.
I cannot control this one either.
Sorry.
Thank you.
Okay.
30 minutes late.
Hey, okay, sorry for the delay. I think we now have it working. And if everything goes well, it should also work for the Waymo OpenSet dataset challenge afterwards. Yeah, sorry for the 30 minutes delay. There will be, unfortunately, no coffee break, but this will help us to get back on track. So with this, it's an honor to introduce Chongchong Li. Chongchong is a director of perception at Waymo, the autonomous driving company formerly known as Google Self-Driving Car Project. At Waymo, she leads a group of researchers and engineers developing cutting-edge machine learning techniques to power Waymo's autonomous vehicle fleet. She holds a PhD from Cornell University with various works in computer vision and image processing. It's a pleasure to have you here, and the stage is yours.
Yeah, thank you for the nice introduction, and thanks everyone for your patience for waiting. And obviously, like the Waymo system have really high level of security in using outside of like Google Waymo Alphabet apps, Zoom, right? So I'm excited here to talk about the future of scaling autonomous driving. So here, let's see. Okay, trying to control it again. Okay. So Waymo is the autonomous driving technology company with the mission to build the world's most trusted driver. And then like the Waymo driver makes it easy and safe for people and things to get where they are going to. So driving today is still not as safe as it could be, which is why safety is at the core of like Waymo's mission. So today, like over 50 million injuries and more than 1.3 million deaths worldwide happening. And actually like 50% of those deaths are actually pedestrians, cyclists, and motorcyclists. And according to some of the recent definitive NISA study, actually like a large portion of this crashes in the US actually involve the human as the critical factor, be it speeding or be it distraction from to our cell phones, or be it like drowsiness due to like lack of sleep, or the danger of junk. So this actually like we think the lesson with all these studies is that like how many lives can be saved and how many injuries and can be reduced by eliminating or reduce the human factors in driving. So in Waymo, like we have been testing our technology over the years with like really the longest and also the toughest like test. We have been driven the autonomously over 20 million miles on the public roads, and also like over 20 billion miles in simulation across 13 states of the US. And the Waymo experience like starts with like using the Waymo app. Like you can just like input the destination, like confirming the details of your trip, and then like just confirm, and then like the Waymo car will come to you. And then during your ride, there was in the screen, in the in-car screen, will show you what the Waymo car is seeing and thinking, and without overloading you with too much information. And with that ease, like you can just enjoy the peace and enjoy the time back in the car, in the spatial car, and then just knowing what to expect in your ride. So then the Waymo experience gets you, just like makes you feel like you are being there.
So currently, like we are operating autonomous driving in 4 cities regions, including San Francisco, Phoenix, LA, and Austin. And here I want to show you some of the recent situations we encounter. So here we are driving through some tunnels, and you can see the pedestrian is walking reversely next to us, and we are going around them nicely. So this is driving under a thunderstorm at night across the intersection. And this is driving across the bridge with the overhanging structures. And then right after that, we meet a pedestrian, a worker guiding the traffic. And then like we react to the sign and then walk around. And this is like after a U-turn, we encounter construction zone. And then we react to the sign, and then like following the gestures of the construction worker. And then we decide to go forward. And this is like we are driving in a very narrow street in San Francisco, and then like we need to navigate between like the vehicles, like including the open doors. Then we nudge nicely, but then like, at the same time we are still also cautiously making progress in this narrow region. So this is a busy intersection. So we are trying to make a left turn. And after we make the left turn, and we see a vehicle that is trying to reverse into the driveway. So we yield to them. And also, like because this is very dense traffic, we don't want to block other traffic. Whenever there's region enough for us to go around, we'll just confidently go forward. So over the past year, like we have been also like when we try to scale the Waymo driver across like the operating regions, we are also trying to like increase our abilities to handle more complex situations, and also like expand into like new operation regions. So one of them is on construction. So as you can see from the video, actually like construction is difficult because like the variance in its setup, and also like it's a very dynamic situation. So in this video, like our car encounter a construction worker holding a sign, and then we stop right away. And then the construction worker is walking away. We continue to stop, and then we see the construction vehicle is trying to move and pull over on the side. And then we see that the road gets opened up, and there's enough region for us to pass by. And so we gradually, slowly going forward. And at the same time, we also react to like the gestures safely and confidently going forward. Another complex situation is responding to the emergency vehicles. So here we are driving on the street, and we are approaching an intersection. And from the other side of the intersection, there's an emergency ambulance. So we just pull to the side, waiting for we see the flashing lights of the emergency ambulance, and we wait for this car to go by until we start to drive again. And this is another example, right? So we are driving in this tree, and in the oncoming lane, there's a fire truck coming, flashing lights, and then we stop to yield to the fire truck. So until the fire truck fully passed by, we would go forward again. So this very last example, like we meet an incident scenes, which is now blocked by a police car. So we understand that like this road is blocked. So then we now try to reverse and make a multi-point turn and get out of this road. And then like so we will choose an alternative route to go to our destination. So in addition to those complex situations, we also expand our ability a lot, like in the new driving scopes. One of them is freeway. We have increased our capability on freeway a lot. So now we are driving on freeways autonomously. And so in this case, you can see that we can drive from the ramp and merge into the freeway. and we encounter vehicles stopping shoulder, we give the enough space and using the right speed to pass them. And we can also go from one freeway going to ramp and then join into the other freeway. And the next example would be like, yeah, driving at night. Like you can see that we even meet like fast moving like motorcyclists. And also that like sometimes the freeway also have dense traffic, and then we need to make our way to do the lane changes without exiting wrongly. So that was the example we can do it. And now this one is at night, like we need to handle like construction or incident scenes correctly, responding to the emergency responders and driving through the regions. Last but not the least, like we also can exit the freeway, going into the ramp, but then you need to also start to pay even extra attention. Like for example, in this case, at night, there's a jaywalker close to the ramp, and then we stop like in time, like real-timely, and then react to them. So as I mentioned earlier, safety is at the core of our mission. And then we really believe that the transparency around safety is paramount for the future and also like the acceptance of the AV technology. So this is why like in the last couple of years, like we have been very actively sharing not just like the information about our approach to safety, but also the real driving performance data. So we published like multiple studies that provide a growing body of evidences showing that like the Waymo's drivers' safety benefits. Actually, in particular, our most recent study over the 7 million plus rider-only miles actually show that like the Waymo driver can reduce 85% of like can cause like 85% of reduction in injury crashes rates, and also like leads to 57 more reduction to the police reported crashes rates. So as I mentioned, like when we scale, right? So that's it's really critical and important to handle the long tail events. So here, like I would like to show a few out of distribution rare events we have encountered on the road. So one of the cases here is that like basically a BBQ grill like actually falling from the back of a pickup truck at a really high speed. So the next here is that like we actually encounter a housing lay, which very abnormal. The third one is that like we actually see a construction worker walking across freeway with the sign, they carrying a sign which occluded a large part of their body. So here, like, so because long tail handling is so critical for the scaling, over the years, like in Waymo, we have developed many technologies for long tail handling. This includes like the multimodality center fusion, which is to leverage like the complementary benefits from different sensor data, including camera, LiDAR, radar. And we also invest into different approaches to mine and augment the rare examples. And we develop different approaches for auto labeling, which can significantly increase the number of data we can use for training. And we also like develop the efficient ML ecosystem, which can help us to really iterate and improve our system very fast. So then what's the next, right? I think in this current period, like as we can all see, like seeing what's happening in generative AI, it's hard for anyone to ignore it, right? So today, like the current generative AI tech is the most mature in the language domain, but it's also evolving very fast for multimodalities. And in the next, like, in order to scale to more, handling more long tails, we also want to leverage the knowledge and reasoning capabilities in LLM and VLM for driving. So here shows some examples. The left side, I think this example is pretty popular on the web, right? So you give one of like the chatbots like this image like which contains like multiple of the signs about parking on this road, and ask them that like it's Wednesday at 4 p.m. Can I park at this spot right now? And tell me in one line, and then they will answer that like okay, you can park for up to 1 hour, starting at 4 p.m. And another example here is that we give this image and give like this prompt to another chatbot, asking them that what's happening, what should I pay attention to, and also why. And the chatbot will tell you that like, yeah, pay attention to the overturned car, pay attention to the emergency responders, and also the traffic. You should like slow down and be patient, follow the instructions, and also like look for alternative route. And then the reason is for safety and efficiency. So you can see here that like actually like the existing BLM models actually show pretty promising potentials for us like, to handle abnormal situations like this. And so in the following, I'm going to show you a few of the recent works in Waymo that try to leverage BLM for autonomous driving. So the first paper I'm going to talk about is unsupervised 3D perception with 2D vision language distillation for autonomous driving. This was a paper from ICCV last year. So the motivation of this paper is like, as we know that like, many of the current perception technologies rely on sophisticated network and requires like heavy human annotation. So the annotations we have are usually a closed set of predefined categories. Right. So however, the closed set approach like, have drawbacks, such as like human labeling can be slow, can be inefficient, can be expensive, and also limited to the predefined categories. So self-driving cars actually needs to handle a really dynamic scene. As Waymo scales up, we have covered more and more object categories and situations, but still anything can happen on the road, right? So therefore, like we actually like this may not scale, right? This predefined categories may not scale. So thus we desire open vocabulary approach that can localize and recognize objects of any arbitrary objects. And also with hopefully with very little to even no labor intensive efforts for scaling up. So as shown in the recent research, such ability of open vocabulary perception on 2D images can be obtained from the large language vision language models pre-training. So these models are trained with billions of image text pairs from the web, and they have shown great generalization abilities to many vision tasks from classification, segmentation to visual question answering. So then how can we extend such open vocabulary capability to the 3D modeling? So thanks to our calibrated sensors installed on the car, we can unproject the unproject the pixel-wise features, which encodes the open vocabulary semantics into the 3D point cloud. So we can develop a method that utilizes these projective features together with any other signals to obtain a 3D open vocabulary perception system. So this is the proposed design of the approach of the paper, and it evolves it includes like a two-stage training process that relies on knowledge distilled from 2D vision language models. So the first stage involves the unsupervised multimodal auto-labeling, where the pixel-wise features obtained from a pre-trained vision language model are then unprojected into the point-wise features using like the camera models. And this also enables a proposal of bounding boxes for the objects of interest. So this is shown as the bottom part of this graph. And then in the second stage, shown in the upper part of the graph, it actually involves feeding the point-wise features and also the auto-label bounding boxes to the object detector for training. So besides the detection losses, we also use like the distillation losses like to preserve the open vocabulary semantics in the detector parameters. So during the inference stage, we just use the text decoder in that text encoder, and then from this pre-trained VLM model, and then to prompt or to query for any of the desired objects. So what sets this detector apart from other previous works is that we can actually handle object category outside of a predefined set of objects. So the query is encoded and then compared with the point-wise features output by the 3D detector. And then this enables us to identify which objects belong to the query categories. So know that at the inference time, we actually don't need any of the camera inputs. And also the only sensor input to the detector is just the point cloud. So this shows the result. So here, our approach can actually pretty faithfully detect the objects of interest based on the user provided text prompts. And you can see that actually we can detect objects of quite some of the fine-grained categories such as bulldozer, UPS truck, and fire truck, traffic cones, trash bins, and so on. So the entire training process here in this approach is free of 3D annotations. So the second paper I'm going to talk about is Motion LM, which is also presented from my CCV last year. So in this paper, we explore a motion prediction model inspired by the current LLMs. So we treat the agents as participants in a constant dialogue, continuously exchanging actions and reactions, and mirroring the fluidity of conversations. So just as today's language models that can capture sophisticated distributions over conversations. So the question we are trying to ask is that can we leverage the sequence models to also forecast the behaviors of the role agents? So this work follows the parallels with the languages and discretizes the set of possible agents motions into the motion tokens and models the full joint distribution of these tokens. So then we can produce the full joint trajectories as it is all the participants talking to each other in a conversation. So this is the proposed architecture of Motion LM. So on the left, we have the initial scene encoder, which utilize the multimodal sensor inputs, including road graph and also any of the outputs from perception based on different sensors. And then we have this autoregressive transformer decoder. This decoder, which performs the cross attention to the scene encoding and also performs the cell attention to the motion tokens along the way. So here is how it works. The decoder samples the distributions of for multiple agents. Here we show two agents. One is in the green color, one is in the blue color. And then we sample the tokens and then we feed them back to the decoder. And then we sample that again and just keep going, right? So now at the very end, usually for behavior prediction task, we usually need to output a certain number of trajectory with probabilities. So what we do is that we just need to sample a really large set of trajectories, and then we can class them, use some simple approaches to class them into the desired K trajectories. And then at the inference time, we iteratively just sample the outputs in a temporal causal way. So as you can see here, you just roll out these features, given the context of a set of motion tokens in the past. And then we predict the next token of each agent. And then you take all these tokens and then roll out the future. And usually you can also sample several futures. And then you predict a distribution of probabilities of these futures. So here shows the example that on the right side is our causal joint prediction. So comparing to the marginal prediction, because we are jointly optimizing all the agents at the same time, considering all their paths tokens. So you can see here that the new result is avoiding the collision between the two agents, which is a more realistic behavior prediction output. And beyond that, we also have the qualitative result of the motion LLM approach. Comparing to like the previous state of art, it performs comparable on all the metrics, and also like performs better on especially two of the metrics like miss rate and MAP, which ensures usually like the more long tail behaviors. And with that, I'm going to talk about also like the last approach, which is last paper, which is the multimodality scene tokenization for motion prediction. So this is actually a CVPR paper this year, and the paper will also be presented in the next couple of days. So in this paper, so the motivation is that like, I think it's also mentioned related to what Nick just mentioned in the previous talk. Like many of the existing motion prediction models consumes the representations produced by perception and in a symbolic format, such as like the oriented 3D bounding boxes encoding the states of all the objects. And these representations, like it reduce the input dimensionality. It makes like the downstream models, like it can, the downstream models can be lighter weight. But at the same time, like this kind of models are also, this kind of outputs are also very easy to rearrange and manipulate it. So such that like making it very possible to construct hypothetical scenes during like simulation or other testing. So this is very popular use, right? But relying entirely on the outputs of like the symbolic outputs of the perception models can also result in like more fragile behavior prediction. So for example, like some of the perception models that it may fail to detect the novel obstacles that haven't been seen in training or haven't been labeled in training. And because of that, like, so the behavior prediction, if you only react to the symbolic outputs, like you may not like create the right prediction. And on the other hand, like, as we have touched the topic multiple times today, like end-to-end system can actually train on like the raw sensor data, can actually better handle some of these cases because like they can encode like some of the open vocabulary information. But at the same time, like the end-to-end approach also have like their own challenges. For example, like it can trigger a more significant computational cost, or it will lose out like some of the interpretability along with the modularity. So here, the approach here like is we are trying to answer the question that like, can we design a system that can enjoy the merits of both the end-to-end approach and also the modular paradigms? So this is the proposed paradigm the paper has. As shown in the graph here, the approach is trying to fuse both the symbolic outputs like, from the normal perception system and also introduce like the multimodality scene tokens. While the symbolic outputs, like, it offers a convenient world abstraction, the multimodality scene tokens actually links the behavior models to the more denser observations in the raw sensor data. So here, like what we propose here is to tokenize the visual world into a complex set of scene elements. And then leveraging the pre-trained VLM models and also the LiDAR neural networks, we can encode all the scene elements in an open vocabulary manner. The pre-trained VLM models helps us to encode the general information of the world, while the LiDAR networks can helps us to like continue to keep the geometric informations. And here as shown in this graph, the primary contribution of this approach is a method to really tokenizing the multimodality self-driving scenes. So to process the raw sensor data, we use the pre-trained model, VLM model, to encode like surrounding camera views, and which are then like projected into the 3D point cloud. And then we also encode the bounding boxes and also like other LiDAR point geometrics together, and also like pull all types of features and then into one token to represent each of the scene element. So here shows some quantitative result of this approach. So this approach that we abbreviate here as most, comparing to like the other existing approach, for example, the original waveformer, it has shown better performance across all the metrics. And here is also an example of the correlative result. As you can see here on the right side is the original waveformer result, which consumes only the symbolic perception outputs. So therefore, it doesn't take like enough information about the wall next to the road, and it produces a trajectory, which in blue, like the car can actually do a U-turn. Battery on the left, like because we the new paper, the paper we are publishing, like also like takes into account the raw sensor data, so it helps the model to identify that like we cannot take a U-turn here, so that like we can avoid hitting into the wall. And last but not least, we also evaluate the performance of this model by injecting perception failures and also the road graph failures. So as shown here, so the performance is actually on par with the original waveformer baseline, even in the case of like having a 50% perception failures or 30% road graph failures. So this shows that like with the open vocabulary manner, we actually help to tackle the situations that are when missing the symbolic representations of the perception outputs or road graphs. So with that, like I've shown like some of these papers, like this actually shows our promise of like the LLM VLM, like shows the promise of VLM for autonomous driving. But at the same time, like I think we still have many questions to tackle in this space. So some of the examples include like, for example, what is the best VLM architecture for autonomous driving? For autonomous driving, like different from like the normal Gen AI problems trying to handle, like we actually like features that we need to take a lot of temporal inputs, that we have like more abundant sensor modalities, not just camera, but also LiDAR, radar. And also we need to perform like spatial reasoning. So these are the unique properties of self-driving, and what should be the right foundational model architecture for this autonomous applications is still an open question. And beyond that, like there's also the open question that how do we reconcile the current but I will scene representation with the language-based scene descriptions, and how can we enable more train of the thought along the way? And beyond that, like, there's also more questions, including like the language condition planners, and also like how can we preserve like LLM, VLM capabilities given the very limited compute on the car. So there's many, many more questions that we need to answer. And then like we actually think that like this industry is evolving very fast, and we want to invite all of you like to join us to explore the space. And to conclude the talk, I want to show this video just to give everyone a relaxing moment. So this video is actually sharing like the riders of the Waymo 1 service, how they feel about the service and how passionate and excited they feel about riding the car. So with that, we also want to welcome everyone to try out the Waymo card when you drop by the operating regions. And we in Waymo, we look forward to continue improving this autonomous technology and then make it available for more cities. This concludes my talk. Thank you. Yeah, I would like to, sorry. Yeah. Just realized that, so therefore I don't want to move anymore.
Yeah, you should. Yeah, you exited that.
Yeah,
Okay, so let's do next one.
Okay, thank you.
Thank you so much.
I mean, Nah. So do you guys wanna just project again the full slide?
The slides.
Where is your slides? Email.
Yeah.
Where would you do that? Yeah. Okay, so now. We ready? Okay, so now I'm gonna just do desktop, okay?
Yeah. So first we connect. Do you want?
No, first I'll present desktop and then
Yeah.
connect.
Okay.
Share. Desktop.
Yeah.
Share.
Cool.
Presentamento.
You need manager approval.
Yeah. And now we need
now you're rock and roll.
Yes,
Okay.
thank you.
It has to be like a monster thing.
What? No, I don't think so. You need yeah, that's fine.
See if I can read.
Yeah,
It's
yeah,
a
that's
bit
fine.
too small.
Yeah.
I mean, we can move
You can bring a different computer if you want.
Like this. I'm gonna check Zoom. Actually, where are we moving it right now?
Can you check if there's like a video? Can we check if it's working?
Okay. Hi, everyone. Please don't leave. There is still exciting things to come. Next is actually again Waymo. This time with the Waymo Open Dataset challenges. It's always very excited. I think it's some of the nicest challenges out there. And it's a pleasure to have you here. And yeah.
Thanks a lot.
I think you can
Yeah.
start. Thanks.
Cool. Thanks a lot for the introduction. So I'm Nico Montali. I'm a research scientist at Waymo. And you just heard from Sonton presentation now, like what are the current problems that Waymo is facing and exciting new features that Waymo driver is acquiring. But now this time I want to shift the focus on how Waymo actually wants to foster and help the research community to solve these very important problems for autonomous driving. And we do this through the Waymo Open project, specifically the open data set and the challenges that we're going to go over today. Here, okay. So a little agenda for today's meeting. So we have first an introduction on the data set for the open data set and the benchmarks that are attached to this to the data sets with highlights of what changed since the last year we had the same presentation at CVPR. And then we're going to go into a deep dive into the 4 challenges that we hosted this year in the last 3 months. And we're going to have winners, a little introduction for each challenge, and winners talking about their solutions. Cool. So first of all, I would like to spend 1 minute thanking all the people that made this possible. It's been a very long journey, and all of these people put a lot of effort into it, and I'm really proud of what came out of this, and we hope like we really help the research community to advance. And there's also like many other people in cross-functional teams that are not cited in this slide, but they obviously contributed. So first I would like to start from the why. Why did we release the open data set and why Waymo wants this? So we believe that for machine learning, having data sets is one of the core important things that we need for research to function, because people need to be able to work on the same problem and share the same results and compare the results on the same benchmarks. Otherwise, it's difficult to say, oh, my method is better than yours. So we basically want to do this by releasing one of the largest and most comprehensive data sets on autonomous driving, which was collected by Waymo cars over the span of multiple years and multiple cities where we operate. As I said, this has been a very long journey. So from 2019, this was the first release of the perception data set. And up until now, we had many new features coming every year and many challenges that we hosted over the span of multiple years. And usually what we have here, it's a split between two main data sets, the perception one, which is usually for perception-related tasks, so detection, tracking, segmentation, and the motion data set, which is more related to prediction, planning, and simulation. So going a little bit into the details of each of these data sets. So the perception data set is mostly about sensor data. So we have LiDAR data and camera data. It has various numbers of labels for different tasks. So we have 2 and 3D bounding boxes, 2 and 3D key points, semantic segmentation of various forms. Last year, we also added the 3D road graph. So that's a map that basically you can use to align all the sensor data to an actual road. And I wanted to point out that last year we also released these two new formats. So one is the modular data set. Since this is a pretty big data set, it's a bit annoying sometimes to work with it. So we released this new modular framework where you can pull whatever feature you want without having to download the whole data set. And hopefully this makes it easier for people with specific tasks to make it easier for them to use the open data set. We also released the object assets data set. This is intended to help generative AI and NERF kind of system. And these are very comprehensive. So you can find all the information about this on the open website that is linked there. On the other hand, the motion data set is mostly about, as I said, prediction and behavior. It's much larger in terms of scenes. So we have 570 hours of driving with over 100,000 scenarios. And we've collected this in very different cities. So you can have a very different span of behavior from drivers and pedestrians and other dynamic agents. This is, again, mostly about 3D bounding boxes. So the output of a perception system and the map data, the 3D map data. But last year we did release LiDAR data for this for the motion data set, and this year we are releasing camera embeddings. I'll go a little bit more into the details of that because I think it's really important. We've seen a surge in end-to-end methods for starting from sensor data and going directly into planning and behavior prediction. For example, last year, Best Paper Award at CVPR was UniAD. So we really believe this is an interesting approach and very promising. So we wanted to make sure that people are able to use the Waymo open data set to solve that sort of problem. So last year, as I said, we released LiDAR data for the 1 second of history that you get in the motion data set. And this year we have released camera embeddings coming from a VQ-GAN model. So we took this approach because obviously having the whole camera images would have been very, very large in size. So we thought that it would be easier for users to just have embeddings coming from this model that we trained. And this has a very low reconstruction loss. So it basically contains all the information that you need to solve a certain task. So along with the data set, there are also a series of benchmarks that we have attached for the different tasks that we think are important for the autonomous vehicle research community. And these, we believe it's the most comprehensive set of tasks and benchmarks that is out there in the wild. And some of them are pretty mainstream, like motion prediction. But some of them were also pretty novel, like, for example, 2D video panoptic segmentation, pose estimation, the occupancy flow, and sim agent were something that it was pretty novel all the time when we released that. I would also like to point out that this is a very long-standing set of benchmarks. So the motion prediction, for example, we run for 4 years in a row. So it's good to see how much the research community is like approaching this problem and seeing improvements over the years is great. So I would also like to point out another piece of software that we released last year. So along with the data set and benchmarks, we also believe that tools are really important for the research community because otherwise you're not able to solve those problems. And one of the tools that we thought it was really important to have is a simulator. So starting from the motion data set type of format of data, so we have your bounding boxes moving around, you want to simulate this with different agents taking control of different objects. So last year we released Waymax, which is a lightweight research-oriented simulator to solve specifically planning and sim agent problem. It is fully differentiable, so you can backprop through it. It's hardware accelerated, so you can use a GPU or a TPU and you get a nice boost in performance. And it's multi-agent, so you can have multiple policies taking control of multiple objects at the same time. It is natively connected to the Waymo OpenMotion dataset, so it's just a plug and play thing, and you can use the whole of the OpenMotion dataset, which is great. And it's designedly, and it's written entirely in JAX, which makes it very easy to use external libraries and tinker with it if you want to. So we released this back at the end of last year. We got a lot of interest from the research community, and we're really proud of that. So we're continuing to work on this tool, and to make sure that this helps more in the planning sort of tasks. We are releasing by the end of this year the route for the autonomous vehicle, which means, you know, at that you're going to know the Waymo driver. We're going to provide the information of where it was supposed to go, basically. So all said that, I want to deep dive a little bit into the challenges that we had this year. So it's 4 of them: motion prediction, occupancy and flow prediction, sim agents, and 3D semantic segmentation. I would like to start by saying that I'm really proud of the results this year and the number of participants and the traction that we got on the challenges. It's always a nice thing to see year over year. We got a total of 94 participating teams, more than 700 total submissions over the 4 challenges, 46 leaderboard entries, and more than 10 countries participating. So I would like to thank all the participants and their great work. It's really great to see that over the years, a lot of these benchmarks are improving the state of the art consistently. And we're really proud of the quality of work that has been submitted so far. We are publishing the reports of the winning teams on the Open Dataset website and on the workshop website. So you're going to find all of those very easily at those links, I think. And yeah, said that, I'm going to give the mic to Scott, who's going to talk about the motion prediction challenge.
Thanks, Nico. I'm Scott. I'll be presenting the motion prediction challenge and the results for this year. So at a high level, the goal of the motion prediction challenge is to predict the positions of up to 8 agents for 8 seconds into the future, given the agent history and scene data for the past 1 second. And I'll get into some more detail about that. But first, I'd like to thank all the participants from the challenge this year. We had great participation, and we appreciate all the work that went into it. This is the 4th year that we've held the challenge since starting in 2021. As Nico mentioned, we've added this year camera embeddings to the data set as used for inputs to the models. And we've also updated our MAP metrics. We've tried to improve the trajectory bucket balancing and some of the corner cases. So to give you a feel for what the data looks like for the challenge, here's sort of a typical scene. We provide HD maps, and we provide 3D bounding box labels for 3 different types of agents. We have vehicles, cyclists, and pedestrians. We also provide labels for traffic light states, and we also have labels for interactions between agents. Not pictured here, we also have LiDAR data as input and the camera embeddings. So some quick stats on the data set. We have 574 hours of unique motion data. It covers 1,750 kilometers of unique roadways collected from 6 cities. Each of the examples is specifically mined to have interesting interactions. And we compute the perception label boxes in an offline in the data center so that we can devote more compute power rather than just computing what we compute on the vehicle for higher accuracy. And then in the last few years, we've added LiDAR and camera embeddings. So here we see an example from the training data set where we've got two vehicles trying to make unprotected left turns. And the goal or the task for the challenge is to take the first 1 second of this data and predict the trajectories of the agents in the scene for the next 8 seconds. And so in this example, there are three vehicles to predict. There can be up to 8 agents of any object types. And so because motion forecasting is sort of inherently multimodal, the models can predict up to 6 trajectories for each of the objects, and each with a corresponding confidence score. And then we use a suite of metrics that we provide on the leaderboard for each of these. The challenge winner is determined by a metric called soft MAP. And the soft MAP metric determines true positives using a set of lateral and longitudinal thresholds. These thresholds are scaled according to the speed of the object. And then we compute these buckets over 8 different trajectory type buckets, as well as 3 object types. And then we compute an MAP score over there. The full details of this metric are on our website for the Open Dataset Challenge. With that, I'd like to announce the winners of this year's challenge. In first place, we have MTR V3 from DD Global and the Chinese University of Hong Kong. In second place, we have ModeSeek, which is from the City University of Hong Kong, Hanhai Research Institute, and Carnegie Mellon University. And in third place, we have RMP Ensemble from National University of Singapore and Movida PTE Limited. So congratulations to all the winners. And now we have a presentation from the first place winner, MTR V3, from the authors.
Thanks for the invitation for the coordinator of the Open Dataset team. I'm Chen Shi from the Chinese University of Hong Kong. In this presentation, I will introduce our solution to the motion prediction challenge. Our framework MTR V3 builds upon the state-of-the-art motion prediction method MTR++, and offers improvements in sync encoding and trajectory decoding. First, let us briefly review MTR++, giving customers of agents and rule maps. An encoder network encodes sync context and generates sync tokens. Specifically, query-centric self-questionnaire is adopted. For each query token, it first converts some of the things to query's local coordinate system, and then utilize KNN algorithm to collect KNN codes, which serves as keys and values. This metric encoding of these context allows the encoded features to be used for predicting the motion of any input agent. After things encoding, a motion decoding network is adopted to predict multimodal field trajectories to alleviate the burden of prediction. MTR++ uses K-means algorithm to pass the 64 predefined anchors from GT trajectories of training data, as shown in this figure. The test queries are then initialized from anchors through MLT, and then aggregate context features from the encoded sync tokens through a set of decoder layers. Moreover, MTR++ introduced a mutually guided integration query module to model the interaction among intelligent queries. Based on this powerful baseline, our framework offers improvement in 2 aspects. Firstly, we incorporate raw data to provide fine-grained semantic information. Secondly, we utilize the evolving and discrete anchors to promote models regression capability. In orange motion prediction pipeline, we mainly focus on abstract representation of the things, including bounding box, hiding velocity of agents, as well as HD maps, which depict standard root graphs. However, RuSense data can provide more detailed information about the things, such as agencies by perception, module, dynamic sense context, network work, and more which root graph like chemical and chemical structure and so on. So we incorporate data point clouds to reconstruct the environment and complement the map information, as well as extract some important real-time context. To efficiently encode data point, we may follow the pipeline of MTT. Firstly, for each focal agent, we transform the point cloud data into its local coordinate system based on its position and heading. Secondly, we use a data intelligence network to extract voxel features and generate semantic labels for each voxel. Then to further enhance the representation, the one-hot included semantic labels and the voxel positions are concatenated with the orange features, resulting in 58 dimensions features. Finally, we apply sparse energy pooling operation to pull the voxel into DB space, resulting in data tokens with a total size of 1.6 meters. In Pico network, we use a dynamic strategy to gather related data tokens for each focal agent. Specifically, we define 3 target positions, including a current position P and 2 feature positions included from the velocity and prior knowledge. Then KNN algorithm is employed to collect data tokens for classification in Pico layer. The updated pipelines show this figure. In vanilla MTL++, the anchors are fixed, which limit the model's regression capability. So we utilize the involving and distinct anchors proposed in EDA. Starting from predefined anchors, EDA updates them based on the endpoints of predicted trajectories in Pico layer. This year, the scene-specific anchors. The MS operation is applied to select the distinct anchors to avoid gradient conflict among cylinder anchors. And finally, in the experiments, we can show that our MTL V3 achieves the first place in this year's motion prediction challenge. That is the end of our presentation. Thanks for your listening, and more information can be found in the technical report.
Great, and with that, I'll turn it over to Reza for the occupancy and flow challenge.
Hello, everyone.
Yeah, thank you, Scott. Next, you're looking at the occupancy and flow challenge, which is defined on the same data set as the previous challenge, the motion challenge, introduced by Scott. So I'm Reza from the Waymo research team, and I'll be giving an overview of the challenge. And following that, you'll see 3 very short videos from the winning teams. Like the motion challenge, the inputs to the model are past agent states, but the predictions are bird's eye view occupancy and flow of agents in the future. This year, the motion dataset also includes LiDAR and camera tokens. The winning submissions that are shown here didn't use these new features, so there's an opportunity here to improve the state of the art by adding these additional inputs to the model. So in the motion dataset, each scenario has 1 second of history over 11 time steps and 8 seconds of future over 80 time steps. For the occupancy and flow challenge, we predict a total of 8 snapshots from these 80 future time steps. So not every time step. And that's mostly to limit the size of the submissions that we need to receive. And these snapshots are 1 second apart. There are 3 tasks or 3 disjoint predictions in this challenge. The first task is to predict the future occupancy of agents which are already observed. The second task is to predict the future occupancy of agents which are currently occluded and appear at some point in the future. For example, as you see in the middle figure, the ego vehicle, as it gets closer to the intersection, it may get to see some additional agents. The third task is to predict flow fields capturing the motion of all agents. In the visualization on the right, we see a sample set of flow fields. And the colors here represent the direction of magnitude of motion at each point. The metrics evaluate occupancy predictions using AUC and soft IOU metrics. Flow is evaluated by averaging the endpoint errors of the predicted flow vectors. But the main metric for the challenge for the leaderboard is flow-grounded occupancy, which warps occupancy according to the predicted flow vectors and compares that with the ground truth. So this metric requires both occupancy and flow to be correct. And the three winners for this year's challenge are DOPE from Nanyang University in Singapore, STNet from Seoul National University in Korea, and HGNet from Tongji University in China. Next, you're going to see 3 2-minute videos from these 3 winning teams.
Hi, I'm Hao Chen from NTU Singapore. Today it is an honor to present our work, DOTP, Differentiable Integrated Occupancy Flow Field and Motion Prediction, which received the first place in this year's Occupancy and Flow Prediction Challenge. Our team members are all from Automat Research Lab in NTU, directed by Prof. Chen Lu. Our research focus are autonomous vehicle system and human-machine collaboration. The general idea of proposed DOTP is to integrate the occupancy flow field prediction task with motion prediction, so that both prediction formats interact in social consistent manners. We leverage the priority-based modular code design upon a portion of our preceding work, HPP. We directly use StretchNet for scene encoding, which is the second place submission of this challenge in 2022. We proposed the MS-Occ to perform aligned occupancy decoding. To be specific, the MS-Occ used cascade transformer-based occupancy decoding for each future step. It designed agent condition occupancy decoding task for observed occupancy. Furthermore, a multi-stage integration between occupancy and the motion features are adopted with design screen multi-head cross-attention module, or SWMSCA, for local integration. DOTP performs state-of-the-art results in occupancy and flow leaderboard and gets substantial prediction improvement compared with our previous StretchNet mission. If you are interested in more resources of StretchNet and our work based on HPP, please scan the QR code below for more information. Thank you. Hi, I'm Hao Chen from
Hello everyone, I'm Gerhan, and this is our occupancy and flow prediction solution for 2024 Waymo Open Dataset Challenges. We are a team from Seoul National University of Science and Technology and Chungnam National University. First, let me introduce our representation. For a given scenario, we extract 11 frames from the past 10 frames to the current one. Each frame includes agent and static features, and they are 256 by 256 world-eye view picture maps. Each picture map has 3 channels. Therefore, the final input features are 2 tensors. 2 4-dimensional tensors, and their shapes are 11 by 256 by 256 by 3. This is our model overview. From input features, the encoder generates multi-scale features. The aggregator defines these feature maps, and then the decoder combines these features and generates one feature autoregressively. Lastly, the prediction path estimates the final occupancy and flow feature. This is our encoder structure. We base our encoder on the CA4 S18 backbone, but because it is designed for static images, we add temporal convolution blocks to handle temporal input. Next, let's talk about the decoder. This is part of our overall decoder based on one frame. Features are viewed horizontally from coarse to fine for multi-scale information. At the same time, they are viewed vertically, and this is an autoregressive process because it keeps adding a new feature from the start frame to current frame. Each horizontal loop produces one frame feature. Of course, the total number of these features is 8. They are stacked and then passed to the prediction head. This is our loss design. We use 3 losses. This is our implementation details. This is our results and visualization. You can find detailed solution in our technical report. Thank you. Hello, everyone.
Hello everyone, I'm Zhang Chen from Tongji University. It's my honor to present our third place solution to the occupancy and flow prediction challenge this year. This is the outline of my talk today. For the framework of our method, we utilize multimodal input, including vectorized and visual input, along with a transformer-based encoder processing this input to generate context tokens for subsequent modules. For the 3 prediction targets in the challenge, we designed a hierarchical aggregator and decoder. Flow is set as the first prediction target, and its high-dimensional features are used as guiding features for the subsequent layers, as they represent the change of occupancy. Occluded occupancy is the last prediction target, guided by both flow and observed occupancy. This approach leverages visible information features for reasoning and prediction of completely occluded objects. Specifically, we propose the feature-guided tension module, FGAT in short, to leverage guiding features during the feature extraction process. Additionally, for temporal prediction target, to enhance temporal relevance and consistency of the prediction output, we adopt the time series memory framework. This framework updates the temporal information hidden state within the time series memory container and outputs feature information from all previous prediction time steps for feature fusion. During training, we use focal loss and cross entropy loss for occupancy and smooth L1 loss for flow. Here are partial population experiments and quantitative results, demonstrating the effectiveness and advancements of our method. Thank you for listening, and if you have any questions, please refer to our technical report or feel free to contact us. Hello everyone, I'm Zhang Chen from Tongji University.
Yeah, that was the occupancy and flow challenge. Next, I'll hand it back to Nico to talk about the sim agents challenge, which is the 3rd challenge defined on the motion dataset. Thank you.
No. Did I just break everything? No. Okay. It's working. Yeah. Okay. Hi, it's me again. So this time I want to talk to you about simulated agents and the simulated agent challenge that we hosted again this year. So it's the second year in a row. So I would like to start from the very beginning. When you have an autonomous vehicle, what you want to do is to test it, obviously. But testing in the real world is quite expensive. So you need a safety driver, you need an actual car. So it's not really a scalable approach. What we usually rely on doing is testing in simulation before testing in the real world. And the main problem is that when you have a simulator where you test your autonomous vehicle, you want the simulator to be as realistic as possible because you don't want the car to learn something that is not would not happen in the real world, actually. And so this problem of realism is at the core of simulated agents and their evaluation. So simulated agents is just an agent that takes control of the dynamic object in a scene when you are in a simulation, and its objective is to have as realistic as possible behavior while interacting with the autonomous vehicle. In defining this problem, we are actually going with the canonical split between a perception system and a behavior system. So sim agents are defined at the level of a planner. So there is no central simulation, which obviously makes things more end-to-end and interesting, but also more complicated. So we thought of going with this approach. And the task in the challenge is to, starting from a 1 second history, you want to simulate forward for the 8-second that you have in the Waymo open dataset. So we published a paper about this benchmark last year at NeurIPS. I left a citation there. It's much more complete than what I'm going to say in this presentation, so please have a look. The main question now, it's like, how do you actually evaluate these sim agents? And our approach has been one of distribution of realism. So you want to have the distribution of behavior that you saw in the real world, and you wanted to compare it to the distribution of behavior that you saw in simulation, and you want those two distributions to match. Obviously, measuring what behavior is, it's a bit of another difficult problem. Our solution is to come up with several sub-metrics that we divided into 3 categories: kinematics, map adherence, and interaction. So kinematics is just like how you move, map adherence, how you move on the road, and interaction between different type of agent and on the road itself. We made several changes in 2024 that we are proud of. So some fixes in making things more stable. We changed the metametric weights, which made things more informative. And those are some simulation from the top scoring for submissions. I mean, they're not moving, so they're not really informative. So with this, I would like to announce the 3 winners of this year challenge. So we have in the first place Behavior GPT. So it's a decoder only model for simulation. We're gonna hear a presentation from them in a video. The second place goes to VBD, and the third place goes to Traffic Bots V1.5. We're also gonna hear a presentation from Google DeepMind team that was not included in this list of winners for obvious reasons, and they're gonna present in person here. So first of all, let's go into this video.
In this talk, we introduce Behavior GPT, a decoder-only auto-regressive transformer that simulates agent behavior via next patch prediction. Validating the safety of autonomous driving system via simulation has become more and more attractive, which enables rapid testing in diverse driving scenarios simulated at low cost. This work focuses on simulating the behavior of agents such as vehicles, pedestrians, and cyclists in the digital world, which is critical for efficiently validating and iterating behavior policies for autonomous vehicles. A good simulator should be realistic, matching the real-world distribution of multi-agent behaviors to support the assessments of autonomous vehicles' ability to coexist with humans safely. We formulate the agent simulation problem as next patch prediction. By forcing models to auto-regressively generate the next patch containing multiple time steps, which requires understanding the high-level semantics of agent behavior and capturing long-range spatial temporal interaction. We prevent models from leveraging simple shortcuts during training. Here is an overview of our modeling framework. We adopt relative space-time representation to equip the model with rotor translation invariance in space and translation invariance in time. Under this representation, we embed coordinate-independent attributes for agents and map elements, then utilizing relative spatial temporal procedural embedding to effectively maintain the spatial temporal relationships. On top of this, we conduct patching operation for agent states and tokenize the map elements, feeding the agent and map embeddings into a decoder-only transformer that operates at the patch level. The transformer decoder consists of 3 attention modules, including a causal self-attention in the time dimension, an agent map cross-attention, and an agent-agent attention. Based on the attention output, we employ teacher forcing to train the prediction head to perform next patch prediction. We assume the next patch distribution to be marginal and multimodal, parameterizing it with a next mixture model. For each behavior mode, We use an autoregressive GRU to generate the next stage step by step without relying on any teacher forcing. To train behavior GPT, we employ the negative log likelihood loss on the factorized distribution as formulated previously. Note that each ground truth trajectory patch is transformed into the viewpoint of its previous patch. Our behavior GPT achieves outstanding performance on the Waymo OpenSim agents benchmark, especially in terms of the mean ADE and the map-based metrics. Notably, our model only contains 3 million parameters, which is much more lightweight than other solutions. Our experiments show that using a larger patch size can improve the performance, which demonstrates the effectiveness of the next patch prediction paradigm. We also know that the frequency of conducting next patch prediction during inference can impact the performance. In our experiments, we found that conducting next patch prediction every 0.5 seconds works the best. In summary, we propose a decoder-only autoregressive transformer for agent simulation, which is simple and parameter efficient. Training the model to predict the next patch instead of the next state enables high-level scene understanding and long-range interaction reasoning in space and time, thereby improving the realism of simulation. During inference, the frequency of conducting next patch prediction also matters. Thank you for your listening.
Okay. Thanks a lot. And now we're going to have the presentation from Xinghua. You want to come here? Yeah.
Hi. So our approach is called a model predictive simulation using structured graphic models and transformers. This is John working with my colleagues from Google DeepMind. So we all know that a lot of great work on building bottom-up neural networks for motion prediction. They have achieved a great success, but we took a different approach. We think of how can we add top-down knowledge and make it better. And we use the graphic models. We think it can bring better controllability, robustness, also reliability. Also, we think PGMs there can act as guide rails against hallucination and false predictions. Also, more important, what we build is orthogonal and complementary to any of the existing work. You can just take your network at hours, and it will help you doing those simulations. This is our model. It's shown as a factor graph. So the nodes, circular nodes, they're actually states of each agent at every time step. And we add a bunch of factors. So kind of energy functions over those different state or different pair of states. We encode, so the actual energies we encode our priors like motion smoothness and linearity of motion, collision avoidance, etc. We also have factors that can encode the output of the motion prediction network. So everything is coherent inside of one single framework. Then we can sample from this model. That's how it works. Well, first we have a history, which is the scene and the agent past 1 second trajectory. So we put it into a neural network for motion prediction. In our case, we use MTR, which is because it's available as a public open source project. Then it essentially generates a proposal, list of proposed trajectories about the future rollouts. It may be suboptimal, it may collide, it may be non-smooth. So we put that into our PGM model, which will give you a smooth trajectory, also give you a score over all those possible rollouts and describing its compatibility with our prior. Then we can use this score to sort of the mean as an example from it. So once we get the output, we take the immediate next step, append to the history, then we repeat. So that's why our model is so-called model predictive. So it's a kind of planning to the deep future, take one step and replan again. We perform really well on the sim agent challenge. We're among the high tops ranked participants, and we score really well on those important metrics as off-roading and collision, etc., because those are where we included our prior knowledge. We implement our modules in JAX and make it work with MTR, which is open source project. This is just example of multi-model diverse behavior generated by our model. You can see this car going left, a car going right. You can see another car which is merging or which is following. Those are all created and simulated. This is also example of how our model can generate common traffic behaviors like unprotected left turn, merging, yielding, etc., etc. So to sum up, we build a top-down priority-based approach that can work with bottom-up data-driven neural network and yield really good results. Our approach is also complementary to existing bottom-up approach, and we can use this and shown to generate realistic and safe and diverse simulations for traffic simulation. Thank you.
Thanks a lot, Xinghua. Now we're going to hear from Zhenpei on the 3D semantic segmentation challenge.
Hello. Hi, everyone. I'm Zhenpei Yang from Waymo Research. Now I will be discussing the final open dataset challenge of this year, the 3D semantic segmentation challenge. We initiated this challenge back in 2022. The task of this challenge, wait, is this mic working? The task of this challenge is to produce a semantic class labels for each LiDAR point, given one or more LiDAR scans and the corresponding camera images. It supplements other perception tasks, such as 3D object detection, by providing a more fine-grained understanding of the scene. We provide point-wise semantic labels for 23 classes in a subset of the perception dataset, which amounts to in total 32,000 label frames and 4.7 billion label points. To evaluate performance, we compute the IOU score for each class and then compute the average across those IOU scores. This year, we focus on further enhancing the label quality. For example, we corrected some false positive cases of the motorcyclists, which were wrongly labeled as cyclists or motorcycles in our previous data release. We also reduced inconsistency in background labels across frames. Overall, we believe these improvements led to more accurate evaluations. Here are the results of the top 3 methods in this year's challenge. First place is PTV3 from the University of Hong Kong, Shanghai AI Lab, National University of Singapore, and Nanyang Technological University. Second place is Mixed Set 3D from Marvel Technology. Third place is V-Fuse Set 3D from Vision RD. All 3 methods achieve over 90% IOU in categories such as buildings, tree trunks, and workable surface. However, we can see there are still a lot of rooms for improvements for future participants in categories like lane markers, motorcyclists, and traffic lights. Looking ahead, we see several promising directions for future participants. This includes, but not limited to, integrating large pre-trained foundation models and utilizing self-supervised joint training with 1D LiDAR data. Now I would like to hand over to this year's winning team to discuss their method, Point Transformer V3. I also encourage you to check out the reports from the second and third place team, which I found to be also very insightful. Thank you.
Hi, everyone. My name is Xiaoyang. I'm a PhD student from the University of Hong Kong. Now let me briefly introduce our new generation of point transformers. The first solution for the 2024 Waymo challenge in semantic segmentation. PDV3 achieves sought-out performance on over 20 downstream tasks across indoor and outdoor, including semantic segmentation, instance segmentation, object detection, and data efficiency. We expand the kernel size from 16 to 1024, but still not reach a limitation. Compared with V2, V3 is 3 times faster in latency and 10 times more efficient in memory, which is even better than MakeUNet, known for its efficiency. PDV3 is motivated by our exploration of large-scale 3D representation learning technology, enhanced with multi-dataset joint training by PBT, another of our work set by the CVPR. We found that SparseUNet, which was proposed 5 years ago, is even stronger than point transformers, but still remain efficient. However, point transformers fail to enlarge the training scale due to the restriction on model efficiency. The observation encouraged us to assume that model performance is more significantly influenced by scale than complex design detail. We should prioritize simplicity and efficiency over the accuracy of certain mechanism. Then the efficiency will further enable scalability, which makes the sacrifice in accuracy ignorable and brings stronger performance. This formulates our scaling principle for backbone design. So what's the starting point for examining our scaling principle? We benchmark the forward latency of the point transformer version 2. We noticed that the k-NIAS neighbor query algorithm, which provide accurate neighbor points for point-based method, take up 28% forward time due to difficulty in parallelization. However, do these accurate neighbor points really matter for good local attention? The answer is not. Attention is adaptive, so we can trade the accuracy of neighborhood for better efficiency. Further, inspired by occupancy and flatformer, we decided to break the traditional paradigm, which treats point cloud as unstructured data and seek a way to transfer the point cloud to 1D structured data while still maintain the spatial proximity to some extent, so that we can benefit from the convenience of structured data and enable a huge leap in model efficiency. That is the serialization of our point transformer version 3. Specifically, we introduce space filling curves, paths that go through every point within a higher dimensional discrete space and preserve spatial proximity to a certain extent. The serialization of point cloud is achieved by sorting the points with the order traversed by the space filling curve. After that, the original unstructured point cloud turned to a structured 1D data. Then after the necessary padding operation, we can easily enable patch grouping for local attention with reshaping operation and utilize high optimized flash attention for structured 1D point cloud. Another issue worth noting is that the relative precision encoding, which is necessary for local attention, also take up to 26 forward time. We found that a simple prepend of sparse convolution is a good replacement for relative precision encoding. For some cases, sparse convolution is hard to deploy, so I suggest use O-tree-based convolution as a replacement. Penshu, as the author of OCN, has a one version fully written with PyTouch. So specific for this Waymo challenge, we launched the extreme version, which views additional pass-through frame as a reference and adopt a non-clipping proxy, which used to be crucial for sparse convolution. Finally, coupled with the model ensemble strategy, we achieved the strongest performance in Waymo semantic segmentation benchmark. The detailed setting and performance is as follows. Finally, we achieved 74.8% MIOU on the validation split and 72.8% MIOU on the testing split on the Waymo dataset. A more detailed illustration is available in our oral presentation and tutorial for point cloud processing. Please scan the QR code for detailed information. Thanks.
Okay, thanks a lot to all the participants. This is the end of the Waymo content with the last self-promotion. So we have a talk tomorrow by Drago, our head of research, at the workshop on data-driven autonomous driving simulation. There's a paper presentation on Thursday about most, and please stop by our booth. We're very happy to talk to any of you about career opportunities and why we are excited about Waymo. So yeah, please reach out and get there. So yeah, thanks a lot for being here. And yeah, with this, I hand over to Alex.
And I get my laptop back, which is that.
Sorry, I can't really see it. Can we remove it for a second? I don't see anything. Thanks. Oh, that's not required.
can,
However you like it.
The video, it's up to you.
It's up to you.
Oh, that's fine. Yeah, you can
Cool.
frame yourself. That's good.
Sweet. So I guess we're already set up. Let's just check the sound for a second.
Yeah. You can, like, other people. No, that's perfect.
Cool.
So we want to do here and here as well, or audio via audio codec?
Let's.
I think so.
Have a look.
Hopefully good. Hi. Good, good. Yeah.
Where are the settings again?
Here, over here. Too many things which can pop up.
Okay, the for USB audio codec. Yeah, and up on the headphones to Realtek. Okay, it doesn't show up.
I think this worked the last time I did it.
Okay, then let's try that.
We can just try. Should we? Oh, oh no, sorry. Again, maybe can we say something?
Test 1, 2, 3.
We were like, now we have this. Yeah, we need a. We will second us. I do also know for other facilities. And if we came back, we got them all talk. They're always really good. That's why you got so many. And the other one was during yeah, also there's some times where you could find out. I think that's actually more.
Okay. Yeah. So thanks for skipping the break. This helped us to get back on track in our program. And with this, it's actually a pleasure to introduce Alex Kandel. Alex did his PhD at the University of Cambridge, where his research interest focused on end-to-end deep learning for scene understanding and autonomous driving. In 2017, Alex founded the autonomous driving startup Wave. Since then, Wave has been the first to develop end-to-end driving on public roads in the UK and opened offices, additional office, except for the one in London, in Mountain View and Vancouver. And I think, yeah, they're really at the forefront of end-to-end autonomous driving. And yeah, with this, it's a pleasure to welcome Alex, and we are really looking forward to your talk.
Thanks, Alex. All right. Hey, everyone. It's great to speak to you all today. I've been giving a talk like this at CVPR, it seems like, for almost 10 years, and sharing perhaps the same message every year. And what's exciting me today is that after all these years, it feels like we are starting to see some of the results that give the substance behind the vision that we've been sharing, that end-to-end deep learning will be the way that we are able to bring autonomy to scale safely. So I'm pretty excited about that. And today, looking forward to sharing with you a number of some new results that actually we're sharing for the first time today. But I start off with this image, which is actually taken from a new data set that we're excited to release today, because for me, it really epitomizes the complexity of the physical world we live in. And if we're truly to get the benefit of being able to interact with and benefit from AI in the physical world, we're going to have to build systems that are able to deal with complex environments like this here in central London. So I'm going to talk about the road to embodied AI today. And of course, science fiction has some of the best depictions of embodied AI from, you can pick your favorite, from C3PO to Marvin the Martian and many others. But what's common among all of these characters is that they have the intelligence to understand scenes that include very open-ended kind of scenarios. They have the ability to understand language and build a sense of a relationship and trust so that we can delegate tasks to them. And that's very much, very much what I think we need to be thinking about how to build. How do we build systems that have the onboard intelligence to be able to delight us and for us to be able to trust, delegating tasks to them? An argument I'd love to make is if we take a step back and over the last decade and look at where the frontier of AI has been, it's been interesting to me how it's moved from different fields, from perhaps vision to language to where I think we're going to be going next. It'll all be about embodied AI. Why is that? Well, I think I'm a big believer in problem-driven research. Problem-driven research, I think, motivates some of the most bold ideas. And in particular, in machine learning, we've seen this recipe that a clear, a vast data set and a clear metric or benchmark or simulation system, these things is a recipe for just incredible innovation. And of course, that started with ImageNet, giving rise to everything from batch norm to ResNets. I think language, of course, recently has taken the cake with the enormous scale we see with text tokens and training. But what I believe is going to come next in autonomous driving is we're now seeing the ability to build truly world-class simulation systems. The scale of video data is orders of magnitude ahead of, and perhaps more open-ended than where we see, language or even sandboxed data sets like we've been dealing with in the past in computer vision. And I think coming into the open domain, and more importantly, the motivation to find a truly fundamental solution to the AI safety problem, I think this is what autonomous driving and, more broadly speaking, embodied AI can offer. So let's dive in a bit deeper. Before we do, I'm just going to really quickly talk about the work that we've been doing at Wave. And look, these slides haven't changed in the 10 years I've been speaking at these workshops. But of course, we've heard a lot today about the what some refer to as the classical approach to autonomous driving, but where the problem is broken down into different parts, many of which, of course, use machine learning today. But people often ask, are we really one end-to-end network? And it's actually the case. At Wave, we have built one single neural net that goes all the way from sensory input to trajectory output. It's a holistic neural network that's completely data-driven, learning how to understand the world and interact with the world. And I can, of course, show driving videos all day long, but here's just an example one from the other day in central London. As you can see, our vehicle coming up into a busy, unprotected right turn. Now, this car does not have an HD map. It does not have any LiDAR. It's, in fact, a camera-only vehicle that is able to learn how to cyclists pass us, yield for them, pull in, and actually figure out from the visual scene which lane it needs to be in, how to navigate into this far lane due to the roadworks, and to do all of the multi-agent navigation required to get through that complex environment. Just one example, but if you're interested, there's many more on our website. The promises of an end-to-end system for autonomous driving are many, but some of the more interesting ones for me are these four. The first one is perhaps less talked about, but end-to-end offers a much more portable system between compute devices. And that's because it's computationally homogeneous. It's, built from building blocks of neural network building blocks, but essentially it's a very streamlined, easy to optimize forward pass of a neural network. There's no multi-threaded different microservices that need lots of communications to go between them, but it is a very, in many ways, simple inference task. Of course, being able to generalize through data means that we can scale with a bit more experience to adapt to new scenarios, new vehicles, new sensor types. Ultimately, we want to build the most embodiment agnostic representation, and end-to-end learning is the promise of being able to develop a system that can learn what it can or can't see and how it can understand the world. Scalable and economic, of course, reduce the dependence of significant sensing stacks or HD maps, but I guess most importantly, produce the most safe and performance systems. We've seen this story time and time again, that end-to-end learning can outperform hand-coded rules, and there's nothing different about the embodied setting. So with that introduction, today I want to talk about three things that I'm really excited about, our whole team is excited about, and this is the culmination of so much work behind the scenes. So I want to give a huge shout out to all of our team that have made this possible, many of whom are here this week. So please come and say hi if you want to learn more, and I hope this can be the start of a conversation about some of the work we're doing in Embodied AI. But for me, these are three front of mind topics that we're going to deep dive: simulation, multimodality, and scale. So let's dive in. The first one on simulation. How about this as a title? End-to-end simulation for end-to-end driving. Well, today we're excited to talk about a new approach to simulation that we're releasing. But let me start off with by zooming out and looking at what are the outcomes that we need from simulation. Well, there are many different approaches to simulation that we've seen today. I've got 4 examples, but there are many, many more than this, from our Ghost Gym system to Waymo's simulator, of course, the open source Kala, Wabi. Well, there are so many, many more. What do we want to see from a simulation system? Well, I think the 5 key things to me are: we need to be able to close the domain gap, not just crucially in perception, but also behavior. We need to be able to simulate the complexity of the scenes we live in. Of course, the edge cases are often when you get car doors opening or debris on the road, and we can't just simulate rigid body actors, but it's really the deformable complexity of the world that becomes important here. Crucially, it's not just about rendering the environment, but actually simulating the full embodied platform, the latencies, all of the artifacts that come with running a full embodied stack. It needs to be data-driven and scalable. And again, going back to the title of end-to-end simulation for end-to-end driving, I think the same story we're seeing play out everywhere will be true in simulation as well, is that an end-to-end learn system will let us scale. And then finally, it needs to be controllable so that we can produce adversarial examples, we can simulate the long tail and things like this. Okay, so what I'm excited about today is that I think for the first time, we are starting to introduce a simulator which addresses all 5 of these. So let me explain how. To start off, I'm going to put together the different building blocks. So the first one is on, of course, neural reconstruction. It's incredible today that we're able to take simply video and in a self-supervised way, produce systems that can render complex scenes with near photorealistic accuracy. And we've seen this for a few years now, right? And so here's one example here in central London. So this is a base building block in such a system. This time last year at CVPR, we talked about Ghost Gym, which for us is our simulation environment that takes us as a building block, but produces a full closed loop simulator. It simulates our robot stack, the latencies, and everything we need to be able to drive in such a virtual environment. And we've been using this for some time at Wave, and it's a really powerful tool for us. But what I want to introduce today is, of course, neural reconstruction has been for years done in static environments. We are super excited today to introduce Prism 1, which is a self-supervised system that can reconstruct 4-dimensional scenes, so space and time. And here you can see some examples from either London or the San Francisco Bay Area. And again, this is a full data-driven, non-parametric spatial temporal reconstruction here. And so this can reconstruct dynamic urban scenes. And if you look at this example, one of the truly exciting things to me here is, of course, we see the thin structures, the incredible reflections in the puddles, but we also see the cyclists in front of us, the wheels turning, the feet moving, and it's incredible fidelity in a dynamic scene here that we can reconstruct. Of course, there's the pedestrians on the left as well, but our system Prism is capable of not just reconstructing static scenes, but from a single drive through here, we can replay and resimulate a full dynamic scene. Here's another example just to show the novel viewpoints that we can generate. Here, we're just driving forward with the sinusoid function. And if I can point out a number of different things in here. So sorry, we're rendering a sinusoid function as we go forward here. But this is, again, entirely simulated. You can see the complex reflections in the puddles on the road. If I point out the traffic light, you can see it turns from red to green. Again, this is a temporal factor that's traffic lights, car lights are often not considered. And then, of course, you see this pedestrian on the right with an umbrella, which is got incredibly high fidelity in its reconstruction. The super exciting novel view synthesis. Here's another example going through a central London environment. Again, the complexity is just, if you were considering a procedural world where you were to place all these different assets, it'd be a very complex one to reconstruct. But again, a data-driven method enables us end-to-end to learn scenarios like this. So you can see here, we're controlling the time dimension. We're placing a camera in 3D space and simply holding the camera still and controlling time. And you can see how we can have some quite fine-grained control and highly realistic resimulation and rendering of these scenes. And of course, in this one, some really challenging lighting conditions. See on the right, you can see the lens flare and all of the realism that you'd expect to see in closing that domain gap. This technology is truly exciting. One of the things we found when we were developing this technology is that there wasn't really the right data set for us to benchmark or develop this and really push the boundaries. So today we're also excited to be releasing WaveScenes 101. This is a start of a data set that we hope can motivate new work in this space. And so please check it out if this is research you're interested in, but it covers, we really aimed for producing the most diverse and challenging driving scenarios. Interestingly, it has a novel camera that we would suggest that we can use as a held out camera to test reconstruction quality. We've got cameras that have up to 2 meters of baseline between them. So some quite novel viewpoints that allow us to really benchmark the reconstruction quality in dynamic scenes. And just to really illustrate the diversity, I mean, here's some examples from light to rain to night, or perhaps more interestingly, here's that scene I showed you at the very beginning, complex central London. And if I've seen a challenging scene to reconstruct, look at that top one with all of the pedestrians and complexity crossing this path in central London. So we're excited to see how this data set might push forward this challenge of reconstruction, and is what we found really useful in helping to develop Prism 1. So Prism 1 is the rendering engine within GhostGym that allows us to render complex dynamic scenes. The fifth aspect that I described that's really a really important factor for simulation is, of course, controllability. And so I want to just touch on how we can use generative AI and other techniques to build on top of this to actually have more fine-grained control in the simulation scenarios. Firstly, I want to just recap Gaia, which is this time last year at CVPR, a model we introduced. It was really the first scaled up world model that we produced at Wave. It was a vision language action model that allowed us to take images, actions, text, and code them into tokens and run an autoregressive model to be able to predict the future and render this in high quality video. And we've got a full paper now published if you'd like to read more, but there's a ton of work in this space. And I'm so excited about world modeling because it offers a natural self-supervised task to build a really robust representation. And this figure just shows it's from one of these surveys that I'd recommend you read if you want to catch up on the space. But from the work Mile that we published a couple of years ago to Gaia to many others across the ecosystem, this is just an exploding space right now, which is super exciting. But here are some results from Gaia. Now, unlike the previous work I showed, which was simulated scenarios that was re-simulating environments that were driven through before, these videos are entirely created from scratch. They're synthetically generated, and you can see that we can control the weather, the day, and we can prompt the system and ask it to create a video and prompt it with an existing image we want to simulate forward from, or even just from scratch, or with a text prompt, or any combination of the above. But I wanted to talk about controllability. And so some of the capabilities Gaia offers is we can actually prompt the system. In this example here, we can force the ego car to drive to the other side of the road and create an edge case. And then you can start to simulate forward how we will interact in that scenario. And this is just an example of being able to control and create an example of an edge case that we may want to learn from in a safer way than, of course, we wouldn't want to see this in the real world. To give more examples, we can even use Gaia to build on top of Prism, which I just introduced. And so here you can see an example where we can prompt Gaia to render a vehicle within, for example, a cuboid, or we can point to a part of an image and ask it to create additional content. For example, here putting a vehicle, or here a bus, or 2 more vehicles. And now this is an interesting example on the bottom where all of the dynamic agents in this video are synthetically generated by Gaia on top of a neural rendering, on top of Prism. Now, the thing I'd point out here is if you look at the sedan that drives past us on the right, we've got 2 novel views here, and you can see that it's consistently generated between those views. I think that's a really powerful demonstration of controllability of the simulator, because we can add content on top, and it's coherent both temporally and spatially between these different sensors. And the final example I'll give within Prism is that we can, of course, remove and modify dynamic actors. And here you can see an example of a pedestrian inserted or deleted here, crossing this pedestrian crossing scene. You can also see, of course, there's a complete full dynamic environment with the traffic light changing and everything like this. So I guess just to sum up this section on simulation, what really excites me here is these are the building blocks of what I believe is a full data-driven simulation environment, GhostGym, that allows us to train the system in a data-driven way, control and create and understand edge cases, and of course, simulate the entire end-to-end stack, including the embodiment and the world jointly. I think this is the kind of tool that will be able to be scaled up. You know, as an arms race, of course, if you solve simulation, you solve self-driving and vice versa. But as we scale up our data-driven driving stack, scaling up our data-driven simulator will be a corresponding task. And I'm really excited for these things to grow and for the possibilities that it's going to open up for our learning. Awesome. Let's talk about multimodality. So second of the 3rd areas I'd love to deep dive. Multimodality has, of course, been a huge focus of the AI space recently. And I want to talk in particular about vision language action models, grounding driving or embodied robotics with language. This is something we've been working on for, I think, almost 3 years now. And at the start, you know, a lot of people were asking, why is language important for driving? One of, there are a couple of really key reasons here. Firstly, multimodality, of course, opens up many more sources of data to be able to learn from, not just, say, driving data, but of course, the broad diversity of internet scale text data. This opens up the possibility of learning more understanding about human values, common sense, other contextual reasoning that might go above and beyond the data we see in video or driving. Of course, it also creates the possibility of interaction and actually building a relationship or debugging or understanding how our vehicles are reacting. And that opens up a ton of interesting features for self-driving. So this time last year, again, just to recap, we introduced Lingo-2. Now, Lingo-2 was a vision language action model that was able to do offline visual question answering. And it was an interesting system, essentially using, we took video data, we were able to encode it and pass it into a language model, which we were able to fine-tune alongside text inputs, fine-tune it to output language about the driving scene. And we could, of course, keep feeding this in and have a conversation with such a model. Now, the interesting thing about this is that it was able to learn language understanding that was really grounded in the visual scene. And to show you some of the results, you can see on the left here, Lingo-1 was capable of commentating. Here you can see it's slowing down due to a jaywalker. It's describing quite dynamic and interesting scenes while our system is driven through them. And so it's able to commentate in an open loop setting, as in it can just watch these videos and commentate by jointly reasoning about the driving decisions as well as the visual scene. We could also do visual question and answer. You might not be able to read this, but we're asking questions like, what do you find risky in front of us? What do you see? And Lingo was able to say, look, there's a van on our left about to pull out, and it even spots a cyclist that's secluded on the right behind the vehicles. We were also able to demonstrate referential segmentation. And what this means is that Lingo would not just talk about what it sees, but actually point to things in the image. Here we're asking, what are you paying attention to? And you can see Lingo points out A, B, and C, this free space in front of us, the car in front of us, and the traffic in the distance. And we found that this referential segmentation really reduced the volume of, say, the likelihood of any hallucinations, because it had to ground its answer in the visual scene. But let me move forward from this there. So that was last year. I'd love to introduce Lingo-2, which is our latest multimodal model here. And what we're really excited about with Lingo-2 is it's the first model, we believe, in the world that is capable of closed loop driving. So what this means is it's not only not only reasoning through language, but it's also actually driving the car in closed loop. And this is something that we've demonstrated. It's a single end-to-end trained model that, of course, takes in the visual state, text, learn queries, navigation prompts, things like this. And through a vision language action model was able to output a conversation as well as drive the car in closed loop. You can read more details about it on our blog here that we put out, I think, a couple of months ago. So here's an example. So you can see us here driving in central London, and we're talking about, so this is actually Lingo-2 driving the car in closed loop, referring to the jaywalkers in front of us and commentating on its driving at the same time. Here's another example, which is quite interesting, where it's talking about it's keeping a steady speed, but then actually recognizing there's a bus and that it wants to overtake it. This is quite a complex thing to recognize, but it recognizes that the bus was actually parked at a bus stop before coming back into its right lane and slowing down for this traffic light. Or here's another example where it's reasoning about, again, an empty pedestrian crossing ahead of us. So some quite diverse examples. And I mean, this is not overfit, right? This is, these, of course, were not present in the training data. We've literally gone to the open world, driving in London. Of course, we can't control the weather or how other agents behave. And you can see the generalization capabilities that Lingo-2 has actually learned things that generalize and are grounded in a physical real world test in central London. Isn't it amazing what AI is capable of today? We can even test it further in simulation. So here you can see on the left, we've actually input a text prompt and we've asked it to continue straight or to slow down for the upcoming turn. And you can see that the driving policy changes its behavior based on the input text prompts. Or here's another one. Again, this is in Ghost Gym. On the left, we can ask it to stop behind the bus, or on the right, overtake the bus. And you can see the driving policy conforms to the prompt instruction that's fed into it. Again, if we go back to, if you remember the Gaia in painting that we talked about, in this one on the left, we've just inserted a car in front of us completely synthetically. And you can see in the bottom left with the inserted car, Lingo says it's slowing down to match the lead vehicle speed, whereas in the top left, it was increasing speed to match the speed limit. And on the right, again, we insert a car. On the top right, it says it's slowing down for the red light. And in the bottom right, it says stopping behind the stationary traffic. And so we can really start to use, I mean, this is an example of using Ghost Gym to be able to test counterfactuals and understand how our system, how the system behaves and operates in the world. Why is that interesting? Why is that important? Well, I want to leave this section with one thought, which was, I can often feel in self-driving of yesterday that when you get in a vehicle, it can often feel like you don't have much control. You get into a set vehicle, follow a set route, and perhaps these are some of the exaggerated, but perhaps some of the emotions that it might conjure up. And I think if we think about the true promise of embodied AI, if you go back to the science fiction characters as I introduced at the start, I think the real full potential of these systems is to produce a system that's much more like a chauffeur driver, one where we can build a relationship, delegate tasks to these intelligent machines, have them respond to us, let us know what they can and can't do. And I think language grounding is the path forward for this. And so one of the reasons why we're super excited about it, and it just opens up an incredible amount of product features and opportunities as a result. Finally, third section, let's talk about engineering to product. I wanted to talk about this because often, when I come to CVPR and talk about results, of course, papers I published, engineering results are never celebrated as much as algorithmic advances, and I'm sure we all feel that kind of feedback. But engineering is scaling laws, I think, are only limited by engineering. What I mean by that is that we are seeing no end to the ability to grow performance and capability with engineering scale, whether that's data or compute. And engineering is so important to make these systems a reality. And so I'd love to celebrate it, to talk about some of the ambition and the capabilities that we want to bring to this problem at Wave and what it might mean for a resulting system. So let's talk about what it's going to take these ideas, these research prototypes, and actually turn them into an embodied AI product that can delight the world, that people can have access to. So what we really want to do, taking a step back, is build a generalizable embodied AI platform. It should be agnostic to the specific vehicle it's on. If it has different cameras or camera radar or whatever sensor setup it is, we want to build an AI that knows what the sensors can or can't see and can understand that embodied platform. Of course, we will do this by learning from the most diverse data across the embodied AI industry. The other outcome that I think is really important to be able to enable this is to be truly excellent in inference and integration. This is can often be a grind against many engineering challenges, but being able to deploy the most intelligence per flop and to be able to have a system that has a hardware, software, fully embodied AI that is, is well constructed and architected together. This is perhaps the gap between a demo and a product. And the final point I want to make is really around safety. And I think the key word with safety is about predictability. These systems should be predictable such that we know what they can and can't do. We know when we can trust them and when we can't. So for me, these are sort of, taking a step back, 4 of the key things that outcomes that we want to create through scale of engineering that will be able to build this embodied AI product. So how are we going to do that? How are we thinking about that at Wave? Well, of course, we want to build an embodied AI foundation model. What is that? Foundation model is often a term that's thrown around, but I think one of the best definitions I've seen is it's a model trained on a diverse set of data that can be adapted to a wide range of tasks, different robots, different applications, things like this. Of course, these models really kicked off with language or language and vision, and there are many incredible examples in this space. But unlike, say, language foundation models or vision language models, embodied AI foundation models have unique challenges. Data is an interesting one. Of course, we can't just, if we're really talking about hundreds of petabytes of scale of data, unlike language data, you can't put it all locally on the compute node when you're training. We have to have enormous amounts of video data that we need to stream to compute nodes, where we sample and build curriculum that almost randomly can access this data across all of the petabytes. Scale of compute is a challenge. And then, of course, the embodiment, the physical world, the safety of deployment, simulation, all of these kind of things. We can't have a static train or test set. It's got to be a closed loop system that we're able to evaluate. All of these kind of things make embodied AI that one step harder. But of course, the opportunity is also one step greater. It's been exciting to see a number of foundation models start to pop up in the embodied AI space. And, we're super excited to see them from of course, RT1, RT2, many of the different manipulation data sets we're seeing coming out. There are many, many examples here. And, going back to my opening comment, I really think embodied AI is going to produce, has the best chance of producing the next AI breakthroughs. So what we want to bring to this problem at Wave is a scale of data and compute that the industry hasn't seen before. And of course, not just driving data, we are really bringing together all kinds of data from internet scale videos to other embodied other embodied experience, from humanoid robotics to domestic robotics, drones, manufacturing, of course, large-scale driving data. And one of the beauties of autonomous driving is that there are millions of vehicles out there in the world already collecting data and doing useful work, making it economic and effective to get access to this data at scale. And then, of course, the high-quality driving data that ourselves and our automotive partners are working with. But whether it's the fleets we work with or some of the compute giants like Microsoft and NVIDIA, bringing together this picture is what I think will make that promise of embodied AI possible. And here's just some examples. You know, if you can't learn a model that understands general purpose physical reasoning from this data, then I don't know what it's going to take. I think this data really provides a super diverse and quantitative understanding of the physical world. And so bringing that together will enable a foundation model that is truly, as we're describing in the past, truly task agnostic, truly generalizable, and enable these kind of applications at scale that can deal with all kinds of different sensor input or robot embodiments, and of course, all different types of tasks, from perception to an autonomous driving, from L0 all the way to L5 levels of autonomy. The final point I want to make on, I'd love to make on engineering to product is around actually building this into a safe system for automotive. And perhaps this is, you know, as a last point, being able to, we've spent 8 years building an end-to-end model and learning how to develop it quickly, how to understand it, and how to make it safe. And this is not a trivial thing to do. How you can create a safety architecture that can build a quantifiable behavioral or SOTIF safety case, and of course, something that's also functionally safe that can meet the needs and expectations in automotive, is not a trivial task. And what excites me about the architecture that we're building, which I'm showing here, is that we're able to achieve that while still being end-to-end, while still being data-driven. And this is an architecture that can scale all the way from L1 to L5 in terms of autonomy, from driver assistance, active safety and warnings, all the way to autonomous driving. We can learn safety features that are self-supervised and data-driven, and allow us to build an understanding of the world allow us to build a system that can deploy such a foundation model that can grow with increasing amounts of data. So that's really exciting, and something that I wouldn't underestimate as being really important to deploying these systems. So I hope that brings together a picture of some of the frontier challenges that we see at Embodied AI at Wave. But to conclude, let me finish with these points. I really firmly believe that embodied AI will be the next frontier of AI. And more importantly, self-driving is the way to build it. It's the way to get access to data. There's a viable commercial model, and there's a really clear imperative to build this technology because of the benefits it'll bring to the world. We talked about our new simulation system and dataset we're releasing, Prism and WaveScenes 101, and how we can build an end-to-end simulator without the need of a scene graph that can deal with the complexities of where we need to operate. We can build trust through multimodality. And then finally, and most importantly, I'm so excited to have the opportunity at Wave now to take this technology, to take these research concepts and actually engineer them into a robust product and see this deployed throughout the automotive industry. I hope this is the start of a really engaging conversation this week. Thanks so much. We are growing our team across our sites in London, Silicon Valley, and Vancouver. If this is a challenge that interests you, I'd love to chat this week. We'll have a booth in the expo, so please come and say hi. Other than that, thank you, and I'm very glad to take any questions. Cheers.
So since we are a bit over behind time already, maybe we can limit it to one question. Is there a question from the audience? Otherwise, I've seen that there are some in the Zoom chat.
There's one here. Hey.
Now it works. All right. Well, first of all, inspiring work. Thanks. I was wondering, you showed that you can place new actors in scenes. Do you have a good way to automate that? Maybe a generative model as part of Gaia, I don't know. But if you want to populate a scene with pedestrians in a realistic way.
Yeah, that's a great question. In short, we're working on it. I think the thing that's really been incredible to me is things like AlphaGo, right? Where the amazing thing about AlphaGo is it was able to produce a adversarial system that could play itself to produce a robust behavior that drilled down into those edge cases for such a system. And I think I'm really excited to see the simulator that we can use in a way where we can find adversarial placements of these in a way that tries to challenge or disrupt the driving policy that we have. That's something that we're working on. It is an open problem. Maybe we'll have some results to share next year. Watch this space.
Cool. Yeah, thanks.
Yeah, thanks again, Alex. It was great to have
Thank you
here.
No, he's again.
But can you hear me now?
He was on mute. He was on mute.
Oh, you
Let's try that first.
Can you hear me now?
Yeah. Yeah.
Okay, good.
Speaker notes. Side. Can even make it smaller, but never mind. It's good. Okay. Are you ready?
Yes.
Good. Then let me introduce you. Okay. So last but not least, it's my pleasure to introduce Yorgos Pavlakos. He's currently, how did he butcher you?
Very good, very good.
So yeah, he's currently assistant professor at UT Austin. His research focuses on computer vision, with a particular interest on 3D human pose estimation, reconstruction, and tracking from images and videos. Prior to his faculty position, he was a postdoc at the UC Berkeley, advised by Angyu Ganasava and Jitendra Malik. He holds a PhD in computer science from the University of Pennsylvania. Please join me in welcoming Dr. Yorgos Pavlakos on the stage. It's a pleasure to have you here.
Thank you. Thank you. Thank you very much for the introduction and for the invitation as well. So
it will be a bit of a change of pace here. I will talk about work on perceiving humans in 4D. This is not specific to the self-driving scenario, but I think this is a problem that is very important in this setting. So you want to be able to predict where a pedestrian will move in space, what their gestures mean or they want to indicate. You want to react quickly. If you see a kid running in front of the car in the street, you want to avoid collisions at all costs. So it's important for this setting how people move in the world, where they are, what they intend to do. These are all very crucial questions. So the way I'm studying the human perception of humans is in 4D, as I say. And what I mean with that is, let's see this unconstrained video where people can move freely. If I pose to a particular frame here, this effectively gives us a 2D observation of the world. Meanwhile, the true state of the world in this setting is, in this case, is 3D. So you see people that have 3D bodies and they can occlude each other. They can, some of them are closer, some of them are further away. And this extends similarly to video. In that case, the observation is 3D, X, Y, and T, so a spatiotemporal volume of pixels, whereas the true state of the world is 4D. So people have 3D bodies and they can move over time and in the space they have. So these are quintessential inverse problems that we are trying to solve, from an image to 3D, from a video to 4D. And we have been making a lot of progress in the last few years. So we can apply these methods for human reconstruction in the wild videos and get the pose of and shape of people. We can handle different poses, different viewpoints, even placing different people in the same coordinate frame, and do this in a coherent way. And the goal, of course, is to do this from any image possible. So, for example, if you give me an image of that includes some of my advisors, I want to be able to reconstruct this in 3D and be able to look at them from different viewpoints as well. And okay, in computer vision, we like to stand around posters. You will see a lot of us these days, but we really want to do more. We want to be able to capture poses and motions that go even beyond that. So our quest is really towards trying to capture any human motion. And this has been something that we are struggling with. So here, I will show you some results from our state-of-the-art models that we had roughly 2 years ago. So this model used to work well with very standard poses, but then the moment that you see something that is not very common in the training set, maybe an unusual pose or like unusual lighting, maybe more truncation, occlusion, this started failing. And this is not specific to this video. This is not cherry-picked. This is the most this is a known behavior of this model, or it used to be, because we think that we have had the breakthrough here. So I will show you how. I'll show you the before and the after here. And on the left, you can see what our model from 2 years ago looked like. And on the right, you see the reconstruction we get with our most recent work. And here, we don't apply any temporal smoothing on either of these methods, specifically particularly on the right. There's no temporal smoothing. This is frame-by-frame processing. We are able to handle much more challenging motions. You see smooth reconstruction for the duration of the motion here. So how do we do that? This is part of our Humans in 4D paper. This is work that was led by Subham, jointly with Jatsan, Angzu, and Jitendra. This work done at UC Berkeley. So this follows on this direction of human mesh recovery. This is the very common way to address this problem in a feed-forward manner. So you have a single image of a person as input. Then you have a network, this HMR network, that takes the image and estimates the parameters of a parametric model of the human body. So we have a simple parametric model of the human body, and this network regresses the parameters of this model for the person in the image, the pose, the shape, and the camera here. And you can pass these parameters to the parametric model and get a 3D reconstruction in the output, which you can rotate as well and see it from different viewpoints. This is pretty standard at this point. What we did with this next generation of systems of what we call HMR 2.0 is scale up when it comes to both the model we use here and the training data. These are the key, the two key ingredients here. And beyond that, we try to keep it as simple as possible. So for HMR 2.0, we go from this convolutional encoder to a fully transformerized design. So we adopt this VIT backbone that takes as input this tokenizes the image and takes the tokens as input, and after processing gives these tokens to the transformer head that estimates the pose and the shape of the person in the image and gives us the same 3D reconstruction as I showed you before. So very much same architecture, just we can scale it due to the properties of the transformers. We can scale it up much more compared to what we could do with convolutional networks. The other aspect is, of course, training data here. This is very important. You see here what we used to employ in this space. We had this a number, roughly 500,000 images, but most of those were in these studio settings. Now we actually go in the wild, we collect a large number of in the wild images, and we use a procedure for pseudo labeling these images. So first we detect the 2D key points of the person in the image, and then we fit the parametric model to the person in the image, such that the projection of this of the joints of the parametric model aligns with the 2D key points that we detect automatically on the image. So this gives us an order of magnitude more images, so roughly 5 million images with this pseudo ground truth, pseudo annotations. So I can show you how it works. I will keep some of these videos playing just to convince you about the robustness and the precision of our model. We tried it on videos from rhythmic gymnastics or from artistic gymnastics. This is from skateboarding. And again, all these are per frame results, so no temporal smoothing is applied here. And we use a single model for all the experiments. We can do diving as well. So we tried to really stress test this as much as possible. And here are some results. We tried it on skating, and this was one of our highlights here, because our advisor Jitendra has been working on this particular video sequence for almost 20 years. He has made students work on this sequence for almost 20 years. And this was the first case. Yeah, the proof is in these papers. This was the first time that we could actually get this level of this quality of results in 3D for this particular video. So this is qualitative proof of how this system works. In terms of the quantitative performance, makes sense to use it to evaluate this method directly on the most popular 3D benchmark, 3D pose estimation benchmarks. And what we observed is that our model was marginally worse, or was performing the same as what these previous works were reporting in these benchmarks, which kind of worried us in the beginning. And then we started thinking how these benchmarks actually look like. So many of these data sets are actually taken, many of this data is collected in indoor settings with same participants doing the same actions in the same scene, or doing some very limited actions and motions in this space. So it makes sense for these previous works, and actually some of these previous works are training on these data sets as well, not on the test sequences, but on these similar settings. So it makes sense to have this slightly more overfitting of the results when applied when we evaluate on these settings. And in fact, we're not so discouraged by this difference in the performance, because it was easy for us to get to improve the performance on this particular benchmark. So with yellow, you see a model that we trained that performs optimally on these benchmarks. But what we actually wanted to achieve was a robust model that would behave very well also on the in the wild case as well, that are the most challenging ones. And here is where our model actually shines. So when we evaluated on more diverse data, we could actually get a more consistent boost compared to previous work. Let me show you some more comparisons with this previous work. So on top right, you see results from our approach, and then on the bottom, we have previous state-of-the-art works. So our approach works consistently better in these settings. And the other way that we wanted to use this work was actually as a model that you could really apply and solve many downstream problems in this setting beyond just the estimating the pose of a person. And one way that we operationalized that was through the problem of tracking. So we addressed the tracking as 3D tracking. So from a video, we're getting the 3D reconstruction of the people, and then trying to solve for the association in this video. So getting this tracking the identities here. And this was done with 3D features, not with just 2D features. And again, we employed that to be able to both reconstruct and track people in the video. So keeping track of the identity here, even in these more challenging cases where there are occlusions, where one is might be occluding the other for a little bit, or even more extreme cases, as these wrestling videos here. And in general, yes, we did evaluate on the tracking setting as well. And the results we report are favorable compared to the state of the art, particularly, again, on more challenging cases. So this is just a summary on the tracking performance on the post-track dataset, and where our tracking method outperforms previous baselines, both 2D and 3D tracking systems. So this summarizes our 4D humans work. We have released the code, training code, testing code, the models. We have a hiding face demo, like a collab demo that you can try. All the code is on GitHub. So just go ahead and try it and see if you can break it. Actually, we're curious to see cases where this wouldn't work well. And if you are already working in this space, I believe that this would work very well as a drop-in replacement for what you might have already been using for pose estimation. So we're very happy with this, and particularly with these results. But we're still thinking that we were very far from actually having something that could solve this problem. And just to demonstrate one of the weaknesses that we had here, I want to show you this. Yes, so this video where we track people in this video, you see a little bit of jitter here. So this is not completely smooth. And things become even worse if you actually observe this from a novel viewpoint. So what you want to do when someone shows you this type of 3D results, you always want, from monocular input, you always want to observe this from a novel viewpoint as well. And here you see that the jitter in the results is much worse here. So you see people, although you know they are mostly static in the space, they can actually translate much more than what you expect. They are not in the same row as you expect from observing the video. And this is for a video with a static camera. If the camera is actually moving, things become much worse. You see people translating in space, and you get something that's completely incoherent here. And this is where our next work come into play. This is what we call slammer for joint motion camera tracking and motion reconstruction of humans in video. This is work led by Vicky together with Jitendra and Angzu again. And our main insight here is that when you watch a video like this one, you see the person running from left to right. That's what you perceive this person actually running from left to right. But if you actually go in the pixel space of this image, you see the person being almost always at the center of this image. So if you didn't know that the camera was moving here, you wouldn't perceive the person as running in this space. You understand this because the camera, you perceive the camera also moving here. And this is a very standard problem of this pipeline. So you see how yes, again, for this video, the reconstruction that you could have with a standard system is what you get on the bottom left, where the person is actually running in place with a static camera. That's the only way to model the 3D scene. You assume that the person is running in place, the camera is static, and the person is not translating. Whereas what we actually perceive, I mean, this is very different from what we actually perceive. And what we perceive is what you see on the bottom right here. You actually see the person running from left to right and the camera actually translating in space. So the main insight was to actually jointly model both the human and the camera motion here. And the details of how we do this is an optimization approach where we first take a video. Using the 4D humans work, we are able to get to track all the people in the video and get an initialization of their 3D poses. The key ingredient that hasn't been leveraged before here is tracking also the camera motion, and we do this with a SLAM system. We use Droid SLAM here, primarily because of its robustness. So when we have both this 3D perception of the humans in the camera frame and the camera motion, we can actually pose this optimization problem and jointly solve for the coherent 4D reconstruction, which will take into consideration both the camera motion and the motion of the people in the space. So here people are actually moving coherently in the 3D space. And as I said, this is an optimization approach. We have a number of objectives to optimize for this for its video separately, and the objectives are related to reprojection of the person in the image. So we want its 3D body to project where we expect them to be in the 3D space. We have some priors, pose priors, and say priors for the people in its frame, plus a number of plus a motion prior, so that the person is moving coherently in the 3D space over time. And finally, some environmental constraints. These are related to, with these, we want to avoid foot sliding, or we want to avoid the feet penetrating the ground here. So it's this, again, optimization approach that we optimize each video separately, and this can also be slower, unlike the 4D humans work, which does all the inference in a feed-forward manner. Now, for some of the results, I want to show you on the bottom, the top right here, you can see the baseline that is not actually using the camera motion. So you see that the motion of the people in space is quite incoherent. The people never come close to each other. The baseline, the single frame baseline, is more coherent when it comes to relative position between the two people, but it's still very noisy. You can get the best of both worlds when you actually combine, or you actually use our approach that combines both the camera motion and the person motion in space. In terms of the results, we achieve a very strong performance. Again, on this setting of when we consider the global trajectory of the people in space, not just their local pose, but also how they move in space, how much space they covered in the video. Here is like our approach, Slammer, and yeah, we have these are results on the ego body dataset, and we consider two different metrics, both global position, global location error, and acceleration error. And let me show you some more results of this. Again, with challenging cases, this can work challenging cases with many people where there can be a lot of occlusions. You put the people coherently in the 3D space, which is actually what we need in many of these applications. We want to know exactly where each person is in the 3D space, not just infer their 3D pose. We want to know how much they moved and which direction they were heading. And we can also handle like more challenging cases with a bit more occlusion or more extreme camera motions and these unusual motions as well. And when you combine this with 4D humans, you are able to get both these smooth poses that I was showing you before for these sequences, both the smooth poses and the reasonable motion of the person in the 4D space, in the 3D space. So again, here, this is a case where the athlete is always at the center of the image, yet you can see actually how the person is translating in the space during the video. So this is our Slammer work. Again, we have the code and the demo available for you to use. This builds on top of the 4D humans work. So just go ahead and try it if this is relevant for your application. And I would like to briefly mention some of the other frontiers that we're pushing while we're dealing also with these problems. So another direction that I didn't cover is better human and scene reconstruction here. So we have work also in this direction where we'll try to jointly reconstruct the people and the scene from data coming from TV shows. With this pipeline that we are building, where we are both tracking and reconstructing people, you can extract even more attributes from these representations. Here, we use this for action recognition, where at every time frame or at every short snippet, we are also predicting the label of the action of the person, which can also be useful. And another attribute that we can extract from our representation. And then again, from other frontiers that are also aligning with CVPR, we have work that studies human-human interaction and close interaction. So considering also the contact of people, this is work led by Leah, and we present this on the poster session on Thursday morning. And these are cases where previous works are struggling a lot because you have very heavy occlusions because they don't consider because they consider each person independently, so it's more common to have interpenetrations. Here we can model the contact more accurately. Something that could be interesting here is follow-up work that are actually trying to put this Slammer reconstruction into a simulation environment and being able to control each character separately, which will allow us to also inherit some of the advantages that the simulation environment can have. So maybe avoiding for free the collisions between the different characters, or avoiding sliding effects. So this is a work that is presented on Wednesday, and this was led by Nicholas. And finally, we are also, have work on building realistic avatars. I didn't touch on that either. We were mostly focusing on the perception problem, how to get an accurate 3D representation. On top of that, you can build another layer and have a better capture of the appearance of the person as well. And this is a poster that we're presenting on Friday morning. And with that, I would like to thank all the collaborators for these works. I'm very indebted to all of them and very grateful. And I would be happy to answer any question you might have. Thank you.
If you have a question, you can come to the microphone.
Hi, thanks for the very nice talk. So like we've seen in some of the previous presentations that for things like prediction, like taking the map into account is very important. So in your work, you haven't considered that. So is that something that you think could help?
Yeah. No, absolutely. I mean, I didn't touch it here. We think with the most recent works, we are actually trying to at least ground people in the same works in the same world. So here, everyone is in the same world coordinate frame. I think that in general, considering, I mean, I call this scene reconstruction, or like considering also the scene or the environment where the people are. This is something that is like part of the agenda going forward. And of course, it's very important. Like, I mean, I would like, I think, at least for these applications, it's very important to know, okay, so here someone is sitting here, or like they are standing on the floor, or they are walking on this on the road, or they are whatever action they might be doing, lying on the bed. This is very important for us, both for reconstruction and for prediction, or potentially even more for prediction. But we have only more limited. I have more limited examples of
So
that.
follow-up question is: in the models, architectures that you have,
yes,
is it natural to encode the scene?
Yes, that's a very good question. This is I wouldn't say that this is natural. There are ways to integrate it, but it has been much more challenging. I think that this is partially why there hasn't been so much work on that. People are using some features, or they are using some part of the geometry, but it's not. I think it's not as because it's harder to integrate it. It's not as impactful as you would like to be.
Thank you.
Mm-hmm.
Yargos, thanks a lot for your interesting talk.
Thank you. Thank you.
And with this, I think it's time to end today's workshop. It was a pleasure to have you all here. Again, a huge thank to all the speakers, and of course to all the organizers which make this workshop possible. I think I was here a bit in the center, but you have seen how much work it takes from all people to make this work. So thanks a lot to all the organizers. And with this, I think it's time to end, and have a nice evening.
The last slide on. Or take it down.
Good to see you. How are you? So, nice to know you. Let's go. Yes.